Hey guys, and welcome to a new video. In this video here, we're going to take a look at the new framework from RoboFlow called AutoDistill. It is basically using like the foundation models like segment anything and also grounding Dino to go in and label your dataset automatically. You don't have to do anything. We'll just have a dataset, a custom dataset that we want to train an object detector on. We basically just have the images. We don't have to label them. We throw them through the AutoDistill framework. It will label the images for us, and then we can go in and train our own custom object detectors like a YOLOv8 model on our own custom dataset without doing any labeling. So let's now just jump into the GitHub repository and take a short look at it before we're going to jump into our Google Colab notebook, where we're going to go over, we have a custom dataset, how we can set it up, how we can label it with these foundation models, label our dataset, train a custom object detector with YOLOv8, and then we can use that to run inference on our edge devices or on our computer. I have videos about all of those different things. I also have courses with my YOLOv7, also my YOLOv8 course. We both cover object detection and object tracking in those. But here we're basically just going to take a look at the GitHub repository. AutoDistill uses big, slower foundation models to train smaller, faster supervised models. So they're basically just using like grounded Dino together with segment anything to go in and do few shot and zero shot learning for these object detection models. Here we can just like scroll through it. This is the example that we're going to use. So this is an example output where we're going to detect these milk bottles in a production line. So this is a very nice and useful specific case that can be used in a real life scenario for a production setup where we want to detect these milk bottles in a production setup on these conveyor belts moving around in the factory. So this is a really cool one. We basically just have a data set with all the images. We have no annotation, no labels for all of these objects. We will just throw it into AutoDistill framework, and then we can train our own custom object detector with the YOLOv8 model to go in and get these nice results. So we can see we have some different kind of like features, pluggable interface to connect models together, automatically labeled dataset. So this is really, really cool. We don't have to spend a lot of time actually labeling our dataset. We can just do like faster prototyping. We can do a lot of different kind of stuff with this new cool framework. Train fast, supervised model. We can own your own model, deploy distilled models to the cloud or to the edge. So we're basically using these large foundation models that understands like complex scenes going on, like complex objects in scenes. It can actually just learn that there's a milk bottle in the image. We don't have to do any labeling. It just knows like how it looks like. Then it uses the segment anything model to go in and get the actual bounding box and also the segmentation mask. So this can both be used for segmentation problems, but also for object detection. So we have the basic concept here. We won't really go into that. We have the task, we have the base model. So these large foundation models is used as a base model. We also have this ontology, which is basically just a mapping from the classes or like what we actually want to detect to the classes for our dataset. We will create a dataset, and then we can have this target model at the end and also a distilled model for the final output. Here you can read a bit about like the theory and also the limitation. Again, we have the base model with the grounding Dino, SAM, and Dataset here. And then we can go in and train like YOLOv8 for instance segmentation, object detection. We can also train all the other different kind of like target models that we have. So this is a really cool framework. We don't have to spend any time on actually like labeling our images, especially if you just want to test some different like data sets out. If you have a video of a production line, you can basically just extract all the images, use it with this framework here, train your own custom object detector, and then you basically have like a deep learning AI model running. Here we can see like how we can install it. We're going to go over that in the Colab notebook as well. You can also see like how we can distill a model here in a custom Python script. We're going to do that in another video. So in this video here, we're just going to see how we can train it. Then we're going to create it with our own custom Python scripts in other videos. We can also visualize our predictions here. Down at the bottom, we can see like object detection with grounded SAM, grounded Dino, and then also all the different kind of like target models up here at the top. So DTR, YOLO-nas, YOLOv8. So we have all these new state-of-the-art object detection models and also instant segmentation here with YOLOv8. So this is really cool. Okay, so we're not jumping into the Google Colab notebook. We're basically just going to scroll through it. I'll explain like what's going on and how we can use it on your own custom data set. Here in the start, they basically just have something like what is the framework. We basically just went over that in their GitHub repository. So we're basically just going to scroll through that. First of all, make sure that you choose the runtime. You use the GPU here in Google Colab. So here I'm going to use this GPU here. We can also choose the GPU version that we want. So I'm going to go with an 800 because I'm on the pro version of Google Colab. We're also going to choose high RAM down here at the bottom for our runtime shape. Then we're going to connect to our runtime and we can go down and actually run our code blocks. So steps in this tutorial here, before we start, we have our image dataset preparation. We're going to auto label the dataset, train the target model with the YOLOv8 model, evaluate that model. We're going to see the results, so the training graphs after we have trained the model on our auto labeled dataset, and then we're going to run video inference. We can also upload our dataset and model to RoboFlow at a later point, but in this video we're going to see how we can do video inference. We're also going to export the model, and so before we start, we're going to have this NVIDIA SMI, so we can see all the details about our GPU. So again, we have this NVIDIA 800 GPU available. I'm just going to zoom in here a bit so you guys can better see what's going on. So here we can basically just see we have this NVIDIA GPU. We can also see the number of megabytes we have in our RAM. So here we can see we have 40 gigabytes of RAM in our GPU, which is really good. So let's not just scroll down and install auto distill and see how we can set it up. First of all, we're just going to pip install it. So we're going to pip install auto distill grounded SAM, and also auto distill YOLOv8 supervision for visualizing the results later on, both from our grounded SAM model and also our target model with YOLOv8. So here, first of all, we're just going to install it. After this is done, we can basically just go down and get started, like trying out doing auto labeling of our dataset. So this might just take a couple of minutes, and then it's actually just set up. So down here, we're just going to import our OS. We're going to get our home directory on Google Colab here. So let's just do that. We're just going to run it. So right now we're in our home directory, which is our content directory. If you go over here to the left, this is basically our content directory. So now we can go in and do image dataset preparation. We're just going to create a directory called images, where we're basically just going to download our videos or like our images to, and then we can use those to feed into our grounded Nano model, the same model for actually labeling our dataset. So let's just go ahead and create a directory. We should be able to see it over here to the left. So here we have our image folder. So here we can download raw videos. If you have your own dataset, you can basically just skip these steps. You will also already have like all your images inside your dataset. So this is basically just for like downloading a video. Also, if you have a video, you can use that as well. And then we're going to convert our videos into images, basically just extract our images from our video that we can then use in our dataset to do auto labeling. So I'm just going to like create a new directory here. So we're going to create this video folder. We're going to cd into it, and then we're going to use vget to go in and download this video from Google Drive. We're going to unzip the video. So we also over here to the left, we should be able to see our videos. So we have this video, and then we have the different kind of like videos down here at the bottom. So we have these milk bottles that we want to detect in our image, as we also store on the RoboFlow GitHub repository. Now let's just scroll down. We can then convert our videos into images. We're just going to create our path, or like set our video directory path, and also our image directory path. And then we can go down and basically just extract all the images from our video. So this might just take a couple of seconds as well. After that, we can go down and display an image sample from our dataset. So let's just visualize what we actually have in our dataset. So first of all, we just need to wait until this has finished. So it took just around like 1 minute to actually extract all the images from our video. And before we're going to build a model with AutoDistill, we just verify that we actually have everything stored in our folders. Let's just go up and verify that as well. So here we have just extracted all the images from the video inside of our images folder. So over here to the right, we should be able to see an example when it has loaded. So this will be one of the images that we're going to feed into the AutoDistill framework and do auto labeling of these milk bottles, and also the caps on top of the milk bottles. So again, this is just really cool that we can do this. We don't have to like label our images. We just have a single video, throw it into it, extract the images, and then we can do auto labeling of our dataset, and even train like object detectors on that. Have a video, just tell our model, I want to detect milk bottles in this video, and then we get the detections. We can use it to train our own custom models. This is just really cool. So just go down and display an image example. So image count, we have 132 images in our dataset. Let's go down and visualize it. Here we're just going to plot like an image grid of all the images, or like some of the images that we have in the dataset. And here we can see some of the examples from our dataset. So we just went over like one of them, but we can see we have all these images with milk bottles and also the caps extracted from a video of a production line with these milk bottles. So these are some pretty good images. Let's now see how we can actually use auto-distill to also label our data set. So first of all, we're going to define something called an ontology. And ontology is basically just like how our base model is prompted, as it also says here, and also just describe what you actually see in your data set and what you want to train your targeted model on. So this is basically just like the mapping from the prompts to the actual classes that you want to detect. So in this example here, we're going to prompt it with milk bottle, and then the class for our target model will basically just be bottle. And then we're also going to prompt it with blue cap, and then we're going to map that to a cap in this data set. So we're going to have two classes in our data set that we want to predict, or like two classes. So we have our bottle and we also have our cap. Then we can initiate a base model down here and do auto labeling. I'm just going to run this first of all because we have to define this ontology. This is one of the things that we need to specify. We also have the base model, target model, and all those different things that were listed in their GitHub repository. Then we're going to set our data directory path, and now we can go in and use auto-distill _ grounded SAM. And then we can import a grounded SAM. We set up our base model, and then our base model is initialized with our ontology for the different kind of like classes. So we throw in the prompts, we get the classes out, and then we can label our data set after that. We're going to create an instance of our base model, and then we can just set our data set equal to our base model dot label. So to have a method called label that we can directly call on our base model. We throw in the input folder. So this is the path to our image directory, the extension of our images. So we're going to use PNGs, and also the output folder where we want to store our data set. And we're also going to just return our data set here. And this data set here is basically like our whole labeled data set. We only need to initialize this grounded SAM model. It will do anything for us. We just need to initialize it with our ontology as well, our prompts for how it should label our data set or auto label our data set. So this is just really cool. Like we import it, initialize the model, and then we can just call this label method, and it will do everything for us. Like this is groundbreaking. This is definitely going to save a lot of time in the future. It is just so cool. So here we will have our data set. Let's just run it and see it. We'll have our data set. We also have our output folder, which is set equal to the variables that we set up at the top. So trying to load grounding Dino directly, downloading Dino model weights. So this might actually take some time. We have to first of all download the weights, throw it through, throw all the images through it, also label them, and so on. So here we can see that it downloads the model. So it might take some time here. So that was it. Now our whole data set is also labeled with this new auto-distill framework. So again, it took around a couple of minutes, so maybe 3 to 5 minutes. Now we have all our images labeled. We have 132 images labeled. Let's just go over here. We have our data set. We have all the annotations. So let's just open that. We probably shouldn't do that with 132. We also have our images. We have our train and also our validation split. So we can go in and see all the individual images that we have in our data set. So now we have our whole data set also labeled. We just went through the whole Colab notebook here. We ran a couple of code blocks, and now we're actually here with our own also labeled data set. So now we can go down and display a data set sample. So we're going to set our annotations directory path, our image directory path, and also our data YAML path. So we're just going to set that. And now we can use supervision to go in and create the detections for our data set from the YOLO format. We basically just set up the different kind of directories that we want to use, and we can set up the length of our data set, which should return 132 as well, which is the number of images that we have in our data set. So here we have 105 because we're only using the training images, I think. Yeah, that's correct. And now we also have supervision to go down and create our image examples. So we basically just have a for loop running through all the image names, creating these annotation images with our mask and also the box annotator from supervision. And then we're going to plot our image grid again down here at the bottom with the samples that we have from our dataset with our auto labels. So we might just take some time here before we're going to see the results. Here we go. So now we have the images here again that we saw in the start. These are just some examples. We have the video, extract them into images. We also labeled it with a couple of lines of code. And now we have these predictions. So we have our cap at the top here, which is the green marker here, or the green segmentation mask. We also have the pink one here, or the red one, which is the milk bottle. So all these annotations here are automatically labeled with these foundation models. We basically just threw in the prompts, milk bottle and blue cap, and now we have these labeled images in our data set. This is really cool. These are some really great annotations as well. Like these are just perfect annotations from the segment anything model. So again, all these foundation models are from Facebook or like Meta AI. So again, some really cool models. We're just going to scroll through them to see a couple of examples. So again, it just does a perfect detection. It does a perfect annotation on all of these examples that we see. So we should have some good annotations that we can just directly feed into our YOLOv8 model, which is what we're going to do now. So now we have our target model. We're going to set up like the YOLOv8 model as we've been doing in all the other videos. I also have videos here on the channel where we go over how we can train our own custom data set with manually labeled images. Now we can just use this script, go through it, auto label it with auto distill. So now we're going to see the entire home directory. We're going to import the YOLOv8 class. We set up our target model. We can also specify what model we want to use. So in this example, we're just going to choose the Nano model for YOLOv8, and then we can call the train method. We throw in our dataset, YAML path, and also the number of epochs that we want to train our model for. And then we should be able to see, first of all, we'll get a summary of our model. We see the number of parameters. We also see all the hyperparameters for our training, the CUDA device that we're using, NVIDIA 800. So these are just all the parameters, all the hyperparameters for a model, the number of layers, parameters, and so on. And then we're going to see the training results down here at the bottom for our epochs. So here I'm basically just going to go over to the right. We're going to take a look at the mean average position. We can also see the box loss, the class loss, but the main ones here is basically like the mean average position. So let's just let it run here, let it train for a couple of minutes, and then let's take a look at the results. So our model is now done training. Let's just take a look at the results here, like the training results for each of the epochs. I'm not sure why we get 0 here in the mean average position of 0.50 and also 0.50 to 95. We might get some results later on, but we can also still see like the class loss here and also the box loss, which is decreasing over the number of epochs, which is good. Let's just scroll a bit further down. And now we should also be able to see, okay, so now we get the mean average position of 0.50 and also 0.50 to 0.95. So again, we get some pretty nice mean average position here. We also have the loss, it is decreasing over time, like the class loss is decreasing. It actually like looks pretty good. We can see that our mean average position still increases. We're around like 0.81, 0.82, 0.84 here. So again, this is actually like pretty good mean average position just by training on 130 images. So just remember we have 130 images or like even only 100 images in our training set. And then we're basically training our own custom YOLOv8 model from our auto-labeled dataset. Here we end up with a mean average position of 0.86, mean average position 0.50 to 0.95 at almost 0.79. That is pretty good. And we also have a good box loss and class loss. We can go down and evaluate our target model here. So we can basically just go inside our runs detection. So if we go inside our directory, we have a runs detect train, and then we can see all like the outputs here. So we both have our confusion matrix, we have the results and so on, but we can also visualize it directly in a block of code. Let's just do that. And now we should be able to see our confusion matrix. So in the diagonal here, we should have the most values because then we have our true positives or like our true predictions. So here we have the prediction labels, and then over here on the x-axis, we have our ground truth labels. So we can actually see when we have the bottles, we do a pretty good prediction. We also do like the cap here, so the blue cap on top of the milk bottles. We actually have some pretty good detections for that. We can also see the results here for our basically like our training graph. So let's just take a look at those. We can see the box loss is decreasing over time, as we also saw when we went over the results in the epoch. The class loss decreases. We have our precision here, so it kind of just jumps from 0 to 0.80 here instantly. It kind of like converges here, is still increasing like slightly. We could probably increase the number of epochs and get slightly better results. We can also see that the mean average position down at the bottom here, it hasn't really like fully converged yet, but we have a pretty good model here, pretty accurate model that can actually go in and do object detection with our target model trained on our auto-labeled data set. We also basically just have a validation batch here, which is a prediction. So here we can see some of the results. This is the results from our YOLO model. We can see that it actually does miss some predictions here. It is pretty good at detecting like the caps. We can also see some nice detections of the bottles here, also here. Sometimes we get some false positives. We miss those detections here and also here. So we kind of like, we can't really like detect this scenario here. It seems like where we can see like the top part of the bottle, or the bottles are very close to the camera. We can also go down and just throw in a video. So we're going to just throw in the video that we trained our model on. So we're basically just going to take that video, throw it through the model, and then we can see the inference. So now we just call this predict method. We can just see that it just throws all the images from the video through the YOLOv8 model. We can also see the number of bottles that it detects, the number of caps, and also the inference time over here to the right. Then if we scroll down to the bottom, it is basically just throwing all the images through the model. The results are saved to runs, detect, predict, and then we can basically just create a video from that. So let's go here to the left and just take a look at it. So we have our detect, we have the predict, and now we have an MP4 file. Let's just go in and download that so we can then see the results on our actual video stream. So let's take a look at the video here and see the inference results on this video. So again, we get some really nice results. We detect the bottles here in the foreground. We lose tracks sometimes, but again, we're only doing update detection in this scenario. The cups, or like the caps up here at the top, we don't really detect those. We just detect them as a single one. Sometimes we detect them on top of the milk bottles, but sometimes we also miss them, as we can see over here. So right now we can see that we take the cap, but with a low confidence score. This was actually like a pretty good detection, and also again we can still detect the bottles with a high confidence score. Again, just remember we only trained this model on 100 images. So these are some really nice results. So thank you guys for watching this video here, and again remember the subscribe button and bell notification under the video. Also like this video here if you like the content and you want more in the future. We're definitely going to use this auto distill framework way more in the future. See you next video guys. Bye for now. So we have another member in the YOLO family, YOLO11. So this is released by Ultralytics. So we have the YOLOv8 model and also the new YOLO11. In this video here, we're going to see how we can take a custom dataset, train the new YOLO11 model, and also how we can run inference. We only need a few steps. First of all, let's just jump straight into it and take a look at the new model. Then we can label our dataset and then train our custom YOLO11 model. So first of all here, let's just start inside the GitHub repository where we can go in and see the benchmarks, so the comparisons with all the other versions in the YOLO model. I'm going to keep this video short so we can just jump in, take the dataset, train our model, run inference, and we should be good to go. You can do all of this within 5-10 minutes on your own site as well. So if you just take a look at the benchmark results, we can see this is a new state-of-the-art model. It runs faster compared to all the other YOLO models and also has better accuracy, at least on the CharuCo dataset. But again, just because we have a new YOLO11 model doesn't mean that the other models can't be better on your own dataset. So definitely test out all the different variations, or probably like YOLOv5, YOLOv8, and 11, because again, there might be some differences. Some of the models, they can run faster depending on the hardware, but also the accuracy on your own data set. So don't just blindly trust these benchmarks, because again, this is on a benchmark CharuCo data set. I feel after testing out this model, I feel it's a bit of a mix between YOLOv8 and also YOLOv10. So we get the speed from YOLOv10. We also get some false predictions here and there, which we're getting with YOLOv10, but not as many. It runs as fast as YOLOv10, but it doesn't have the exact same accuracy, at least on the custom dataset that I have tested out with the YOLOv8 model. So I feel it's a bit in between YOLOv8 and YOLOv10. So let's not just jump straight into our Google Colab notebook. Let's go ahead and take a look at it. We can just connect to the runtime. You can use this. It has free GPU resources available. You can just go up to the runtime, change the runtime type, and you can choose the specific GPU that you want to use. So I think it's the T4 on the free version of Colab. So I'm just going to connect here with my 800 on Google Colab. The only thing that we need to do is pip install Ultralytics. Make sure that you're updating it to the latest version. So if you have it on your local, you can just pip install upgrade and they will download the latest version. So if you're running into errors, make sure that it's just updated. That might be the reason. So now we're connected. Let's just go in and pip install it. Here we'll have our data set, and then after that we can just run a single command and we're going to train our own custom YOLOv8 model. So let's now go inside RoboFlow. I have a data set here where I'm basically just annotating these helmets. So if people are wearing helmets or not. So this is for protection equipment. So let's just go through a couple examples. I've already labeled out the data set, have tons of videos on the channel already, how we can label, set up the whole pipeline and so on, and go over this tool, but also some other annotation platforms. So we have all these images in our data set. I've generated a version, so we can just see we have this raw. Then we can go in, download our data set up here. We have 70 images in our training set, 20 images in our validation set, and 10 images in our test set. Then we can choose the export format. So let's go with YOLO11 for now, show downloadable code. Going to check that off, continue. It's going to zip the folder, and now we actually just get this code snippet. We can copy it and paste it directly into our Google Colab notebook. So this is everything that we need to be able to train our own custom models. So we have downloaded it. Now we can just run this pip install RoboFlow. We should be good to go. We're then downloading our data set, and we can just run this single train command. We can then export, take a look at the results from Ultralytics. We can see all the epoch per epoch, mean error position, precision recall, and all of that. So now we have our data set. Let's go over into our folders. We have our hot hat sample, we have our test, train, and validation, and then we also have our data YAML file. So inside the data YAML file is just going to specify the names that we have in the number of classes. So we have head, helmet, person, and we specify the directory for a train, validation, and test set. So that's pretty much it. We just have these folders. This is the structure that Ultralytics is using to train all their YOLO models. So this is just what format you need. Also, if you have your own local data set or using another annotation platform. So we have our images, we have our labels, train, test. So this is pretty much just folders with all the labels and also all the images. So inside our label file, we have our object class to start with, and then we have 4 values for a bounding box. So that's a bounding box point, but also the width and height of it. So that's pretty much everything that we need for the YOLO format. We can then just go down and call this command. I'm just going to close this. We have detect, train, and then we have data. We just specify the data YAML file path. We specify which of the models we want to use. So right now we want to go with 11. So this is how easy you can just swap out the models. If you want to test out other models, just YOLOv8. Now it's only called YOLO11. We have the small, medium, nano, large, extra large versions as well. Let's just go for 30 epochs, and we can specify the image size. They also have all the other high parameters that you can specify. Just check out the Ultralytics documentation. So YOLOv8, we're good to go. We can just hit go, and it will start training this custom model. So first of all, it's going to download the weights automatically, check your data set if it's in the correct format and so on, set up all the high parameters, go in and do some data augmentation and so on, set up the optimizer, and it will start the training. Again, if you want to dive more into details about any of these stuff, definitely go in and check out my other videos. I have like whole tutorials covering like the basics of deep learning, object detection, computer vision, and so on. So now we can see that this training has started. Epoch per epoch, it's going to go very fast because we only have 100 images, and I'm running this on an A100 GPU from NVIDIA. So we should be able to see our mean error positions go up here over time. The losses, they should decrease. Let's just go down and take a look at it. Now we have already completed 15 epochs. So if you just have a couple of 100 images, you can train your models within like 10-15 minutes. You can test out the different variations, model sizes, and so on, and basically just do some modifications. So this is how easy it is to use. If you're using Ultralytics, like you can just test out models like within an hour. You can probably figure out what is the best model for your specific data set. So we can see that the mean error positions, it's not really the perfect model. It could be because of the data set as well, or the number of epochs, but we can see we started around 0.3 here in the mean error position, and then once we go up, we end up here at around 0.63. So we could definitely train it for longer. We can also go in and see the precision. The precision is pretty good, but the recall is not that good, or pretty much bad. That basically just means that we're missing predictions. We get the predictions with our precision, but our recall, we miss a lot of predictions, which we should actually have predicted. After that, it's going to do the evaluation on our validation set, and then we can go in and see for each individual class, how many images, instances, what is the position and recall. So we can see that the helmet, it has problems with detecting helmet, or that is like the best one. Person, it has problems with that. Could be because of the annotations as well. But in general, this is an okay model. We could probably use it, but we definitely need to train it for longer. Now we can go over in our runs directory, detect, and then we should be able to see our train, and we have our train 2. We have our weights here. You can just go in and download that. If you want to run inference, I'm going to download the best weight so we can see how to run inference as well. You can just download it, use the exact same code as I have in the Google Colab notebook here, and basically just throw it into your own local machine. Here we get all the different graphs. So I normally take a look at the results.png, where we can see all these metrics, the curves, the training curves over time, and we can see that our model hasn't converged at all. So we definitely need to train it for longer. The losses, they're decreasing nicely, so it just needs more training. We also get labels, we get some validation badges. So let's go and take a look at validation. So this is basically just images that the model has never seen before. And again, these are some very hard use cases as well, because again, there's so many different variations in the data set. so many different examples, like different humans, different environments and so on, but it already does a pretty good job, at least with the helmets, as we also saw in here for validation. Then you can also go up and take a look at the precision recall curve. Ideally, we should have it up here at the top, so it should be 1, 1. So we basically just have 1 in precision and also 1 in recall. We get all predictions, we don't miss any predictions, so our model is pretty much perfect. So now that we have our model, let's jump inside the Ultralytics documentation, and we should be able to just pull the code for running inference. I'm just going to show you the documentation so you can see how to navigate it, but it's basically just calling the predict command. So you can both do it in Python, but also directly from the terminal. So if you just go inside our predict, we can then see we have tons of videos covering here. I'm doing the videos for Ultralytics, working closely together with them to create some cool content and also videos covering all the documentation. So in here you can see how to run predictions with all the different tasks. So if you're just running object detection, we can load in the model. So this is the best.pt model that we just downloaded. We throw our images through a model. You can take any, like could be a video stream, 0 index for a webcam, RGBS stream, list here of images as well. Everything you can just throw it into the model. You'll get the results out, and this is how you extract the bounding boxes, masks, key points, and so on, depending on what type of task you're doing. In this example, we're just doing object detection, so let's go ahead and take a look at that. If we want to run the detections, either we can use Python, so this is only a few lines of code, or we can use the command line. Right now, we just use the command line to train it, so let's now use the Python code, and you can do the exact same thing on your side. So right now, we can delete all of this, and we just need to take the path from our best.pt. I copy the path, throw it in here, and we don't want to run train, so I took the wrong example. So here we can run prediction, but it will basically be the exact same thing. It's just throwing the image through our model. Let's go back here again. We run predict, delete this part. And again, either you can just use the boss example here that they have, but let's go ahead and take a look at some of our test images. Grab that one, just take an arbitrary, we copy the path to that, and there we go. We should be able to see our results, and we can even go in here and just call save, set equal to true, and it will save the image. You can also specify show if you want to show it, but you can't do that in a Google Colab notebook. So we're running it in here now. We take our image, throw it through the model, and we will get the results out. So we can see here, pre-processing, 7 milliseconds pre-processing, 60 milliseconds inference, and also post-processing. And then we can see we detect one helmet in 61 milliseconds. All the results are saved within runs detect, and then we have our predict folder. So let's go inside that one, predict. And this is the results that we get out when we have our model. So we can see that we're detecting one helmet, which is correct. So this is a whole pipeline that you need to set up to train your own custom computer vision models with the new YOLO11 model. We took a look at the results, the benchmark. Make sure that you test out various models because it could be depending on your dataset, or it is. Then we took a dataset with RoboFlow. You can just go in and annotate it, export it into a Google Colab notebook, train it in a few minutes. We're good to go. We can now run inference with it, download the model, use it in our own applications and projects. So I hope you learned a ton this video here. If you want to learn more about computer vision, all my courses and so on, I even have my community, the AI career program. If you want to get into freelance work, level up your career, how to land AI machine learning jobs. I also have the AI career program. You can check it out on our website. Everything is down in the description and so on. And then I just hope to see you guys in one of the upcoming videos. Until then, happy training. So Apple just released a new depth estimation model for metric depth estimation. The model is called Depth Pro, and we're going to see how we can set it up, how we can use it, but also take a look at the crazy results. Then we can take an image, throw it through the model, and we will get our depth map out, and we will get metric depth values, which means that for every single pixel, we're going to get a value in meters. So then we can combine that with a YOLO11 model or any object detection model, or even segmentation model, and we can take the individual points, index that in our depth map, and then we will be able to say that this person here is 2.4, 2.5 meters away from our camera. So this unlocks a whole new bunch of opportunities in the computer vision space, tons of different projects, applications, and so on. So just jump straight into the GitHub repo. We have this ML-depth-pro. Let's go down and take a look at it. We can see some very awesome results here. Even just by looking at it, the results, they speak for themselves. We can see these bird cages. Even with the high details, we have really good metric depth. The closer it is to the camera, we have the red color, and then it will become lighter or like more blue, more cold once it gets further away from the camera. So these are some very good estimates. We can even just see the hair here on the cat and also on the left side. If you just take a look at it, it's going to produce a 2.25 megapixel depth map in around 0.3 seconds if you're just using a standard GPU. So it really depends on your hardware, but you're not going to run this in real time. There's also a ton of other new depth estimation models coming out. This model here only works on a single image. So some of the other new depth estimation models coming out, they're focusing on consistency across multiple frames. So that could be in a video. So this is a very nice model where we can use to get metric depth estimation. It's also going to estimate the camera's focal length because you need to do that to get metric depth. So all we have to do is basically just run these few commands. Clone the GitHub repo. I've already done that, but I'm just going to open up a new terminal so you guys can see how to do it. Just go up here, take the code, copy it, and we can just git clone like this. I've already done it, so let's just cd into it. ML Pro. There we go. And let's go down and take a look at it. Now we can just pip install it. And then after that, we can open up a Python script and just import that module. There we go. And we can also source the pre-trained model. So just call this command. It's going to source the pre-trained model, download them into the checkpoints directory. We're good to go. We have everything now. And now we have two options. Either just run it directly in the terminal or in the command line or in a Python script. So this is all we need. Just a few lines of code, we're good to go, and we can combine it with a YOLO11 model or whatever object detection, segmentation model, and so on that you might use. So let's just open up my code editor. I'm going to scroll up here to the top. So I've cloned the GitHub repo. Everything is over here to the left. I just have a couple of examples. They also have an example image if you don't have any on your own, but definitely try it out on your own images. It is very awesome. We also have the depth_pro PyTorch model. It's around 2 gigabytes, so it's a rather large model. These models, they're becoming better and better over time, so they're definitely going to be able to run way faster in the future, get better, get more efficient, and so on. So in the end, in 6-12 months, we might be able to run these models in real time. It just unlocks so many opportunities. No expensive depth cameras, stereo vision cameras, lidars, and so on. We get very good metric depth values, as we're going to see at the end. So this is everything that we need. We import the different dependencies that we need. So depth_pro, import that pro. This is just the one that we pip installed. PLL, CV2, NumPy, and Ultralytics for our YOLO models. Then we create an instance of our YOLO model, the new YOLO11 model, and we take the small version of it. That's pretty much it. Once we run it, it's going to download automatically. We're using a pre-trained model now, but we also have custom trained models. We have tons of videos covering that, even also courses covering that. How we can set up like full computer vision pipelines. If you're interested in getting into projects, freelance work, and so on, I also have the AI Career Program. Everything is available on my website, down in the description, and so on. It's basically just my whole system that I'm teaching, and we have all the weekly calls. We have the whole community, people helping each other out, and so on, doing freelance work. So it's just one big agency essentially. I'm going to build that over time. So we have the image path. Just have a bunch of images that we're going to run it through. We read in the image with OpenCV, throw it through our YOLO model. You're familiar with that. We have our results. This is how we can loop through the results that we get from our YOLO models. We can extract the bounding boxes and also the classes. So we're only interested in the person in this example, but we can just call results.boxes.xyxy. That will be the top left corner and the bottom right corner. Convert to CPU if you're using a GPU, and also to NumPy. Then we can just zip our boxes and classes so they will be together. And we're only interested in storing all the classes, all the predictions that contain the class person. So we're just going to find the distances to people walking around in the frame. And right now I'm just going to take the center of the bounding boxes, but you can also have a whole segmentation mask that you just index in the depth map. So this is pretty much it. We're just appending all the values to our person boxes. We draw it and we just visualize our results. So once we've done that, we just take the code snippet from the GitHub repo, depth_pro, create model, and transform. So this is how we can do both the transformation, so the image pre-processing, and also run the model. Run in evaluation mode, so we have less RAM, it will also run faster and so on. We can load in an RGB image from the image path, so depth_pro.load RGB, specify the image path, and we do the image pre-processing with our transform. That's pretty much everything that we need to do. Then we can run our inference on top of it. So depth_model.infer. We have our depth_input. So that will be our pre-processed image, but we also need to have this estimated focal length in pixels. We have tons of videos covering what that is. Everything in computer vision, all the camera parameters, intrinsic, extrinsic, camera calibration, all of that. So we cover all that in pretty much a ton of videos here on the channel. Then we get a prediction out, and we can just extract our depth map directly from our prediction, and that will be in meters. We squeeze it, so we just get rid of the batches, CPU, NumPy as well, as we did with our YOLO predictions. So now the idea is to take our Persian bounding boxes, calculate the center of it. We can take the center, so that's basically just one value in our image, so that will just be a coordinate system. We take that value, index it in our depth map, and we'll get one single value because our depth map is just a one channel image, and that will just contain one value, floating point value, that will correspond to our meters. So that's the metric depth value that we extract from our bounding boxes. Then we just do some setup here for visualization. So the depth with the depth value, we set up font, text sizes, and also just the position of our text and our bounding boxes. We use the rectangle, put text. That's pretty much everything that we need to do. We visualize the results. Every time we have done a step, we just visualize the results until we hit a key on our keyboard. We write out the results as well, and then we normalize our depth map so we can apply this color map on top of it, so we get the red and blue colors. Then we can also invert it here, so we basically just have the red colors in the foreground and also the blue colors or the colder colors in the background. That's pretty much it. We're good to go. We can open up a new terminal and just run the program. I'm going to activate my conda environment. There we go, and we can just run this Python script. Python depth_test.py. First of all, it's going to download the model the first time you run it. Then it's going to do the predictions and visualize the results. There we go. Now we have these persons detected in our frame. They're just walking around. Now we can take the image, throw it through the Depth Pro model. We'll get the depth map out, and then we can do these extractions and indexes directly into it and take a look at the results. So this is the output that we're going to get from this Depth Pro model. We can just take a look at the results on the left side. They are very, very crazy. This can be used in a ton of different applications and projects like drones, robotics, like navigation systems, obstacle avoidance, and so on. We can just run an object detection model, get the depth to it, and we can navigate based around that. But we can also take individual objects and calculate the distance in between, which is really hard to do or pretty much impossible if we don't have any depth information and only have the predictions in 2D space. Of course, we can base it depending on the size of the bounding box and so on, but that's not really accurate. Take a look at the results. So right now we have the closest person to the image, which is the lady here on the right. So 2.48 meters, 248 centimeters away from the camera. Looks pretty accurate in my opinion here, and this model here is also very accurate if you read through the paper and so on, and also test out a bunch of different use cases. But even just the depth map here on the left side, it looks very accurate. And we can just see the level of details and also the gradient once we go from the front to the back of the image. But even though we have a person here walking in the middle, pretty much like the whole body is at the exact same depth values, and it's only in between. We can even see the fingers in the hand here if I just zoom in a bit. So we can see around here, we can just see the fingers, and the details of this depth map is just very crazy. So let's take a look at some of the other ones. We have a guy here walking in the middle, so he is the third guy, and we have the kid here on the left side. So it looks very accurate, like he's probably like 30 centimeters in front of the woman, which is also very accurate. They walk just right beside each other, but again, the child here is probably walking in between the woman and the male here, so that's also pretty much in line. This is just crazy. Like, I couldn't imagine we'll be able to do this with just a single camera if you're just talking about like a couple of months or like a couple of years ago. And this just unlocks a whole bunch of opportunities in the computer vision world. So definitely going to test this model here out. You saw how easy it is to run. Everything will be on my GitHub. Down in the description, you can find the courses, AI career program if you want to get into freelance work or learn how to land AI machine learning jobs and so on, and help with all of that. Test out the model here. I'm going to do a bunch of videos in the future, try to run it on my NVIDIA GPU as well to see how fast can we get this model up and running, maybe do some optimizations, create some projects around it. We have the other models like Midas and so on. Like, these new models here are just crashing down. But we also have some other models which is pretty good for having consistency across frames. So if we are working with videos and so on, this model here might not be the best one yet, but of course they're going to do updates, optimizations and so on. So at the end of the day, we will have real-time single camera metric depth estimation that we can use for all our computer vision projects and applications. So really looking forward to that. Hope to see you guys in one of the upcoming videos. Until then, happy predicting. Let's set up a whole computer vision system in just a few minutes. We can use RoboFlow to set up the whole pipeline. If you have a custom data set, you can just go in directly, upload it in there, do the data annotation. They have also labeling tools with AI models, so you can just prompt whatever you want to label your data set as, train the models in there, set up different custom workflows. You can then deploy it directly, get the code snippet, run it, and we have a whole computer vision system up and running. If you don't have your own custom data set, go in and check out RoboFlow Universe. You can find all these different public data sets. They're all available. If you want to do updatation, classification, instant segmentation, key point taking, and so on, just press it here, and you can see all these different data sets. You can forward them, you can use them. If they have models available, you can run them directly. So right now, let's just go in and create a custom workflow. We have input here, could be an image. It is an image from either a video stream, single image, or from a video file. So we have our input, we add a block, we have all these different blocks available, model, visualization, logic, branching, and so on. Go ahead and check it out. Let's now just take a model. Let's just take an instant segmentation model. We can use public models, or you can find your own. You can specify a workspace model, train a custom model directly if you want to do that, and you have your own custom data set. Just upload it in here, and it's just a few clicks. So let's now jump back into our workflow, our custom workflow. We add a block, have our instant segmentation model. Let's now just take a public model, grab a YOLO11 model. We can hit save. That's pretty much it. Specify all these other different parameters, but right now we have the outputs. This is how our JSON format is going to be. We have our model predictions. We can add any outputs, and we just output our predictions. If you want to do any visualizations, let's say that we want to do that. We have bounding box visualization. We can also go in and add label visualization. So we pretty much just display all our predictions that we get out from our instant segmentation model. So instead of bounding box visualization, we should probably just delete this part. There we go, because we can actually do our polygon visualization. There we go. We have our outputs, which is going to be both now. So we have model predictions, and we also have our label visualization image. So this is pretty much everything. Could also go in and do a filter. So we can go in and create webhooks directly, like triggers, Slack, something. If you want to create an alert, email alerts here, email notification, if we have a specific threshold condition met. Once we have created a whole workflow here, we can just save it. We can test it directly in here. So say that we have an image, I'm just going to drag in one of my thumbnails. I'm going to run it. You will see the output response over here to the right, where you can see all the keys in the JSON format. So you're just going to load the preview here. You can host it directly in here on the hosted API, dedicated deployment, local host. If you have your own server or just want to deploy it on your local hardware and run the inference, it's just going to automatically update all of it. So now we get the preview here of the output. We have our model predictions with our bounding boxes, confidence, class ID, and so on. If we scroll down all the way to the bottom, we will also have our visualized frame. There we go. Now we have our instant segmentation or our polygon zone, our mask around our detections as well. Now we have tested the workflow. We can then go and deploy it. RoboFlow hosted API, run on a local image or on a local video, pip install inference, and we'll just grab this code. Now we go into our code editor. We're just going to copy paste it in. If we do any changes inside the workflow, it's automatically going to change it in here. So no code changes are necessary. Instead of output image, we're going to call it visualization image. If you go inside our here again, we have our label visualization. There we go. There we go. And it's going to run inference. It's basically just going to take our API key, workspace name, workflow ID, video reference, either a video path, device ID, or an RTSP stream directly. Let's now just run it on our webcam. So I'm going to run Python test underscore RoboFlow. We have this callback function that's just going to take all the results, going to create future videos on how you can extract all the results to use in your custom applications or projects, or you can use the workflows to just connect all of it in the pipeline. So now I'm running it here. We have the whole pipeline. We took a data set. We have our model. We can train it inside RoboFlow as well. We set up a whole workflow. We can do update counting in a region. We can do tracking, triggering like different alerts and so on. We can host it on their server, our own server, local environment. We can deploy it directly. If I make any changes inside the UI, it's actually going to automatically update it in here as well. We just need to rerun our application. So now we have a scissor, not really a scissor, we have a person, and we also have a potted plant here. We're not visualizing our bounding boxes. For the polygon visualization, we can go in and specify the thickness, palette size, if you want to use different custom ones, RoboFlow ones. So let's just try this one out. So it's now going to add another step here just for visualizing our bounding box as well. So here we go. Let's just visualize the bounding box. We'll grab our polygon visualization, or we can just directly do it on our label visualization. Polygon visualization here. We can specify that we don't want to show anything, or our index or track. So now we're both going to do a polygon visualization, bounding box visualization, and label visualization. We save it. I go inside my program again, rerun it, and it's automatically just going to update it in no time. No code changes, do it inside the UI, and you have your whole workflow up and running. It's now going to connect to my webcam, and it will run the program again. There we go. Now we can see we both have our bounding box visualization. We have our instant segmentation mask, both for the potted plant in the background, both of them. We have our person. So this is how fast it is to make updates to the workflow. No changes at all. We just need to rerun it. This is how easy it is to use the RoboFlow whole ecosystem, going from a dataset, model, inference, visualization, set up the whole workflow, and create a full computer vision project in just a few minutes. Definitely go and check it out. It's very valuable if you're a computer vision engineer. You don't need to know any code, how to use it. You can just use it, build software systems around it, and provide business value. Definitely go and check it out. Hope to see you guys in one of the upcoming videos. Until then, happy learning. So in this video here, we're going to see how we can run the Ultralytics YOLO models on a Jetson Nano using DeepStream. So this is an optimized framework from NVIDIA that can run specifically on NVIDIA hardware. So I have a Jetson Nano over here in the back. I've just connected to it, and then I'll have a TeamViewer connection running here on my MacBook. We'll just go over the step by step. So just have it set up over here, nothing installed yet. So we're going to go through all the installation steps. If we run into any errors, we will resolve that, and then also take a look at the results after. But it can run crazy fast compared to if you're just using the standard models, if you run it on the CUDA GPU without the TensorRT optimizations. So it's basically just a framework that can go in and do parallelization, it can do batch processing and so on. You can also connect multiple sources, and it's going to do all the synchronization, the parallelization and so on if you have multiple cameras, videos and so on. So this is pretty awesome, but it uses TensorRT optimization to run faster. So just by using TensorRT, we probably get like 2, 3, 4x speed up compared to using the GPU. So we can actually run just on a small Jetson Nano board, like 5 millisecond inference with the new YOLO11 model. I've just jumped straight into the TeamViewer here. I'm connected through it to my Jetson Nano. We can see we have the Linux over here to the left. I went into the Ultralytics website. First of all, I also have a terminal up and running here. So let's just clear. There we go. And first of all, I'll just show you the JTOP. So we're going to install JTOP if you want to see all the different specs, the resources it's running, all the versions, dependencies that you have pre-installed as well, depending on your Jetpack version. So right now we can see all the stats here. We can see the GPU resources, how much GPU it's using and so on. So that's also pretty awesome. The gigahertz for the different cores. So here we can see we have 8 cores. Jetpack 6.0. So we need to use this information when we set up DeepStream. I can also press 7 here to get the information. We can see the architecture that is running on Linux, Ubuntu 22.04. We have Python 3.10 at default. We have CUDA version 12.2, cuDNN, TensorRT, VPI, Vulkan, and also OpenCV. So all these things are pre-installed with the different Jetpacks. So you basically just get a Jetson board. You install the Jetpack version, you basically just need to flash that. That's different ways to do that. You can look that up on YouTube. Sometimes you run into some problems and so on, but when you have the Jetpack version installed, just have the raw NVIDIA board. You just bought it from somewhere. Some you can even just buy pre-installed with DeepStream or with these Jetpack versions as well. But then you buy it, we just flash it with the Jetpack version, and we have everything needed for CUDA, computer vision, deep learning, and so on that we use it for. This is very easy to work with. Here we can see the different versions which we will need. Remember, Jetpack 6.0 here. We also have the CUDA ArcBin. Could be that you want to build OpenCV with CUDA support as well. We have videos about that here on the channel. So right now, let's go inside our documentation on Ultralytics. let's go inside our guides tab. We can read about like NVIDIA Jetson, deep stream, and so on. We have some pretty cool videos in here, like very good videos. It's a nice guy creating these videos on their channel as well. Very detailed, so definitely go in and check them out if you want to see some other cool videos. So let's go inside. We have NVIDIA Jetson, you can read about that. We have deep stream on NVIDIA Jetson. If you just want to run like a single stream, just get it up and running, you can just use TensorRT with NVIDIA Jetson. You can also grab that in from the integrations tab. So this is all the export formats that you can use. So we have TensorRT here, for example. You can see some different graphs, key elements, what is actually going on under the hood and so on, converted to an ONNX and then an engine file. And this is just all for getting these models to run as fast as possible, and it's crazy fast. It's gonna run crazy fast on NVIDIA GPUs compared to other hardware. All the arguments, I think you can even see some graph if you scroll a bit further down. Here we can see some inference time, NVIDIA 800, consumer GPU 3080, so like 1 milliseconds, 0.6 milliseconds inference per image. So just 1 millisecond per image, that's like 1000 frames per second on a consumer grade GPU. Here 0.5, 2000 frames per second. Let's go back here again to the deep stream and let's just jump straight into it. Again, all I'm doing here is basically like on my TeamViewer connection to my Jetson board. So it's pretty nice if you're working with MacBooks and so on. Just have an NVIDIA Jetson board laying around. You can even buy the new one, which is like pretty low end, and you still get very good GPU resources. You can just spin it up. You can see it's set up a local server and so on. Right now it's just on my own network, but it's pretty responsive. So that's awesome. Then I don't need to connect like a monitor, keyboard, like mouse and all that to my Jetson over there. I can just hook it up. So yeah, let's try to find it again. Now I kind of like got lost here. Let's go inside our guides. We have deep stream on NVIDIA Jetson. Let's go down and see why NVIDIA Jetson. We can read about that. We have the Jetpack versions and so on, how you can install them. And now let's go in and take a look at this one. So let's just go in and pip install. Just grab these commands. Let's see if what commands it's using. So I need to copy paste it with control. There we go. So when you just open up a default terminal in Linux or Ubuntu, you have to press Shift Control and then CMV for copy paste. And right now I'm on my Linux machine. So outside the terminal, I have to press Control C, and then I go inside the terminal and Shift Control V. So now we're cloning Ultralytics, then we will CD into Ultralytics and do all the pip installations and ONNX Slim. Let's go back, let's CD into Ultralytics. There we go, and we can run this pip install command. Now we need to go in and use this DeepStream YOLO repository. So this is a separate repository, basically just for optimizing the YOLO models for DeepStream. So let me grab this link and just going to take a look at the GitHub repository, but it's basically just a way how we can set up all the configurations. We need to specify batch size, the confidence score, a lot of different stuff we need to specify when we create our engine file, but also just the DeepStream configuration. So you can read all about it here, YOLO pose, segmentation, phased model, and all that. And this is pretty much just the exact same for all the YOLO models. So just going to take a look at YOLOv8, for example. This is the configuration for a YOLOv8 model. So we have GPU ID, we have the ONNX file. So first of all, it's going to convert it to an ONNX file and then into an engine file. Let's see if I can zoom in here a bit. There we go. We have a batch size. If you just want to run inference on a single image, you can just use a batch size of 1 or set it to 4, 8, and so on. If you're using DeepStream, we can just specify all different RGBS streams, video files, and so on, basically just line by line in another configuration file. And then we can just have a batch size of 4, and it's going to speed it up significantly. If you go a bit further down, we can see the pre-cluster threshold, so the confidence score, the intersection over the union threshold, and also the top K values or predictions that we want to take into account. So yeah, we have the DeepStream app configuration and we have the configuration for our model. So this is the DeepStream configuration we need to set up. This is the only thing that we need to do. When we have our DeepStream configuration, we have our model exported into the correct format. We can use DeepStream on our Jetson or any other NVIDIA hardware and Linux operating system. So we can see we have a tile display. We just have one row and one column. We can specify multiple if we have more video streams. We have source 0, so this is just going to be an example video that we have directly from DeepStream, but here you can specify whatever video file that you have, and you can also go in and change this to RTPS, and then you can specify the RTPS stream URL, log in and all that, and it's going to automatically connect to that if it's connected to your network. Number of sources 1, we can make duplicates as well. So we just need to understand how this configuration file actually works, and then we're able to play around with the DeepStream framework. Here we just have some text, color, some visualization stuff. We also have our stream mixer down at the bottom. If we have a live source, the batch size that we want to run and so on, because it's going to use a mux. If we have multiple streams, it's basically just going to take like one frame for each. It's going to do all the synchronization. It's going to do all the muxing and also demuxing later on, just to make sure that we're processing all the streams in basically like a series. We don't want our frames to just jump around. Okay, then we take one frame from this camera here, another frame from another camera, and we don't really have any order or structure. So they're also taking care of that directly. So this is pretty much everything that we need. We also have a labels.txt file that we need. So this is just the CharuCo dataset, but if you have your own custom dataset, you can go in and use or just change the different labels here. So I've also created a video, definitely stay tuned for that, where we're actually going to see how we can use the custom models, but also extract the results to use it in our own applications and projects. So yeah, this is pretty much the DeepStream that we're going to use. So let's just make sure that we have that too. I'm just covering everything here in detail so you guys can like do it on your own. You don't run into any problems or anything. You can just follow it line by line here. If you run into any errors, it's most likely because you have like versions not matching up. Make sure that you have the correct Jetpack versions and also look into that. So you can see I already have this in my computer. Let's go in and copy it. Just copy it into the Ultralytics repo that we have cloned as well. And now we can CD back into it. There we go. And let's see here. So export YOLOv8 works for both Ultralytics V8 and also the 11 model, because it's just basically the whole same here, like the same structure and architecture. So it's going to grab the weights. And you can specify whatever model. Right now we are using this model. It's just going to download the Nano model. And then we will convert it to ONNX. So they have a script export YOLOv8. You can also use a custom trained YOLOv11 model. We have videos covering all that on the channel and so on, even the new YOLOv8 But instead of having the pre-trained weights here, you just specify the path to your own weight file or trained model. It's downloaded. We can go in and export it. So let's make sure that we have the Nano version instead. There we go. Now we can see that we run into some errors. So libqdnn cannot open share file, no such directory. So something is wrong with our PyTorch version. Let's try to pip uninstall that. And we'll also uninstall Torch Vision. So most likely, if you run into any error and so on, you have all the versions, all the CUDA versions and so on installed in the correct way. I think I've done some modifications, so this is not like a system directly out of the box. So you might be able to, or you might be able to run it like pretty much just out of the box if you do it from a fresh install. I've probably done like a ton of different changes to the versions and all that. You can even also, like Ultralytics, they also go in and take and check and do checks for the versions that you have. So let's go in and pip install Ultralytics as well, just to make sure that it is installing the correct PyTorch version. If it can't detect PyTorch while it's installing Ultralytics, it's going to automatically go in and pull that. Could also be because we have an older version of Ultralytics installed. So now we can see that it's going to download Torch and also Torch Vision, and it will run some checks and pretty much just set everything up automatically. So you just need to run this export YOLOv8, and we specify the weights. You just need to make sure that we're not running into any torch issues. This is a torch issue, so dependencies version, and not really any code issues. See, we rerun the command, and now we can see we're generating the ONNX file. So this was just because I had the wrong torch. So now we can see that it has exported YOLO11n.ONNX. I want to create way more of these videos where it's just like raw videos showing all the steps and so on, where I explain, okay, we ran into this error here, how can you resolve it? It's way better than just like clipping it out, figuring out and saying, okay, now it works. No one is going to learn from that. I'm gonna sit here anyway and figure out the error, but I pretty much know all the errors with working with it for so long. So it's either PyTorch, I can just directly see, okay, this is PyTorch, we need to figure it out. Okay, I know somehow we can fix it if we pip install it, pip uninstall it. I know that AutoLeaks does some checks and so on when we install it again. So it's basically just experience, but it's really good to show you guys that if you run into errors, it's most likely some dependencies which are off. So now we have the YOLO11 Nano model. Let's go down and see the next steps. We have converted it. We can also specify all the other different kind of like arguments here if we want to use a specific offset. This is also very important for ONNX, but again, just use the default if you're not familiar with it or know exactly what you're using it for. We can also simplify the ONNX model, and we can also use it do it dynamic, which means that we can have a dynamic batch size. So then you can actually like to go in and throw 1, 2, 4 images into the model at the same time, which is really helpful. So you should definitely probably just specify that argument. Most likely if you just have a single stream, you just want to process like a live stream, just use a batch size of 1. But if you have video file, for example, you could actually like go in and batch those, because we still have all the frames. It's just how fast can we process that whole video file. Copy the generated ONNX model file and text file to the deep stream folder. It's gonna do that. Let's see if we should already. Okay, so something's off here. We don't need the .pt, we just need the ONNX. So there's an error here in the documentation. So, and we also have the Nano, and it should just be .ONNX. There we go. Set the CUDA version according to the Jetpack version installed. So right now I have Jetpack version 6.0. So just Jetpack version 6. Let's go in and export this one. It should already be this as default, so you might not need this step, but let's just do it out of good practice to make sure. And I think it was version 12.2. Oops, 12.2, there we go. Now we can compile the library. So this is basically just going to do the inference from the library that I showed you in here in the GitHub repo. So it's gonna make the model ready for deep stream and this whole inference with CUDA hardware. Let's go in here again, paste it. So we're going to make NVIDIA Infer custom implementation YOLO clean, and then we're going to basically build it or compile it. So no such file or directory. Let's make sure that we're inside the correct one. Let's see if it's inside here. So yeah, we can see we have it here. So we were inside the wrong directory. Should definitely have that in. Oh, we forgot to run this command here. So let me see. We ran the copy, but we forgot to cd into the deep stream YOLO directory here. The export CUDA is not going to have any effect here. And now we can just rerun this command. Let's see, there we go. Now we shouldn't run into any problems. We're using CUDA 12.2 as we just specified. We might get some warnings and so on. It doesn't really matter. This will just run for some time, depending on like how much CPU power and so on you have. It might take a few minutes for doing this step, and then we can go in and edit this file. So the one that I showed you with the primary config, number of classes, the model file that we're going to use. So again, we have a small error here. Now let's go in and find that file. So inside the root home directory. Stream YOLO, we find the config infer YOLOv8. There we go. Make sure that we're using the correct model. So let's use the Nano YOLOv8 nano.ONNX. it's going to generate this engine file here, so floating point 32. This is also a very important file, so I'll probably just go through this as well, but we can have a batch size of 1, network mode. So if you set a network mode to 1 or 2, you can, or the type here, you can go in and check that in the NVIDIA documentation, but then we can actually use floating point 16 or int8 calibration. So need a calibration file. If you have that, I think we should specify that somewhere. Let me see if they have an engine file. int8 calibration file, so we need to have a calibration table if you want to do int8 calibration and quantization. So, but yeah, if you use floating point 32 or floating point 16, you don't really lose any accuracy and you get a crazy fast model. So let's just go with this one here. I think it's the network type or the network mode. Probably just make it fully raw here. So let's check this one here. They might have some documentation with it, or they have, just need to find it. I think it's the network mode, to be honest. Or might even be inside this GitHub repo as well. Oh yeah, so inside the custom models.markdown, they have a lot of different different resources that you can read about as well. Network mode. So network mode, if we have 0, it's going to be floating point 32. If we have 1, int8, and 2 for floating point 16. So this is very good. Definitely make sure that you go through the documentation. It's the exact same GitHub repo as I showed you before. So they both have like a int8 calibration markdown file for different YOLO models and all that, if you want to use some of those things. So let's see, it's done in here now. Let's go back into Ultralytics documentation. We changed our file. Let's make sure that it's saved. So we changed this YOLOv8 Nano model. So we should use 11 instead. I think we used 11, right? Yeah, and we used the Nano model. So this is none of the default stuff. This is a custom one. And if you have your own custom train model, you just need to specify it here. So this should be good. Just make sure that it's saved. We can go back into documentation. We need to edit this file here. So this is the deepstream app config. Deepstream app config. Deepstream. There we go. And now let's make sure we use the YOLOv8 config infer. So that should also be good. And we can change the video source if you want to use another video, RTVS stream, your own video file and so on. Right now, let's just use the example video from NVIDIA. It's just a file path that you can swap out. So now let's grab it and see if we can do inference. First time you run inference, it's actually going to set everything up, generate the engine file. So it will take longer the first time you run it. Sometimes it can take 30, 40 minutes to generate the engine file. It's going to do all the optimizations, everything, and then it will just run with inference. If you rerun again, it has already generated engine file with the floating point 32.engine, and it will just reuse that. Let's see if we can run the inference deepstream app. Something is happening. Let's see if we get an error or if it's just gonna start the run. So now we can actually see it's running here, 4 streams here. So this is pretty cool. We can see the number of frames per second. So this is 10 frames per second, but we're running this on 4 streams, so it's around 40 frames per second that we're getting, and we can see we get it for each of these individual ones. I even had a custom path here, so I had been playing around with this before, so I'm not even using the default one. I'm using this cars.mp4 and I'm specifying number of sources equal to 4. That's also why it had the model. There we go, let's save it. Let's go in and quit it. And this is running with the YOLO11 model. Should be, let's just make sure that we're using that model. App config, we're running YOLOv8. And in here, we're specifying our YOLO11 Nano model. And if we go inside our directory, we have the Nano ONX model here, and we have generated the engine file. So we actually need to change the name of the engine file because I can see this has been changed in 2014. It's because I'm just using the exact same naming. That's why it's just pretty much just opened up instantly. So make sure that you change the name, or it's just going to reuse that file. So instead of calling it model, let's just call it new v11. There we go, let's save it. And now we should be able to rerun it. And now it will take some time to generate the engine file and spin up the inference. We're only going to use one source now, but we're still using my own custom video. Generating engine file, trying to generate engine file from files, building the TensorRT engine. This will take 30-45 minutes. It will probably throw some warning and so on. Doesn't really matter. You'll be able to run the inference after, and this is everything that we need to do. I covered everything in detail. You can probably set it up in 5 minutes if you know what you're doing, if you're not running into any errors and so on. Ideally, you should just take your Jetson board or any NVIDIA hardware, set up all the dependencies with the Jetpack versions. You can get them out of the box, run a few commands here, get the GitHub repo. The most important is the GitHub repo from the other here, and then run it, set up the configurations, get familiar with what are all these configurations. I pretty much explained all of them step by step, so make sure you understand it, make sure you go through the video and understand each of these steps, because it's basically just the 2 configuration files that we need, but you still need to know what is GPU ID, what is the type here, how do we specify a custom file, how do we specify an RTBS stream, what is this rows and columns. So this is 2 by 2. We should probably change this to 1. When we only have 1 display right now, shouldn't really cause any problems. It's just going to duplicate it. So this is very important to know. Also the batch size, even the network mode, because you can just switch it here and then you're running floating point 16 and your model will probably be like 30-40% faster just by running that without really losing accuracy. It's still generating here. Will probably take 30 minutes or so. We'll get back. We'll take a look at the inference results, but this is pretty much it. So it's now done generating the engine file here. I had a quick nap while I was doing it, probably around 45 minutes until it has generated. But right now we can just go in and rerun again, and it's automatically going to use that model. And now we're only going to run it on a single stream. So it should just open it up in a second here. We will get the number of frames per second and everything. But yeah, here we can see it's running around 60 frames per second on a Jetson Nano board here. So right now you can see that it's basically just running this video, running it all the way through, quitting app run successfully, around 60 frames per second. But this is pretty cool. This is very fast as well and so on. We can also have it loop, so it's basically just running the same video through all the time, but we get some very good predictions. This is pretty much the exact same predictions we get as if we're just running the model out of the box. We're not losing any accuracy or anything, but we get a significantly faster model running it here with DeepStream and TensorRT. So in this video, I basically just went over the whole pipeline, how we can set it up, do the installation step by step, even if you run into problems and so on. It's very important to know how to tackle problems, especially when you work with DeepStream, CUDA, NVIDIA, Jetson, and so on. You will run into a ton of problems, so it's very important to know. Definitely go and check it out if you have an NVIDIA Jetson board. It's a very good way to get started with CUDA, NVIDIA, and the whole NVIDIA suite with all the frameworks they have, and you get crazy fast models. Hope you learned a ton this video here. It's definitely a lot to digest. You need experience playing around with it and so on, but get familiar with it. This is how we can run both models in production, but also crazy fast compared to just using them directly out of the box with Autolytics or some other inference framework. Hope you learned a ton. Hope to see you guys in one of the upcoming videos. Until then, happy learning. We have a new member in the YOLO family. We have YOLOv8. So in this video here, we're going to see how we can train it on a custom dataset, run inference and so on. We're basically just going to go through a guide, a Google Colab notebook. We're going to talk about some of the new things with YOLOv8 and also compare it to the previous models. So just jump straight into it. I've jumped into the GitHub repo here for YOLOv8. This is not from Autolytics, but it is based on Ultralytics. So still the same license, everything. You still can use it from the Ultralytics package and all that. If we scroll a bit further down, we can see we have these comparisons where we have the benchmark results on the CharuCo dataset. So if we're taking a look at it, we can see that this is actually like a new state-of-the-art model. And just from the benchmark results here, it actually like looks significantly better compared to the other YOLO models. Let's compare to V11 and V8, which is the one that I have the best performance on. So we can see just compared with YOLOv8, both 11 and also 12 is significantly faster. Like significantly faster, almost like 2 times faster running inference. We get comparable results and so on, but again, We get a bit faster inference speed with the new YOLOv8 model, but again, we also get a bit better accuracy. There's one downside with the new model, and for right now, it actually requires GPU because it has this attention-centric real-time object detector. So it's using something called flash attention, which is actually just a technique from the large language model and so on, the attention mechanism, where it basically just learns what to pay attention to in the image. So right now it's only supported on GPU. I'm not sure when it will be available on CPU. But yeah, again, right now you can use it on GPU, Google Colab and so on, as we're going to run it through. You can see the paper. You can see they also have a Hugging Face space. Here it has some different updates. We're going to run through and use the RoboFlow tutorial that we have right now. We're going to use a custom dataset and set up a whole pipeline. It will also be supported with Autolytics fairly soon, and then we can just use that directly out of the box from their framework. It's still based on the framework now, so it will still be the exact same thing. But if you just update it from Autolytics' own repository, then it's not supported as we speak right now, but will be in the next few days. We have the Nano, small, medium, large, and extra large model, the exact same one as all the other YOLO models that we have. Here you can see the installation steps. You can also basically just go in and do the installation steps that I'm going to show you in a second. We can run validation, training, prediction, exported, and we also have a demo with an app from Gradio. So this is pretty much everything that I want to show you guys. Let's now jump inside a Google Colab notebook and get to do some real work. First of all, here you can use the free GPU resources on Google Colab. Right now I'm using the guide from RoboFlow. Definitely check them out as well. They have the RoboFlow blog, GitHub repo, and then we also have the Google Colab notebook here. They basically just write about a lot of different stuff here with the description, what it is, what are the different comparisons and so on. They also compare it to other iterations where we have this window attention, crisscross attention, actual attention. So this is some new stuff coming into the YOLOv8 model that uses the attention mechanism. So it basically just has some mechanisms, some features that go in and learns basically just as the human. So we pay attention to something, like we're not looking at every single thing when we look with our eyes. We pay specific attention to specific things. So right now I'm looking into the camera, so my eyes are more focused, or I pay more attention to the camera compared to all the other things in my surroundings. So this is what you can go and read about. You can also read about the paper and so on. And we can see the graphs here as well. First of all, you can set up your RoboFlow API key. It's going to be very easy once it's integrated into Autolytics and so on as well, but we need a GPU. If you go inside the runtime, you can change the runtime type and just use one of the free GPU resources from Google Colab. I've already put my API key in. If you go inside the API key tab here to the left, you can just put it in there and you can extract it in Google Colab in this way. I already ran a command here because I'm been running some tests and so on. You can just rerun here. We can run NVIDIA SMI. I'm also going to do a comparison where we're going to compare all the different versions. So V11, V12, V8, and so on, where we have them side by side to see if it actually achieves better performance. Because one thing is the benchmark result. We need to test out our models in real world situations, different types of data sets and so on, but RoboFlow is also very good for that. Right now, we can then just import our home directory. Then we set up our dependencies. So from the YOLO12 GitHub repo that we was just in, we're going to just pip install that. Going to use RoboFlow and also supervision for our annotations. The other thing here is flash attention. So we need this flash attention here, and this is why it's only working on GPU for now, and it's used for accelerating attention-based computation via optimized CUDA kernel. So this is why it's running faster compared to the YOLO11 model and the other ones as well. We pip install it. You just have to run this one here. We go in, get an example from RoboFlow with the dog example. You guys have probably seen that before somewhere. So this is how we can run inference. So import CV2 from Autolytics, we import YOLO. So everything is based on the Autolytics framework. So you can run the exact same commands, exact same arguments and so on. It's just a model that is swapped out. So it will also be available in Autolytics in no time. Right now, let's just run it. Let's see the results. So we get our results from our model. We do our inference. We take our predictions, convert them into supervision class. We have our box annotator, label annotator. We can copy our image, just the original image, and we annotate our bounding boxes and also our labels. Then we plot our image and we get our predictions here. So we have the person here, Peter from RoboFlow, his popular dog here, handbag, backpack, and also a car here in the background. So it's really nice that it's picking up the car in the background as well. We get a handbag here, probably because of like this one here. Wouldn't really say that that's a handbag, but again, we can also go in and use a confidence score threshold. Now we can go in and take a data set from the RoboFlow universe. I'm just going to open this one here. This is the example that they're using in the notebook. You can go in and use whatever. You can have your own projects as well. If you go inside your projects tab, label your custom data sets. I have whole pipelines, whole tutorials and so on covering how we can generate our own data set, how can we connect to a camera, how can we connect to a video, and then just extract frames from that. Then take those images, upload it into RoboFlow platform, do the annotations. They have a lot of different cool also annotation tools as well. I have a very popular video on that topic, so definitely check that out. If you don't want to do like manual labeling, we just throw in our data set, prompt what we want to detect in our image, and it's going to come up with the bounding boxes. So RoboFlow, very cool platform, setting up the whole computer vision pipeline. We can train our models in here, we can export, then we can do whatever, and then we can also use the Inference SDK. So we have the whole computer vision pipeline. So we have a data set here. We can basically just go up and grab the URL, and then download that model automatically. But it's now going inside the universe here. So I'll just gonna search for any project. We can also just go back here. So we go inside the RoboFlow app, and we can go back into the universe. So universe is down here at the bottom once you are at your main page. This is all the different projects that we have. If you want to do self-driving, gaming, manufacturing, agriculture, and also sports, you can search for specific projects up here. They have tons of public available data sets that you can grab out of the box. Let's scroll down a bit here. I think this PCB holes is a pretty nice one. It has around like 100 images. We can go inside our data sets. We have already trained models, which is doing very good at solving this specific problem. If we go inside our data set, we just grab the URL. There we go. We go back into here. Need to export it into YOLOv8 format. Again, this is just Ultralytics format. And then we're just gonna download the dataset. This is how easy it is to pull any dataset from the RoboFlow platform, from the universe. You can also grab your own dataset in the exact same way. So if you go over here to the left, we have our PCB holes 4, test, train, and validation split. And we also have our data YAML file. So let's see what classes we have. We basically just have one class, which is going to detect missing holes. Now we should have everything. We can just set our different path to our data YAML file, our test, train, and validation split. This is pretty much just everything that we have to do. Missing holes, so this is our data YAML file. Now we have everything. We can go in and train our models in the exact same way as any of the other YOLO versions. There we go. We have a model, we create an instance, YOLOv12 small. You can also just specify N, medium, large, and so on for pulling the different models. Let's just go in and use a small model. This is actually like going to train them from scratch, but you can replace them by any model here. So this is if you want to just, if you have a very large data set and you want to train your own custom models with random initialized weights, we can do it this way here, but we just want to fine tune an already pre-trained model. So the pre-trained model was how we was running inference up here at the top. So now you can just go in and hit start train. If you want to run inference, you can do it in the exact same way here. I'm just going to grab the code snippet. There we go. We can pull in a new model, and then instead of train, we can just call predict. We can throw in a video. So this is what I did before. I just did some runs so I can go in and do comparisons of YOLO11, YOLOv8 on different videos. So predict here, we can just specify our road. So we copy a path. There we go. We can specify that we want to save it. We set that equal to true, and then it's going to save a video file. So while it's actually like training here, we can see that now we get some different predictions, epoch 1 to epoch 100. So we're training for 100 epochs. This is probably a bit too much. Let's just cancel it and only go for 50 epochs because we only have 100 images in this data set. There we go. While it's training here, let's grab up some videos that I just ran through. So I have this example here. This is a video covering the YOLO11 model, or the new 12 model, and this is the Nano version of it. Then I also did the exact same thing with the YOLO11 model. and we can just run the results here on the sideline. So just initially, it looks very similar when I'm looking at the cars. Maybe we get some more detections from the 11 model, but again, it should run faster with optimized CUDA kernels for different GPUs and so on. The good thing about the other YOLO models is that they run on CPU directly out of the box. Yeah, I think it's very similar results here, at least for the Nano models. I was also running through the medium model just to see if we get more predictions. So this one here is the YOLO11 model. Let's grab this one. This is the YOLO11 model. Now we start to get some cars up here in the background and also a bit further away. So once they start to come around this region here and this region, we actually have detections with the Nano model, or this is the medium model. Let me close all these and let's grab the last one here, which is the new 12 model with medium size. So I think the medium size, it's definitely better with the YOLO11 model, definitely, and even like YOLOv8 might be better than YOLOv11, at least on smaller objects. So just initially here, might be that it's a bit faster, but just because we have a new version in the YOLO family doesn't mean that that's the best model, especially like if they just run it on the benchmarks, because it depends on the GPUs that they're using, the CUDA versions and all that, because they're using this flash attention, which is optimized for CUDA kernels. So I'm not really seeing better results with the new YOLOv8 model. Let's see, we're probably going to do a pretty good job on the training because it's a relative easy data set. But make sure that you test out your data, you test out your projects on various different models. Just from the initial results that I'm seeing here, because we can't use like CPU, it doesn't look as good with the larger models. I think the YOLO11 and the YOLOv8 model is still like better compared to this one here. I have to play around with it like way more, use it for different projects, different use cases and so on. But initially here we might get some speed ups. I've been running some different speed ups, maybe need some more optimization and so on, but I'm not really seeing it's that much faster compared to the YOLO11 model. So we'll see in the future when I get to run more tests, but this is how you can train the model, and it's very important that you train it. It's so easy to train, like it's just a single line of code, and if you want to train it on a YOLO11 model, we basically just copy paste the exact same thing, paste it in here, we change it, this is only called YOLO11, we have a small model, you can run it here, and then you can run like 3 different models. You go grab a coffee, probably more than one coffee because it will probably take an hour or something like that. So you can grab a few coffees, you can come back, and then you have trained a ton of different models basically. So that's very important. Now it's done training, we get our evaluation. So precision recall pretty much 1, mean error precision is also pretty much 1. So this is almost like a perfect model. Very good to use directly out of the box. So now we can also go in and do evaluation. Could be that we have more classes and so on. Then it makes sense to go in and look at the confusion matrix. So it's not gonna like create one for that right now. If we go inside our run folder, or it is. The reason why I got it is because I have like train 2. We didn't finish the first training. We converted it to epoch 50 or 50 epochs. So yeah, this is our results. We get our train 2. If you want to grab the custom model of your train, we just go in here, right click, download the best.pt model, and you can use it in your own custom Python script, application, and project. We have our results, PNG as always. We can see the training metrics, so the recall precision, how it's going up over the number of epochs, and we can see here that it's pretty much enough with 50 epochs. Some of the losses still going down, but the precision recall, mean error precision, and so on is pretty much perfect. So this is very important to run through. I'll just run through it here. If you use the Colab notebook, it'll be down in the description. So you can just grab it, run these blocks of code, and you can create like a computer vision model. Use RoboFlow for setting up the whole pipeline, the data, and so on. You don't really need to write any code. It's just copy paste and run through some commands. Now we have computer vision. We have missing hole. Let's go in and grab the best trained model. So train 2. There we go. You can see the mean error positions, pretty much perfect. We can also plot it directly when we're using supervision metrics. So this is very good if you're creating report, if you're a student, if you're a researcher and so on. Supervision, like it's very good for visualizations, plotting, graphics, and all that. Now we can run inference with the best trained model. Again, I need to change it out here. You can also just, if you download to your own local machine, just drop it into your directory, and you can just specify the relative path as well. There we go. And now let's just run through some examples. We have a missing hole here, detected perfectly, but again, we also expect that with the model results that we are seeing. So this is how easy it is. Again, we can just run it again because it's gonna grab a random image, or at least it should. Yep, it is. So yeah, we're basically just running through random images here and detecting missing holes. Here we have 2 missing holes in our PCB soldering. This is how easy it is to use the new YOLOv8 model. It's a new family member, but again, it's just as easy training any of the other models, if not easier, because you can use CPU. You don't have all these different things that you need to take into account. Just wanted to cover this new video here. Gonna cover it more. We need to test it on some more real world examples, see how does it actually work. Is it better than YOLO11? Just because we have a new version it's not just equal to a better model, even if it's showing it on the benchmark results. Sometimes I'm seeing like very good benchmark results, but when you get it into run in real world projects, it doesn't even get anywhere near those results. Hope you learned a ton this video here. Definitely going to check it out. We'll have it available with Ultralytics. You can use RoboFlow, very cool platform to have the whole in there. I'm creating a bunch of tutorials covering both platforms as well. This is what you need if you're a computer vision engineer, or not even a computer vision engineer, if you just want to create computer vision projects, do detections with cameras, videos, and so on. Hope you learned a ton. Hope to see you guys in one of the upcoming videos. Until then, happy training. Hey guys, and welcome to a new video. In this video here, we're going to control a smart home with the new YOLOv8 model. So we're going to use this YOLOv8 model for object detection, so we can actually control a smart home. We're going to turn on and off the lights based on if we detect people in the image. So we can actually control my lights in my living room. We're going to see that at the end here. First of all, we'll go through how to set up the YOLOv8 class and also how we can connect to the Philips Hue bridge. You can also use this for Wish. I'm going to create another video about that. So definitely make sure to hit the subscribe button and bell notification under the video so that you will get a notification when I upload that video. So we can both control our smart home with Philips Hue and Wish. So we basically just jump into the code, see how we can set it up, and then we're going to see some really crazy results at the end. So we're going to jump straight into Visual Studio Code. I'm going to show you how we can use the YOLOv8 class that we made in one of the previous videos. So if you want to know more details about that, definitely go check that one out. We basically just create a class where we load in the new YOLOv8 model. We can just specify what model we want to use. We can also train our own custom models, videos about all of those different things on the channel. Then we're basically just going to take an image. I'm going to have a webcam in my living room streaming over Wi-Fi to this computer here. And then we're going to run inference on that and control the smart home and my lights in my living room based on the predictions we get from our YOLOv8 model. So first of all here, we're just going to import the different modules. We're going to set up the object detection class. Then we're going to connect to the Hue bridge. And then we can actually just turn on and turn off the lights based on the predictions that we get. So first of all, we just import the different modules. We need PyTorch to run this YOLOv8 model. We also import CV2 so we can do our image processing. We can load in our images. We can also display the detections and visualize the results. Here, we're just going to use the YOLO class from Ultralytics, so we can use the YOLOv8 model, just directly load that in. We're also going to use supervision for the detection part, and then from Philips Hue, we can import bridge, and then we can connect to it with our IP address. You can basically just go into the app, and then you can find the IP address under settings. You'll basically just specify your IP here, and then you're connecting to the bridge. Then we can use this to actually just connect to the light. You just go in and specify the name of the light, as I'm going to show in just a second. So first of all here, you just need to pip install all these different things. So I'm just going to open up a terminal. I'm just going to show you how we can pip install the Hue. So basically here, we just hit pip install as with any other framework or library that we're going to install. So we just have pip install. Then it's just called Hue for Philips Hue. We can see that my requirements are already satisfied, but this is the only step you need to do to actually import this Philips Hue bridge that you can then use for controlling your smart home and your Philips Hue light. And then all other things here is basically just the same as in the previous videos. we have our object detection class. First of all, we set up our video capture. If we have a CUDA device available, we're going to use that. So CUDA if it is available, or else we're just going to run it on the CPU. We're going to load in a model here as well. So first of all, we just have a function for loading in the model. If we just go down and take a look at that, we basically just have load model. We set our model equal to the YOLO class, and then we specify the model that we want to use. So this is the pre-trained YOLOv8 Nano model. So again, we're going to use the Nano model in this example here just to show you that we can get some really nice predictions, even though we're running on the Nano model. We can also like choose a larger model, but we want to have this running in our living room controlling our light. So we don't want like too large of a model running, and we don't really need that if we're just going to detect persons in the frame. Our detections will actually be a bit slow when we're going to run it. It is not because of the size of the model. Like I can run the YOLOv8 extra model with up to like 50 frames per second, but our frames per second will be around 10 frames per second because I'm going to use the webcam from my phone in the living room, and then we're going to stream the images over the Wi-Fi, and then we're going to load it in with OpenCV. So that will take up some of the processing, and just the delay of actually like loading in the images will slow down this project and application. Then we're just going to fuse our model, and then we're going to return it. So we just have self.model. We just load in the model that we want to use. We can set up the class names dictionary, and then we're going to set up this box annotator that we're going to use to actually like draw these bounding boxes. I go into way more details in the YOLOv8 tutorials I have here on the channel, where we actually like implement this class. So we also have this predict function. We basically just take in a frame. We have our model, we pass the frame through our model, we get the results, and then we're just going to return those results from this predict function. Now we go down and just use the results to plot our bounding boxes. So first of all, we can extract all the information, the X, Y, coordinates of our bounding box, the confidence scores, and also the class IDs. Then we're just going to have a for loop running through all of our detections. First of all, we just set the class ID. We can extract the class IDs from the results like this, and also the X, Y coordinates for our bounding box and our confidence scores. So here, if the class ID is equal to 0, that means that we have actually detected a person in the frame, and then we're just going to append the results from that person we detected. We're going to append that to those lists here, and then we can use that to determine when we should turn on and turn off the lights, as we can see down here in the next line of code. So here we're just going to use the class ID. So if the length of our class IDs is greater than 0, which means that we actually have people detected in the room, then we're going to turn on our lights in the living room. We basically just have our bridge, so our B instance here. So we have b.setLight. And then we basically just specify the name of the light. So I have 2 light sources in my living room that we're going to turn on. So that will be living room 1 and living room 2. This depends on the name that you assign to your light source in the field of view app. Then we're just going to specify on. We're going to set that equal to true. So if our class length is greater than 0, which means we have a person in the room, we're going to turn on the lights. Else, if we don't have any detections in our room, we're just going to set them equal to false. So we're basically just going to control our light based on the predictions that we get from our YOLOv8 model. So this is actually like a really cool project that we can use in real life. We can actually like control something in our home based on these detections from the YOLOv8 model. And as you can see here, it is pretty simple to set up. So you can actually like create some really nice applications around this. For the detections and for the bounding boxes that we're going to visualize, we're going to use supervision from RoboFlow. So we basically just have imported supervision as SV. We just create detections with our confidence score here, our bounding boxes, and also the class ID. And then later on, we can just call this function box underscore annotator dot annotate. We pass in the frame, the detections, and also the labels that we want to show. Then we're going to return the frame here because this is basically the function for plotting our bounding boxes. So now we're going to go down to our call method in this class. We're going to open up our video capture with OpenCV. So here we can just set the capture index. We're going to specify that when we create an instance of our class. We just assert that our capture is actually like open. We set the frame width and the frame height. So this is how you can control the resolution of your images. I'm just going to set it to full HD here so we can see some really nice results. My application here and project would not really be slowed down by the resolution of the images or the network that we're going to use, but by actually like transferring the frames from our Wi-Fi connection from my mobile phone here to my computer. So if I just use like a USB webcam, it will be way faster, and I could be able to run like 50 to 100 frames per second on my PC. So then we're just going to have our while loop running as long as we want to until we hit escape or Q on our keyboard, and then we're going to terminate our program. First of all, we just start a timer. We read in a frame from our webcam. We store it in this frame variable that we can then use to throw through our model. We call this self.predict function. So we basically just take a frame, pass it through the model, and then we get the results. We can then use those results here to plot our bounding boxes and also control the lights. So we are controlling the lights inside of this plot boxes function. You could also like return the results, and then you can have another function for act like controlling your smart home. So that would act like be a pretty good idea. So we pass in the frame and also the results, and then we get the frame back again with all the detections drawn on top of our frame. Then we can end our timer, calculate number of frames per second. We're just going to put out the number of frames per second on our frame, and then we're going to use imshow from OpenCV to visualize our results that we have in the frame. And then we're going to control the lights, and then we can see how it actually works out. We just have our if statement here checking if we hit escape on a keyboard, we will terminate our program, release our webcam, and destroy all the windows that we have opened up with OpenCV. Down here, we're just going to create an instance of our class, which is called detector. We set that equal to object detection, and then we just specify the capture index of our act like camera. They could act like be 0 if you only have one camera connected to your computer. We basically just call this detector call function down here at the bottom, and now we're ready to control the lights in my living room based on the detections that we get from the YOLOv8 model. So now we're going to run the program. We can see the detections here in the frame. We get around 10 to 12 frames per second. Again, that is because I'm streaming my frames from my camera on my phone to the computer. Here we can just see we get all the detections. We get a really nice confidence score both for the person but also all the other objects. But here in this example, we only care about the person detection. We get around like 0.8, 0.9 in confidence score, so we act like pretty confident when we're doing these detections of the person. Here we see that the lights actually like turns on pretty nicely and also turns off again when I'm going out of the frame and we don't do the detections. Here we're basically just going to see me moving around in my living room, and then the lights will turn on based on if we act like get detected in the frame. This also works with multiple persons, but again, the idea behind it is that we want to control these lights based on if there's any persons in the room or at least in the frame. We could also have like multiple cameras and so on and then merge the detections, but here we can see it works very nicely when I'm moving around. You can basically like control your whole home. Let's say you have different like light sources, you just have a camera in each room, then you can actually like just go in and turn the lights on based on the detections for each camera. So you can actually control like every single room of your house. That would act like be pretty cool to do as well. Here we can just see that I'm controlling my living room, and again it actually like works out pretty smoothly. The lights actually like turn on in a very natural way when I'm walking into the frame and act like going inside of the room. I actually want the lights to turn on at the exact same time as it does. So this is actually like a really cool application and project that we have done. You can try out more light sources, and I'm also going to do another video where we're going to use the Wiz lights instead of the Philips Hue. So this is some really nice results we get. We're actually like able to control a smart home or my living room based on detections from the YOLOv8 model. We were only using the Nano model, but we saw we were still able to actually control my living room with really nice detections. It was actually controlling the lights very good when I was walking like in between like the frames around in the living room, when I was going out of the frame and so on. So it also depends on the camera placement, but some really nice results. This was a really cool project. We're definitely going to do that way more in the future. And again, I'm also going to show you how we can do it with the Wiz lights. So thank you guys for watching this video here. And again, remember the subscribe button and bell notification under the video. Also like this video here if you like the content and you want more in the future. It just really helps me and the YouTube channel out in a massive way. So I'm doing these computer vision tutorials where we go over like all the basic image operation, camera calibration, stereo vision. Now we're using deep learning together with computer vision. So if you're interested in that, I'll link to one of the tutorials up here, or else in the see you next video, guys. Bye for now. So we have a new member in the YOLO family, YOLOv8. It was just released yesterday. We're going to create a video on how we can train a custom YOLO10 model in this video. Every single step from scratch. We're going to see how we can generate a dataset, connect to a webcam, store individual images, how how we can upload them to RoboFlow for labeling, export into a Google Colab notebook, and see how we can fine-tune a YOLOv8 model. Then we're going to export and run it live on a webcam to see how we can set up the whole computer vision pipeline. So let's just jump straight into the YOLOv8 GitHub repository. We're just going to scroll through it quickly. So it's just released yesterday. Here we can see the benchmarks where it compared to all the other versions in the YOLO family. So we have YOLOv8, YOLOv8 8, 9, now also YOLOv8, but it also compares it to some of the other YOLO models and also the real-time detection transformer. And just by looking at the results, we can see that this model is significantly better on the CharuCo dataset. So just to make it clear, this is still on benchmark, so the CharuCo dataset benchmark. Could be that some of the other models are still better for your specific applications and projects, so definitely test out various models on your specific dataset. So right now, we're just going to take a look at the results. We can see the mean average positions. We have better performance on pretty much all the models, but the huge advantage from the YOLOv8 model compared to all the other YOLO models is the inference speed and the latency that we can see down here on the x-axis. So we can see that it only takes around 2 milliseconds to process a single image with the Nano model. We have the Nano, small, medium, large, and extra large model, the exact same variations as we have with YOLOv8. So this is actually built on top of the Ultralytics framework. We can use all the models from Ultralytics directly, training, validation, inference, export the model, and so on. So that is built around that framework. If you just go through it, we can see here we can download all the weight files. We can see the number of parameters, floating point operations, and also how to set up the environment. But let's just jump straight into it and see how we can do it on our own. So when we're starting out with the computer vision pipeline, we need to generate a data set. I'm going to show you the whole pipeline here. There's a ton of videos out there just showing you how you can go inside a Google Colab notebook and fine tune a model, which is relatively easy. But here we can see how we can generate images from a live webcam, which is most often the case. Or you could have like an image folder. We can upload it into RoboFlow and annotate them. So right now we just have this generate images Python script. So what it does, we're importing the different modules, so CV2 and also our operating system. We connect to our webcam. So if you have a video file, we can also specify the MP4 file, video file, and so on in here. But right now we're just going to connect to a webcam. Could also be an RTPS stream. First of all, we're going to check if the webcam is open. If not, we're just going to print that it's unable to read the camera feed. We create our output directory. This is where we're going to store all the images to our dataset. We then have our while loop just loading in frames from our camera or video stream. We show it here with our imshow function. We check which of the keys that is hit on our keyboard. If we hit escape, we will just terminate our program, close down our webcam, and then we can use our output directory as our dataset and upload it into our computer vision pipeline. If we hit S on our keyboard, we're basically just going to create an image name and then write out that image to our output directory so we can generate our dataset. So that's pretty much it. Let me just open up a new terminal. There we go, and we can just run this Python script. So generate images.py. Now I'm going to run it. It's going to open my webcam right here in front of me, and we can capture some images. So here we can see that it has pretty much just opened up this webcam, and right now we can hit escape. It will terminate the program, or we can hit S on our keyboard. So right now I'm just going to hit S. We can take up different types of objects. So right now we can have multiple objects. So this is my Apple Wallet. We can just hit S. We can see in the terminal that it actually saved these images. So say that we want to create a data set where we want to detect this wallet. Could also add my phone here as well. There we go. And then we'll just have to generate X number of images. If we want to fine tune the YOLOv8, YOLOv9, YOLOv8 models as we're doing now, we probably need 100, 200 images. We can always do data augmentation later on. But this is just to show you guys how we can have a data set. I'm going to show you some we already have on RoboFlow that we can use directly to train our YOLOv8 model. So right now I'll just hit escape on the keyboard. Let's go over and see if we actually have our output directory. So right now we have our output images. If I scroll a bit further up, here we have our output images, and we have all the individual images that we have saved in here for my Apple Wallet, but also my phone down here at the end. Then we can take this data set, upload directly to RoboFlow, annotate it. We can draw the bounding boxes, the auto annotation tools. We already have videos covering every single step in there and also in more details. Now I'm just going to show you that on a high level. So if we go inside RoboFlow, we can create a new project. Right now, let me just call it wallet. And here I'll just have a class called wallet as well. We can choose between object detection, classification, instant segmentation, and key point detection. I'm just going to create this data set. Right now we have the data set. We can go inside our code files again. I'm going to reveal it in Finder. There we go. Then we have all our images. We can just upload a batch of it. There we go. I'm just going to drag them in. It's going to upload them, and we can go in and annotate them later on. So right now it has uploaded it. We're going to save and continue, and we can always export it later on as well. So now when our images are uploaded, we can start the annotation. Right now we only have like 20 images or like 16 images, so it might not be enough to train a model, but we can just test it out. And this is like the whole pipeline that you need to set up. I just need to annotate each individual one of them. So here we have phone. I'm just going to annotate all of them, and then we can start training a model and also use data augmentation. So now we have annotated our images. I'm then going to add it to the dataset, and we can specify how many images we want to use for train and validation. Right now I'm just going to have one for each, or probably there's just a couple for our validation, just to make sure that we have enough. So I'm just going to add it to the data set. Again, this is not enough data at all. We probably need like 100 or 200 images, but it is the exact same steps that you need to do if you're creating your own projects. So right now we have our data set. We can go in and create a new version. If we go inside generate, we can specify the size of it, auto orientate, or if we need to add other pre-processing steps, probably just go with the default settings. They're more than good enough. Also, when we're going to train the model, just always go with the default settings unless you want to train something specifically or testing out multiple models. So let's now go in and add some augmentation steps if you don't have enough data. And this is the reason why we only need like 50, 100, 200 images in our data set, because then we can just use data augmentation. So right now I'm just going to add some flip, both vertical and horizontally. We can add some zooming effect as well with the cropping, and then we can just add how many images we want to have in our data set. So now we're pretty much ready. We have all the steps in here. We can specify how many images we want to generate. So right now let's just go with 7x. So we have 81 images in our data set. Let's see if that's enough, even though we probably need 100 more images to have a really good model, but we will still be able to train it. We'll still be able to fine tune it and get some results out that we can take a look at, and also run live inference where I'm moving my phone and the wallet around as well. So now we can go and export our data set. We can go in and specify the dataset format as well. So right now we can just use any of these ones from Ultralytics. So we just need the exact same format. So we can take YOLOv8, for example, you can download the zip file to your computer, or we can get this downloadable code. If we hit continue here, we just get a code snippet. We can copy it, paste it directly into our Google Colab notebook. So we have our code snippet here. We're going to copy it so we can paste it into our Google Colab notebook in just a second. So I'll now jump straight into the Google Colab notebook that we're going to use for now. First of all, we need to specify the runtime, so we can change the runtime. You can use the free GPUs resources in here so we can speed up the training process. So right now I'm just going to choose this T4 GPU. Make sure that you do that, and then we can connect to the runtime and we'll get a T4 GPU assigned to our environment. Once it has connected here, let's go in and run this NVIDIA ASMI command, which basically just shows us the information about our GPU. And here we can see that we have our Tesla T4 and around 15 gigabytes of GPU RAM. So that's pretty good. Right now we're just going to import our operating system, so we can create this home directory and set that, which is our /content in a Google Colab notebook. So that is the file system that we have over here to the left. Now we need to just go in, pip install the new YOLOv8 model and also supervision, so we can use that to show the results later on and basically just do inference. So right now we're just going to process each individual one of these. We're going to pip install YOLOv8, and it will also be integrated into Ultralytics, so you can use it directly with Ultralytics. We can call all the commands and so on because it is built on top of that framework. After we've done that, we need to go in and create a directory with our weight files, and then we're going to pull and download the weight files from the GitHub repository. So this is just the URL for the download link, and then we just call this command vget and copy all the weight files into our new directory. So that's pretty much everything that we need. If we just go inside it again, this is actually like just a link. If you right click on this one here, you can copy the link, and this is the download link that I'm showing. You can also just press on these and it will download it to your computer. So that's pretty much it. We can just run this block of code, and let's go down and take a look at how we can run inference. So I'm just going to take an arbitrary image, upload it into this Google Colab notebook environment so we can run inference and just see some initial results with a pre-trained model before we fine tune it on our specific dataset that we just created from scratch. So I just uploaded this image to the Google Colab notebook, just a screenshot from a video, and let's try to go in and do inference on it. So I go over to the left, copy the path, and then I just need to specify it in here for the file name so we can share it to start with. So we're just going to use IPython to display this image, and this is pretty much the image that we're going to throw through the model to be able to detect these bags and also suitcases. So to be able to run inference, this is the exact same thing that we're going to run later on live webcam, but in Python code. So we call the YOLO command, we want to do object detection, we want to do prediction, so this is the mode that we need to specify. We can set up the confidence score, we want to save the results, and also specify the path to our model weights, and we can choose any of them, so small, medium, nano, and this is the exact same way that you will do with YOLOv8 and also YOLOv9. So right now, let's just go with the small model. We need to specify our source, so right now that is not a video, but our image over here to the left, so just copy it, replace the source here, and we specified our image, and we should be good to go. So we cd into our home directory, call this YOLO command, and do inference on just a single image. So it might just take some time just to load up the model, but the inference is very fast with the new YOLOv8 model. So here we can see that I actually got an error. We haven't specified the correct path, so we have content twice. So I just need to make some modifications with that. I just copy it the whole path here. We don't really need to have content in front of this one because we have our home directory. So it should be good to go now. I just rerun it. We have content and we're doing prediction now. There we go. We load the model and we do our inference. It takes around 100 milliseconds because we're only processing a single image right now. So yeah, that's pretty cool here. We can also do it in raw Python code. So from Autolytics, we import YOLOv8, we create an instance of our model, and then we just call our source directly on the model instance, and we get the results out here, which we can extract. So that's pretty much it. Let's just go in and take our image again, copy the path, and this is the exact same way that you will do it in Python. There we go. We can run this block of code with Python. We get our results. From the results variable here, we can extract the bounding boxes, the X, Y values, confidence scores, and classes. So I'm just going to do that. We're going to print it out. So here we have the X, Y, X, Ys for all the different classes that we're detecting, which is most likely suitcases. CUDA device here, we're using GPU. We have our tensor with our confidence scores and also classes. So here we see that these are the class labels for suitcases in the CharuCo dataset. So these are the pre-trained models that we're using right now, but we're going to fine tune it on our own dataset in just a second. So if you want to use supervision to visualize the results and the predictions directly from our results variable here, we saw how we can extract it. Now we need to know how we can visualize the results. So I'm just going to copy paste this image again. We throw it in here. There we go, and we should be good to go. We load in our model weights, and now we're using supervision to draw our detections. We create these detections from our results, have a bounding box annotator, label annotator, and then we just plot that on top of our image. And here we can then see we have our bounding boxes plotted on top of the suitcases detected in this image. So we have some false predictions here and also here, but could probably be filtered out with a confidence score. So right now, let's go down and take a look at how we can set up and download a dataset from the RoboFlow. So right now, I'm just going to go in, copy our code snippet. We paste it in here. Then we run this block of code. It will download the dataset automatically. Then we can just call the path to our dataset and train our YOLOv8 model. So if we go over to the left now, we now have our YOLOv8. So this is the dataset that we annotated from RoboFlow. We have our test images, training, and also validation. And then within each folder, we have our images and also labels. So another cool thing here is that we have our data YAML file. So this is a structure that Autolytics and all the YOLO models are using. So we just need to specify the path, and I just like to do that manually because sometimes it messes it up. So image path here, I just copy the path and change it out here for test, train, and also validation. So here we have valid and we have train. There we go. We hit Control S just to save it. And then we just specify here we have RoboFlow, the number of classes we have 2, which is the phone and the wallet. We should be good to go now. Let's close our directory and we can then do custom training. To start with here, we're just going to go with 25 epochs. The batch size probably be a bit too large here just with the free GPU. So let's go with 8 for now. We want to plot it and also specify the model. Let's go with the Nano model for now because we don't have too much data in our dataset, and also specify the data file. or the path to our data YAML file. So that's pretty much everything that we need to do. And again, this is the command from Autolytics that we're just running directly. And here you can just swap this model out with YOLOv8 or YOLOv9 if you want to train those models. Just because we have better benchmarks on the CharuCo dataset for the YOLOv10 model doesn't mean that YOLOv8 and also YOLOv9 would be able to outperform on your specific dataset and task. We get a summary of the model. First of all, it will download it. It will set up the whole dataset, both with our training set and our validation set. So we have 77 images in our train and 3 in our validation set. So when we only have 3 images in our validation set, our training results epoch per epoch might look a bit off, but let's take a look at it once we evaluate the model and do inference later on. So our model is now done training for 25 epochs. Let's just take a look at the results. Just after a single epoch here, we already get pretty good results with the mean error precision of 0.80, but it should be able to increase over time, and also the losses come down. So here we can see that the losses 1.4, 3.4, 1.6 here, they are decreasing over time as well. And also the mean error precisions, it is fluctuating a bit in the start because it's modifying and optimizing the weight a bit more in there. And then we kind of just start to converge up here. The mean error precision of 0.50 is pretty much spot on. They should be close to 1. And we can also see the precision recall is also fairly good once we come down here at the later epochs. So let's just go all the way down to the bottom and let's take a look at the final results. So yeah, we have pretty good results, pretty close to 1 in both precision and recall. Again, we only have 3 images for our validation. So of course, ideally we want to have more images, and also here we have images, instances, and our precision recall and mean error precision. So this is the validation that is running on the validation dataset with our best trained model. So if we go over to the left here, we then have our runs directory. If we go inside runs, we have detect, and then inside detect, we have train, we have our weights, and right now we can just download the weights and use them in our Python application and projects. And I'm going to show you that in just a second, how we can upload it, how we can open up the webcam stream, set it up, draw our visualizations, and use this model in your own applications and projects on a live webcam. So let's just download the model here and then we can use it later on. But we also have all the other training graphs here. We have our F1 curve, precision recall curve. Let's take a look at that. It should ideally be close to 1, and we can see here that it is pretty much just spot on. For most data sets, you can probably expect it to curve out here a bit towards the top right corner. Another good way is to look at the confusion matrix. Ideally, we want to have all the values in the diagonal. It makes a bit more sense when we have more classes, but again, we want all the values to be in diagonal. Right now, we only have 3 images in our validation set, but this is pretty good to take a look at. We also have our training badges here, both a training and also a validation badge. Let's just take a look at our training badge. Our validation badge, it hasn't been training on those images before. Here we can see all the different predictions, or the bounding boxes around these images that we're training our models on. If you're taking a look at our validation badge here, it's just going to throw in the 3 images and do predictions on top of that. So we can see that the model here is actually able to detect the phone and also the wallet in pretty much these cases. Again, you only have 3 examples, so let's try to open up a live webcam and see how it performs. So right now, I'm just going to go inside our code editor again. Let's go in and grab our code from generate images. I'm going to show you how we can set up this whole pipeline. We have our best.pt, so this is the model that I just downloaded. Let's make this a bit smaller and this a bit larger. So right now we don't need our output directory anymore. So let's go in and delete that part. Image counter, we can keep that for now. And we don't really want to hit S on our keyboard either. We just want to hit escape for closing our application and show our results. So in between here, we need to run inference on our images, but we need to set up a model to start with. And if we just go inside our Jupyter notebook or our Google Colab notebook again, we can go in and grab the code that I showed you guys earlier on. So let me just scroll up. There we go. We kind of have the whole code base here. We need to import supervision and also YOLOv8 from Autolytics. There we go. And now we can set up our model and also our image. We don't need to do that right now. We can just take our model, create an instance of it outside of a while loop. And now we just need to specify best.pt. There we go. And this is how easy it is to set up with Autolytics and the whole framework around that. So right now, let's just grab this one here. The bounding box annotator, the label annotator can also be set up outside our while loop. So let's do that. And this would actually go inside our while loop. So first of all, we need to do our predictions. After we have done our predictions, it's going to basically just throw it in here. And to get our results,
we do this. And instead of image, we need to swap it out with our frame. So we grab our frame, throw it in here, we extract the results, and then we're going to use supervisions to create this detections instance and for image down here as well. Now we have our annotated image with both our labels annotated on top of it and also our bounding boxes, and then we can go in and just visualize our annotated frame. So this is pretty much the whole pipeline. Now we can just run it on a live webcam, see how it performs, and move my phone and wallet up in front of the camera. And this is how easy it is to use in your custom applications and projects. If you want to extract the individual results, again, you can go up and use these ones. So you can just access the bounding boxes, the X, Y values, confidence scores, and also classes. And you're pretty much good to go. You can use it for whatever application that you can come up with. And you can also use a custom dataset, an arbitrary dataset. I just took this dataset here while doing this video. You can use an arbitrary dataset. There's also a ton of datasets on the RoboFlow platform, or use your own. So this is a pretty cool way to learn how to set up this whole computer vision pipeline. We're good to go. Let's now go down and run our Python application. So webcam inference.py, let's run it and take a look at the results. So now we can see that our model is up and running. I'm just running this on a CPU right now. On my MacBook, we're running around 70 milliseconds inference time. So that's pretty fast as well. That's around 12, 13 frames per second. So that is actually like pretty cool just by running on a CPU, and you'll get significantly speed ups by using a GPU as well, especially with this new YOLOv8 model, where I feel like this is the advantage that you get is the inference speed or the latency, how long it takes to process a single image. So let's just take the phone now. Let's move it up and see if we can actually like get some predictions. So right now we need to have it like fairly close to the camera. I think we got one detection. Again, this is not an ideal model. We definitely need to have it for longer, train it for longer. Could also be because some of the reflections, but we actually get it in some specific situations or positions. So here we can see that it detects the phone. So this is pretty cool. We might get better results with the wallet here. Let's just try to move it up. I'm just going to rotate it around. And now we have the wallet that we're detecting in the frame. Of course, we miss a lot of detections here and there. We can probably also like lower the confidence score and so on. But now we have this custom trained computer vision model up and running. We can move it around in the frame and we still get these detections. Right now, we only do detections on each individual frame. You can also apply object tracking on top of it. I have courses around all the theory behind object trackers, how you can apply it on top of different object detection models, deep sort, and all of those stuff. Go over the theory. It's all based on a Kalman filter, how you do a prediction state and also an update state. And then it's just like an iterative update prediction states. And this is pretty awesome because then we can assign an ID to each individual track or object that we want to track around in the frame. You can use it for object counting, tracking like how long specific objects are in the frame. But this is pretty cool. This is how we can set up a whole training pipeline. And again, just remember, I only captured around 16 images with both two classes. So my phone and also this Apple Wallet. So this is pretty awesome. Probably need to have it in this orientation because this is what we had in our data set. Let's try to see if we can get both predictions at the same time. Might not be the case. We didn't really have that situation in our data set. There we go. Now we have our predictions, and this is how easy it is to set up the whole pipeline. You can take all the code. It will be available on my GitHub, and you can have this up and running in 30 minutes. So thank you guys for watching the video here. I hope you have learned a ton. Definitely go in and test this out here. This is the new member in the YOLO family, YOLOv8. I've tested out a bunch here on a bunch of different video streams and so on. I'm not sure if we get better accuracies and results on custom datasets, but it is definitely a faster model compared to the YOLOv8 and also YOLOv9 model. But it all depends on the task and also the dataset that you have on your side. So go in, test it out. You can solve from this video here every single step in the whole pipeline. It is easy to do. You just need to follow the video. You're good to go. Use it in your own applications and projects. I hope to see you guys in one of the upcoming videos. Until then, happy training. So we also have an AI career program if you want to learn how to land AI jobs and get AI freelance work. I teach you everything in there. We have programs, all my technical courses, weekly live calls, personal help, and I'd love to have you guys in there, help you out in any possible way. You can check out the program down in the description and the community, and then I'll just see you guys in there. Hey guys, welcome to the new video. In this video here, we're going to take a look at how we can set up a whole computer vision training pipeline with YOLOv9. So basically going to start from scratch. We're going to take some raw images in our dataset. We're going to use RoboFlow with the new annotation tool, so you can also label your images. Just throw your images in there, prompt it what direction I want to detect, what are the different classes that we want to have in our dataset, and then how we can export our dataset, throw it into Google Colab Notebook, train our own custom YOLOv9 model, export and use it in our own applications and projects. So we're going to cover the whole computer vision pipeline step by step. And if you watch this through, you'll be able to set up projects on your own and also train your own custom models on whatever data set that you can find out there. So we now jumped into RoboFlow. This is the tool that we're going to use to auto annotate our images. We just created a new project here. I'm just going to call it car 2, and then we also have some annotation groups. Then we have all these different kind of like project types that we can choose from: object detection, classification, instance segmentation, key point detection, and so on. First of all, here, just want to show you guys the images that we're going to use. So let's go inside my desktop. Then we have the images in here, and then I just have a bunch of images, 98 images in total. And here we can just see some image samples. So this is just like a highway or a freeway where we have like a camera. This could be like a CCTV camera that you want to do traffic analysis on top of. We can even apply object tracking on top of it. I'm going to show you all of that. So the whole pipeline and how we can run inference at the end. So it's basically just a camera, live camera, where we have sampled some images from. You can also use your own web camera. You can use like different types of cameras, video streams and so on, even just individual images where you actually want to generate your own data set so you can train custom computer vision and AI models. So here you can basically just see all these cars here. We can prompt auto annotation tool with RoboFlow using grounding Nano. So that is a foundation model that you can actually like prompt. So it's going to find a specific class, but also give you the bounding box around each of the individual objects. So yeah, we can both like just specify a car. We can also like have trucks and so on. We can add an arbitrary class. So it's not just take all of our images here in our data set that we want to use, create a public data set. So first of all, here we just create the data set. Now we're inside the RoboFlow project tool. To start with, we just need to drag and drop all the images in. I'm just going to hit Control A. So I copy all the images and I'm just going to drag them in. It will just take a couple of minutes, probably just a couple of seconds, depending on your internet connection. So right now we have all our images. We can now hit save and continue. It's going to upload the files, but we can just get like a quick overview all over all the images. Once it's uploaded, now we can go in, start the manual labeling process, but that is very time consuming. And I promise you guys, it is also very boring, where now we can actually just automate it with some of the new foundation models that have come out. And this both applies for object detection, but also instance segmentation. So we have different models, different foundation models that can both output like bounding boxes, segmentation mask, and so on, and even assign a label to them. So we can use that to get our specific objects in our data set. So right now we can just hit start auto label, and this is everything that we have to do. Now we get these different options. So we have different classes. So first of all, we need to specify our class name. So that is a car, and we can also prompt it. So we're just going to prompt the car as well. Could be that we want to like prompt it with specific shapes or even like colors. Let's say that we only want to detect yellow cars. We're also able to do that. We can also go in and add multiple classes here. Let's say that we want to add a truck as well. If you want to do that in our dataset, truck, we could even just be like a white truck. So we only want to detect those in the images. And this is actually just how you keep on adding classes for the specific objects that you want to train your model on. So you can then use it later on to do detections in your own custom applications and projects. But just delete this class here. Let's just go in and act like just detect the cars. First of all, we get a couple of test images. So we have 4 in this example, and then we can just generate the test results before we process our whole data set. So we actually need to have some credits here on the RoboFlow platform to be able to use this tool. So that's also why it's pretty nice to just see this preview before we actually just run through all our images. We also need to play around with the confidence threshold here as well, which basically just means like how confident is the model in each of the predictions for the classes here that it has assigned, and also the bounding box. And then you can basically just fine tune it. Let's say that the model is 50% confident, then it's actually going to assign the label car and also draw the bounding box. And then we can just have this track bar that we can play around with. Here we can, for example, see that our model is not confident more than 85% in any cases, and then we can just lower it to get more predictions. So we can see that we have some cars here up at the top. The model is not able to detect it now, but if we just scroll a bit further down, we can actually see that it gets significantly more detections. But if we just go all the way to the end, we can see that we get some false predictions over here. These are definitely not cars. So I think if we basically just fill it out around here, so like around 20%, that pretty much just gets every single car in this image, even some of them up here at the top, which is even hard to see from the human eye. So right now I actually think that this confidence score threshold is pretty good. We don't have to do anything. We can just scroll through a bunch of the examples here in our test set. Just scroll up. So here we just scroll through them, and I'm pretty satisfied with the results. Just run through 4 examples. We can see here that we detect a car, even though it's just like a trailer behind the car. But we can train our model on it. We can go in and clean it up. We also have to go into the approval stage after this step. So auto label with this model here. Now we can see that it takes 1 credit per image. Start the auto labeling. It'll just take a couple of minutes, maybe just a few minutes. And then we have all the labels for dataset. We can now export it and use it to train our own custom models. So we can now see that it's done with the auto labeling job. We can now go into it and we can just like add approve to dataset, or we can go in and manually approve them or reject them. We can even go in and adjust the bounding boxes if you need to do that, or if it had misdom detections, you can go in and add those or delete detections if we have some that we don't want. So you can basically just go manually through it here again, just to make sure that you have all the correct labels before we train our models, because trash in is also trash out when we're talking about like training AI models, and that pretty much applies to every single domain within AI. But again, generally these images here look pretty good. Again, it shouldn't have too many problems with cars, but if you're just satisfied with it, we can also just go over this preview, just go through them, see, okay, it looks pretty fine. We can just add approve to dataset or approve all up here. There we go. Now we can choose the train, validation, and test split. Let's just go with default values here. Maybe just lower the validation and test a bit, and we hit add images. And now it's going to add that to our dataset. We can go into the left tab here, hit generate. Now we can go in and add pre-processing steps and also augmentation if we want to like have even more data and make our model generalize better. Could, for example, as we just go down here, we can have augmentation. So we can have both flip the image, we can rotate it, crop it, rotation, and so on. When we're just detecting cars in this specific example, it probably might not make sense to do flipping, not even rotation. Could be a bit of cropping, but again, it depends on the camera angle. Right now, it's just going to do a bit of cropping. So there we go. Now you can see that we can increase the cropping. So this is the zooming effect in the image. So let's just add around like 10% for that, basically just to get more data to our data set. Now we're going to choose like how much we want to do for our annotation. Maybe just go ahead and use augmentation or delete that. So we have crop 10%, and let's just go in and add some saturation. There we go. We'll hit apply, continue, and now we can create a new dataset with 176 images. So again, here we can see that we act like just double our dataset by using data augmentation. So if you don't have enough data, you can basically just go in and use data augmentation. Now we can train a custom model here. We can also export dataset. We can train it directly with RoboFlow. We have our dataset split, pre-processing, and augmentation steps. So now going to export the dataset. We're going to train a YOLOv9 model. So they have all the different formats here, but again, we're going to use Analytics to train our YOLOv9 model. So we could probably get away with using the YOLOv9 format. I'm not too sure about what the differences are, but they're probably very similar since YOLOv9 is built on top of the Analytics and YOLOv8 and 5 framework as well. So it's basically just the text annotation files where we have the class ID and also the bounding box value. So that's pretty much it. We just have an image and then we have a file with all the individual classes, all the individual annotations with the class, the bounding box in a single file, and those act like just like image and label pairs. So now hit show downloadable code, we'll get a code snippet. Then we can basically just copy this code snippet, throw it into our Google Colab notebook and train our models directly. So right now I just created a Google Colab notebook from scratch. I'm going to show you all the individual steps that I'm doing instead of just like having a Google Colab notebook that we just run through block by block, so you guys can better understand like what's going on in the whole process, and everything will be down in the description so you can just directly take it. Now you're going to learn it from this video and you can try to apply it on your own data sets. So first of all here, we just need to do our imports and so on, but let's now go in and just use Analytics. So first of all here, let's go inside the Analytics documentation. If you go inside the modes, we can see that we have train, validation, predict, export, and all those different things. We have a bunch of tutorials in here and also with videos. If you scroll a bit further down, we can then see how we can go in and train these models. So there we go. This is actually like how easy it is to use. We just need to import YOLO from Analytics, create an instance of our model, and then we can just directly train it, where we need to specify the data path. Specify number, epochs, image sizes, if we want to use GPU, and so on. So I'm just going to copy paste this code snippet. First of all, there we go. Inside of our Google Colab notebook, we need to make sure that we have pip install Analytics. So this is how you can do it in a Google Colab notebook. We want to run this on a GPU, so we go inside the runtime and make sure that we have our T4 GPU assigned to us. So let's hit save. so connect to the runtime. Now we can see that it has been connected and we're now running this runtime on GPU. Let's go in and pip install Autolytics, and then after that we should be able to go in and train our model. I'm just going to take the code here as well. So the code, we copy paste in our code snippet from RoboFlow, and we will be able to use our dataset. So the only thing that I've done is just pasting in this code snippet that we got from RoboFlow, and right now I've just deleted my API key and already ran this block of code, so we should be able to go over to the left and see our dataset. So now we have our car, we have test, train, and validation, and we also have our data.yaml file. So if we just open that up, we can actually just see the path to our test, train, and validation split. We also get some other information here, the number of classes and the class names, which is a car. So first of all here, what I like to do just to make 100% sure is that we just go in and specify the correct path. So let's just go in and copy the path directly for our test set, because right now we're using a Google Colab notebook and we have this content directory. And here we have train. And the last one here is validation. There we go. We hit Control S for save. Now we can just close it over here to the left. We can see how I have our images. So these are the images that I showed you in the start. And we also have the corresponding labels. We have the class here on the left side, and then we have the bounding box for the rest here. So this is basically just the format that we're using. So now once we have our dataset, I've just scrolled a bit further down, and now we're ready to use the Autolytics code for training our model. The only thing that we need to do is specify the path here to our data YAML file. So we're just going to copy that. There we go. We set our data equal to our data YAML file. We specify the number of epochs. We can probably lower this to 30 just for the sake of training. The image size, so this is the image size that we export our dataset to with RoboFlow. It's also automatically going to use the CUDA device, but this example is if you have multiple devices and CUDA devices available. So this is pretty much everything that we need to specify. Of course, we can specify a lot of other different kind of like arguments, but you can find those on the Autolytics documentation. If you just go inside train, we can specify all of these arguments. So the number of epochs, patients. If we want to tune around on the batch size, we probably want to lower that as well, depending on how much RAM you have. You can specify save, cache, the device, and so on. If you want to use CPU or GPU, you can go in and check all of the arguments in here, and they also have a pretty good description of it. But let's just go in and specify the batch size as well. So batch equal to 8. There we go, we should be good to go, and within the GPU limits. So we create an instance of our model. Let's just do that in one block of code. So actually I just saw here that we're using YOLOv8 model, but if we just go inside Autolytics, we can go inside our models, and these are all the different models. You can go in and see if they're supported for training, inference, exporting, and so on. But right now let's go down to YOLOv9, and we also have all the other models over here to the left. Let's scroll a bit further down. We can see we have YOLOv9 C and also E model usage. This is how you can use it, and again you just need to specify YOLOv9 C. So that's everything that we need to change here, YOLOv9 C, and this is how easy it is to swap between the different models with Autolytics. So now we're going to create an instance of it. Let's see if it's able to do it. First time we run it, it's going to automatically download the pre-trained weights. So we're actually going to do fine tuning. So first of all, the models here have actually been trained from scratch on the CharuCo dataset. So that is a pre-trained model, and now we're going to fine tune it, which means that we're just going to make some small modifications, some small changes to the weights in our neural network and in our model. So it fine tunes to our specific data instead of like a general dataset as the CharuCo dataset. So there we go. Now we have it. We can go down and use the training code. So let's just delete this part. It has nothing to do with what we're running. And again, you guys can see how easy it is to set up this whole pipeline. Let's now try to run this and see if we can get some results and act like the training running. So now we can see that our model has started training. Only one line of code, and we can train a custom YOLOv9 model. First of all, here is going to download the dataset, download the weights and so on. We get a summary of the model. So these are all the individual layers in our model. We can also see here that it starts up a bunch of other things. So like both the training, it scans for the training images, optimizer, the validation set and so on. You can see the optimizer. So it's Atom V, and we also have the learning rate and so on, the momentum. You can specify all of those arguments, but if you go with the default ones, you're pretty much good to go in 90% of the cases. So here we see all the epochs. We're training it for 30 epochs. We basically just go like one by one. So over here to the right, we can see the mean error position of 0.50 and also the mean error position 0.50 to 0.95 in intervals of 0.05. So it's basically just the precision at different levels, and then we take the mean across all the classes. But in this case here, we only have one class, and we can see that we actually get pretty good accuracy. So we already get pretty good results out of the box because, again, we're just fine-tuning it on a car, and the CharuCo dataset already contains tons of cars, so it has already been trained on that. Right now we can see we're pretty much done. Let's just let it run here for the last couple of epochs. We also get the class loss, so we can see that slightly decreasing over the number of epochs, the box losses and so on, like how does the bounding box act like fit around your object, and we can also see how many instances do we have per epoch. So an epoch is basically just running through all of our images in our data set, and then for every single batch. So when we have a batch size of 8, we just take 8 images from our data set, and then we have a number of batches. So our whole data set is basically just divided into batches, and within each batches, we will have 8 images. Then we run through all of our batches, our whole data set. After every epoch, we're going to optimize and fine tune the weights in our model, and then we just keep repeating that for a number of epochs and iterations. So now we're pretty much good to go. After the model is done training, it's going to do some validation, and we also get a bunch of different graphs and outputs over to the left in our folder. So we're going to have this run folder, detect, train, weights, and then we can go and extract the best weights and also the last weights. So most often you'll just use the best weights while you're training your model. You just go in directly, hit download, you can download into your own computer using your own custom applications and projects. So we're going to do that right now, and then I'm going to show you how you can load it in and use it on your own. So while it's doing that, let's go in and take a look at the confusion matrix. So that's also pretty useful when you want to detect objects. So ideally, if you have multiple different objects, you want to have all the values in the diagonal. So this is really useful. Just taking a look at the mean error position, the confusion matrix, and also the precision recall. It's pretty much what I'm using most of the time to get a good understanding of how does my model perform. And we can also go in and take a look at how our model perform. So if we go inside our validation prediction, so this is batch 0 in our validation, and we should be able to get the predictions with our bounding boxes. So these images here, the model has not seen these images doing training, but again, all of these examples scenarios are pretty similar to each other, and also because this model has been trained on a CharuCo dataset, so it would be able to detect the cars even though we didn't do any fine tuning. But this is just to show you guys how you set up the whole computer vision pipeline, fine tune it on your own data set. So these are predictions directly from the model. So it both gives the label, so car in this example gets the confidence score and also all the bounding boxes for the predictions. So this is pretty cool. We can also go in and take a look at another batch here. So we both had it for train and also validation. So this looks pretty good. Now we actually just validated our model. We're taking a look at the results. We can export it and use it in our own custom applications and projects. But even though I'm talking a lot, guys, this is how easy it is to train a custom YOLOv9 model. You don't have to do anything. The Google Colab notebook will be down in the description, but it's just a few lines of code, and you can pretty much copy paste everything. Copy one thing from RoboFlow, copy one thing from Ultralytics. You hit start train, and you have a custom model. So our model has now downloaded. I've jumped into a custom Python script, and now I'm going to show you how easy it is to use a custom model as well with Ultralytics. Of course, you can set everything up on your own. You can export and extract the results. I also have videos about that, how you can extract the results and use them in your own applications and projects when we have our results generator in here and do inference with the Ultralytics functions. So right now, first of all, here we have from Ultralytics import YOLO. So this is the exact same way that we're creating an instance of our class when we did it in our Google Colab notebook. But now we actually just need to specify another path to our model. So we download our best.pt. So we can just specify that, best.pt. We can also change the name to our car model or whatever name that we want. We just want to have this .pt model. So this is how we can create an instance of our model. And right now we just need to go down and call model.predict. And we can then go in and specify the source, image size, confidence score if you want to save it, and also show we set that equal to true. You can go and see all the different arguments that you can set to this predict function. If you're using video and so on, you can also just change it to track, and it's going to track objects over time and assign an ID to them instead of just doing detections on each individual image. So right now, instead of specifying source 0, that will be your webcam. It's not going to work with that. So right now we can just go in and specify. I have an image example that I just took from the data set. So right now let's just go in and rename it. So I just have an error here. There we go. Image example. Underscore example dot JPEG. There we go. This is everything that we need. We can even set it equal to result. And then we can go and extract all the individual results, bounding boxes, confidence scores, classes, and so on from this results variable. Right now, let's go down to our terminal, hit Python, custom model. Let's make sure that we have saved it. Custom model.py. Let's hit enter and let's see if we get some results. So it's both going to show us the results and also save it. So right now it basically just went out immediately, even though we have show equal to true. But let's go over inside our runs. We have our detect, predict to, image example, and here we can see all the predictions on our image. We get all the bounding boxes, we get everything. So I hope you have learned a ton this video here, guys. It's basically the whole computer vision pipeline. We have tons of different tools that is going to help you set up everything. We don't even need to write any code. We can just copy paste a couple of things, have our data set, also label it, also annotate it with all the new cool AI models that has come out. So this is the whole computer vision pipeline. Definitely test it out on your own data set. You will learn a ton from it. But even though you're using this, make sure that you actually understand how a training loop works, how a neural network works, how they're actually being trained and so on. So we're just not using this as a black box, but we actually know what is going on under the hood, and also have tons of videos about that here on the channel. So thank you guys for watching this video here. I hope to see you in one of the upcoming ones. Until then, happy training. With the workflows inside RoboFlow, we can actually go in and set up a whole computer vision inference pipeline. It's just a drag and drop UI where we can take the different components, connect them together. We have our input image. We can connect them to different layers. Could be an AI model. We can have visualization layers, different condition layers, and so on. We can even hook it up to foundation models, large language models, and so on. So in this video here, we're going to take a look at the RoboFlow workflows, how we can use the templates out of the box, and also how we can create our own custom workflows. Then we basically just create it inside the UI. We specify all the things that we want. We export it. We can then deploy it either on the hosted server, your own local cloud, or you can actually deploy it on your local machine as well. It's just a few lines of code. We can connect to the inference pipeline, specify where you want to run it, live webcam, video, or whatever. So let's not just jump straight into the RoboFlow platform. I already have a lot of videos covering pretty much everything in here on RoboFlow, how we can take our own custom data set, how we can train our own model, and so on. So this is really easy. We can both use it for data labeling. You can train your own models in there, export them, deploy it, and so on. They also have a very cool feature if you want to find public available data. Maybe you can use it in your own application and projects. You might want to find some inspiration, or you basically just want to test out some different computer vision systems. So basically just have this RoboFlow universe. We can go down and choose object detection, classification, and so on. So right now I'll just take all these. Has a model, so if there's actually a model available already, you can use that out of the box for a specific data set. So RoboFlow universe projects, they already have some out of the box, both for vehicle model, they have for rock, paper, scissors, they have the football player detection system. Right now, let's just go in and take this construction site safety. There we go. We can see all the different classes. So we detect mask, ladder, safety mask, trailer, sedan, and so on. We see the metrics for an already trained model. We can use that out of the box. You can also fork the project if you want to apply some different stuff to the dataset. Could be different augmentation steps, pre-processing steps, or just add more data. You can try the model directly, or we can just go in and grab it and use it out of the box. So if you scroll a bit further down on the documentation, we can see we can run RoboFlow inference. I'm creating a whole playlist, whole tutorial with all the different tools, things you can do on the RoboFlow platform, but also with the open source tools, with the inference SDK, supervision for visualization, and all that. If you scroll a bit further down, we can then see we have code snippet for hosted API, on device if you want to run on device native SDKs, cloud, and utilities. If you want to run it from the command line, Docker, or RTPS stream. We're going to cover all of it in future videos, so definitely make sure that you are subscribed to the channel. Hit the bell notification so you get notifications when I upload new videos. But everything is pretty much just covered here. If you want to use it, we can just copy paste it, so we can just grab it. Let me just open up a code editor before I show you how we can set up the workflows. So just have a bunch of new stuff here. Let's just go in and say, so I open up my code editor here. Let's just go in and create a script called test RoboFlow.py. There we go. Let's zoom in a bit. We'll just throw in this directly. We have the API key. So here you just need to specify our API key as well. Then we can pass in our video for a construction site. We can also specify as 0 if you want to run it on our webcam. Or if we have RTPS stream, we can also directly connect it in here. From the model ID, it's going to pull this model automatically. If you have your own custom model and so on, you just need to specify your model ID and API key, and it's going to take care of all of it. So now we can just go in and save this code file, run it. Again, we have this inference pipeline, which is the main thing. It's going to start the pipeline, so it's going to run a background thread. Everything is synchronized. If you have multiple video streams, it handles all the video loading and so on. So it's basically just the best that you can get. If you deploy it on any system, like if you have CUDA device, it's automatically going to set it up for that. CPU, MacBook, Jetson and so on, all of that is supported. I definitely recommend to set it up with Docker, which we're going to cover in a future video. Then we can just talk back and forth. It will basically just be an endpoint. So we're just talking back and forth between our Docker container and our application. So just run this test_RoboFlow. There we go. Let's see if it opens up the webcam. It should pull the model directly just from the model ID. Probably just take a few seconds here to start with. Try to rerun. It is making a request to RoboFlow. And on prediction, it's going to print the boxes. So it's basically just going to take the bounding boxes, display them in the UI. We can also have another callback function where you can extract the results, use it in your custom applications and projects, as we're going to see once we pull up the workflows. So for some reason here, it takes a bit longer. Could be because of the API key and so on. So while it's loading here, let's just jump in and see the workflows. So on here to the left, we have projects. You can create a new project, object detection, classification, intersegmentation, key point detection, and so on. So you can basically just create a new project, do the labeling. Once you have that, we can create our workflow. Even just workflows, you can use the pre-trained models out of the box. They have different templates that you can use both for object detection, intersegmentation, multi-label classification, and so on. Now it actually started the video over here, so just drag it over. So you can see no mask, no hard hat, person, and also no safety vest. It looks pretty good when I'm moving around here. Looks very smooth. It pretty much gets all the detection, even though you can even see the top of my upper body. No mask, no hard hat, and we're detecting a person. Even when I'm moving around, you can see how fast it is. This is running on a CPU. So this is pretty awesome. Let me just pull up my code editor again. Right now it's not using CUDA or anything. It's running on a MacBook on CPU, and it works very fast. So let me just move around here. Like again, you can detect multiple people and so on. You can raise alerts, triggering and so on if people are not wearing a hard hat. It just took a bit of time here to pull the model the first time. Let me just try to run it again, and it should be faster. There we go. Now we can see it pretty much opened instantly. I should be able to see it connects to my webcam in a second. There we go. And now I can pull it over here. So this is pretty cool. It's just going to call this callback function. You can also have a custom callback function where you extract the results and so on, but we're going to see that once we have our workflow up and running. So let's jump back in here again. Build my own template. Detect, count, visualize. So this is just a whole pipeline. Could also be that you want to do SAHI divided into tiling windows. We have videos like covering all of it, so definitely just make sure that you check out those videos. Background removal, active learning, line counting, time and zone. If you want to track how long people are in a specific zone, I'm going to cover these templates, how we can use them, what it can be used for, and so on in future videos. You can do them for intersegmentation, classification, multi-label classification, and so on. Right now, I'm just going to create a custom workflow from scratch. There we go. We have our input, which is just going to be images, can be image, video stream. We're just going to load in images from the video stream. Could also be a live webcam as we're running on now for the other application. We can now go in and add a block. You can share workflows, you can deploy it, test the workflows and so on. But here we have all the different blocks, logic and branching, data storage, notification, video, transformation, classical computer vision, advanced, and we can also have custom blocks. So let's say that we want to send a notification once we detect that we're not wearing the required PPE requirements, or it could be any class, could be any model that you're using, could also just be a pre-trained model out of the box. Then we can go in and send different alerts, send e-notification, Slack notification, or a Twilio SMS notification as well. Let's now go and grab a model. Let's just take an object detection model. It works the exact same way for any of the other ones. We can even have the large language models connected to it. Let's say we want to create a license plate recognition pipeline. We take it, detect cars. We have another model that goes in and detect the license plates. Then we take the bounding box of the license plate, send it into one of these APIs with vision capabilities, and it will be able to extract or do the OCR part and extract the act like numbers and characters. All these are available. Gaze estimation, already have a video about that, but let's just grab an object detection model. So now we'll load all the models that I have on mine, and we also have public models. So if you want to use YOLOv8, YOLO-nas V11, V10, people detection, vehicle detection directly out of the box. So right now let's just grab the newest YOLO11 model. So let's hit save. Then we can see we have this stuff here over to the right. We have our model name, input image, so there will be an image. We can specify the model, you can change that as well. We can set a confidence score for a prediction, so let's just say 0.4. There we go. Class filter, if you only want to detect a specific classes, so right now could be 0 for a person if you only want to take that from the CharuCo dataset. Right now, let's just take all classes. We can have active learning target dataset, where it's basically just going to like save images into. You can feed that back into your training pipeline, retrain your models, and they will just get better over time. So this is also a pretty cool feature. But everything here, no code, and we will get the code snippet after we have created this custom workflow. So we have our model now. It's just going to do the inference. We will get the outputs. We will get a dictionary with our model. Then we can just take the key value, which is the prediction, and we will basically get our output. We can extract it, do whatever we want with it in code. But if you don't want to do the code, if you want to iterate fast, if you want to create some pretty cool stuff, we can go in. Either here, you can fork it, and then you can create like 2 separate pipelines going in parallel, or we can add a new element here or block. Could be that you want to do detection filtering. You only specify specific, you're only interested in one specific class, for example, for one side of the pipeline. You can create another side of the pipeline that happens like if another class is detected. Let's say that we want to detect people walking around. Okay, maybe we trigger an alert if we see a person. Then we can send an alert either to Slack or the other different types of communication like email notification that was also available directly in here. You can also create your own custom blocks. But if you detect a person, it's going to send the email alert. If we detect animals and so on, probably just going to visualize it or something else. So we can have these separate pipelines. Instead of writing everything in code, connecting the outputs and so on, we can directly do it here in the workflows, and it works very good. After we have deployed our app, if you want to make changes, you can just go back here in the UI, make the changes, hit save, and it will automatically like instant update it, and you can just rerun your code and it will have the new changes. So let's just start very simple here. Now we're going to add a bounding box visualization. Just going to draw a bounding box around the detections that we're getting. Our input image here will be our image, and the predictions that we want to visualize with our bounding box visualization, it's going to be our predictions. We add a coupler image. We can specify what color palette we want to use depending on like whatever. If you want to have your visualizations, your label and so on in a specific format, specific colors and so on, you can specify it in here. We can also choose how bounding box colors are assigned, if it's class assigned, index, or depending on if you do object tracking as well. If you want to do object tracking, I'll show you a quick tip here. You can just hit plus. Let's just search for tracker, by track, and now we have implemented object tracking on top of our object detection models, and now we will also get IDs. So if you get in here to our predictions, instead of just taking our predictions from our model, so now we can see it splits it into 2 pipelines because I just took this bounding box visualization, connected the output from the object detection model. Now I go back here again to track detection, and it's going to pull it back because then we're visualizing all the tracked objects that we have in our frame. So maybe just keep this object tracking here. Again, it's just going to track all the bounding boxes and so on top of our object detection model. I'm also interested in visualizing the labels. There we go. And we can specify what we want to visualize for our labels. Class, confidence, class and confidence, index, dimensions, area, or track ID. So right now we visualize our class based on color. So let's now just go in and specify our track ID for the text in our label visualization. That's it. That's everything that we have to do. And if we go into the output now, we can see that we can both take our predictions, we can take our label visualization. So if we take our results that we get back from our inference in our callback function that we're going to have, then we can just take our output, take the key value, label visualization, and we can show that with OpenCV. We have our model predictions, and we can also add another output here. We can select any output that we want to have. We can even see an example in here when we test out the workflow. There we go. Let's say that we maybe want to take our, could be that we want to take like all properties, or we only want to have our track detections, already seen instances. So if we are still like keeping track of the same objects, we can take our model ID, inference ID, or just all properties from this object detection model. So we're not really interested in that. We just have our model predictions and our visualizations. So this is actually like the wrong one because we want to have our track detections. There we go. So now we have a visualization image and we have our track predictions. So let's call it tracked predictions. Hit save. It's gonna save it here. We can either host it on the hosted API, so we can just test it out directly. Test the workflow here. You can drop in an image. Probably just pull out the webcam as we had before. So let's go ahead and run this application again. This is just going to run like with the other YOLO models out of the box. Just gonna open up the webcam. Have it here. Let's just grab a screenshot. And I'll just throw the screenshot in here. We can now run our pipeline and we should get our preview over here to the right with the JSON format that is going to output for every single frame that we throw through it. So here we get our output JSON. We can also like take the visualized. So right now we both have our track ID 1, 2, 3. The other bounding boxes are from the model that I just screenshotted. So you can basically just not look at those. We have our track predictions. I changed it from model predictions to track predictions in our output block, as we can see here, track detections. So this is why we have this key. We have our predictions, and we also have our label visualization with our image. This is pretty awesome. We can set up whole computer vision pipelines, drag and drop in this UI. Don't have to do anything, no code at all. Very nice structure. You can directly see it in here and test it out when it's running on the hosted API. You can also do a dedicated deployment. You can specify your name if you want to use CPU, GPU, development, or production environment. Local host if you have your own computer that you want to run inference on. You just need to pip install the inference CLI and also the inference server start. I'm going to cover like way more in the future, so definitely like stay tuned for that. Whole playlist covering all the cool features from RoboFlow, because we can use this for setting up whole computer vision systems. So we connect to the local host. It's just going to connect automatically to it. Then when we run it in here, it's going to use our own resources, and we can also do it on edge devices. So it supports real-time video, CUDA GPUs, all blocks, running, custom code. It requires Docker, but again, here you can have your server URL or local host. Right now, it's just running on hosted API. We've created a whole computer vision system. We now want to deploy it. We just press deploy here in the top right corner. We have a RoboFlow hosted API, run on an image or run on a video local. So we just get the code snippet and what we need to install to be able to run this code. So just run it on a video. I'm just going to copy paste this code snippet. First of all, we need to pip install inference. So make sure that you have that. Just close this application. Pip install inference. Already have it installed on my computer. Let's go back. We will just grab this code snippet. Everything that's happening here is just we import inference pipeline from inference, CV2. We have MySync here, which is just a callback function that is going to use every time we get a response for our image. So we have init with workflow. We set our API key to start with, our workspace name. We have our workflow ID, video reference, so path to a video or 0 for a webcam. Specify the number of frames per second, max number of frames per second. Could be use cases where you only want to process 30 frames per second or the same FPS as your input video or stream. Then on prediction, it's going to call this MySync function, and you can do whatever in here. You can store the results, you can use them for visualizations, you can use them for triggers, you can call other functionality in here, you can store them, you can have global variables and all that, but here is pretty much the main stuff. So I'm just going to grab this one here and put it into our test RoboFlow. I will delete this API key here, so it doesn't really work. We have the API key, workspace name, have all of it down here at the bottom. Right now, we don't have our output image. If we go inside our workflow again, we can see the response that we have. So it's called label visualization. So I'm going to grab that instead. There we go. We're just going to import it with OpenCV and also print the results. So when we print the results, it's just going to throw out our track predictions and also our predictions with our track ID. We get our bounding box, confidence score, and also our class ID. So this is pretty cool. Now we can just run it. It's automatically going to set it up. So let's run Python test_RoboFlow. We run it, should just pull the model. It opened up the webcam. And here we're running our predictions. So it works pretty fast. Again, this is just running on CPU with this whole inference pipeline. It loads it in very fast, real-time performance even on a CPU. We get all the outputs out at the bottom, all the IDs that we need, detection IDs, inference IDs, we have parent IDs, label visualization, which is the image that we are visualizing, and we also get our bounding boxes, track IDs, confidence scores, and so on as we're used to, and we can extract it over here. So if you want to extract like all the different things here, I'm going to create another video where I'm just going to take this result variable that is the output and just extract everything. So we just have for loops running through this result, storing it into separate lists and so on, so we can take our bounding boxes, classes, confidence scores, use them in our own applications and projects. We can build out custom workflows in here, custom blocks of code and so on, but at some point you need to take the results from this pipeline, connect it to other systems, or like build your software system around it, create an API around it or whatever, but you can do most of the work in here, even custom blocks if you want to create templates that you can use later on as well. But it's running pretty fast. We have our track ID, even though I'm moving around, we still keep track of me with ID 1 and the potted plant in the background as ID 2. This is pretty cool. Let me just show you how fast it is to update it. So I'm going to terminate the program, go back into Safari. Let's now say, okay, we don't want to do object tracking anymore. Then we have to go in and take this one. We just take our model predictions, and here we just take our model predictions again. Have our output. We don't have our track now, so we just take our model predictions directly. Have our label visualization. We hit save. We can go up to deploy again, but it's just going to be the exact same code. Jump into cursor, rerun the application here, and now we will not run with object tracking. Now we can see no track ID. We can jump into our pipeline again. Label visualization, instead of track ID, we're just going to set class. Hit save. It's still running here, as we can see. Gonna terminate it. Rerun it. Just gonna spin it up. And now we should see our class IDs instead. There we go. Potted plant, person. This is so awesome. Like, you can save a ton of time by just using this whole workflow, the pipeline, the inference, and so on. You can see how fast it is. It's running with the threaded in the background. We're going to build whole systems around this, templates. You can have your own custom templates. It has the whole computer vision pipeline. Take your data set, label it RoboFlow. They even have auto annotation tools. I have videos covering that as well, so definitely make sure to check that out. It's doing really awesome now, the video. Like, it's just going crazy now, my auto labeling tool, auto labeling video with RoboFlow. So check that out. Just drop in your images, specify, prompt it, what do you want to actually like label your data with. Could be cars, persons, and so on. It's automatically going to do it. Wait a couple of minutes and you have a labeled data set. Then you can train your models. We're going to cover that, how you can train models in here as well with RoboFlow. Upload your custom weights if you train somewhere else, and then do the whole pipeline in here. This is awesome. We're going to cover this way more in the future because this is so important. This is so valuable for computer vision engineers, machine learning engineers, and so on. You don't need any coding experience at all. Follow these guides. It's very intuitive, nice UI. We can then focus on building systems around it, focusing on getting the best models, like fine-tuning our data, trash in is trash out, fine-tune our models, get it out there, build software systems around it, act like solve business use cases, because just taking your model, training it, doing fine-tuning, testing out different models, like training it, you can just train everything in parallel, test it out, extract the results, and so all those things are like just repetitive, boring things. We need to build software systems around it, and RoboFlow, they have built this whole framework. I'm also going to build out like a whole Ultralytics playlist, RoboFlow playlist, where I basically just have like 15 videos covering both frameworks in depth. Going to do comparisons, when to use what are the pros and the cons for the different frameworks. So definitely stay tuned for that as well. And then I'll see you guys in the next video. Until then, happy learning. With the workflows inside RoboFlow, we can actually go in and set up a whole computer vision inference pipeline. It's just a drag and drop UI where we can take the different components, connect them together. We have our input image. We can connect them to different layers. Could be an AI model. We can have visualization layers, different condition layers, and so on. We can even hook it up to foundation models, large language models, and so on. So in this video here, we're going to take a look at the RoboFlow workflows, how we can use the templates out of the box, and also how we can create our own custom workflows. Then we basically just create it inside the UI. We specify all the things that we want. We export it. We can then deploy it either on the hosted server, your own local cloud, or you can actually deploy it on your local machine as well. It's just a few lines of code. We can connect to the inference pipeline, specify where you want to run it, live webcam, video, or whatever. So let's not just jump straight into the RoboFlow platform. I already have a lot of videos covering like pretty much everything in here on RoboFlow, how we can take our own custom data set, how we can train our own model, and so on. So this is really easy. We can both use it for data labeling. You can train your own models in there, export them, deploy it, and so on. They also have a very cool feature if you want to find public available data. Maybe you can use it in your own application and projects. You might want to find some inspiration, or you basically just want to test out some different computer vision systems. So basically just have this RoboFlow universe. We can go down and choose object detection, classification, and so on. So right now I'll just take all these. Has a model, so if there's actually like a model available already, you can use that out of the box for a specific data set. So RoboFlow universe projects, they already have some out of the box, both for vehicle model, they have for rock, paper, scissors, they have the football player detection system. Right now, let's just go in and take this construction site safety. There we go. We can see all the different classes. So we detect mask, ladder, safety mask, trailer, sedan, and so on. We see the metrics for an already trained model. We can use that out of the box. You can also fork the project if you want to apply some different stuff to the dataset. Could be different augmentation steps, pre-processing steps, or just add more data. You can try the model directly, or we can just go in and grab it and use it out of the box. So if you scroll a bit further down on the documentation, we can see we can run RoboFlow inference. I'm creating a whole playlist, whole tutorial with all the different tools, things you can do on the RoboFlow platform, but also with the open source tools, with the inference SDK, supervision for visualization, and all that. If you scroll a bit further down, we can then see we have code snippet for hosted API, on device if you want to run on device native SDKs, cloud, and utilities. If you want to run it from the command line, Docker, or RTPS stream. We're going to cover all of it in future videos, so definitely make sure that you are subscribed to the channel. Hit the bell notification so you get notifications when I upload new videos. But everything is pretty much just covered here. If you want to use it, we can just copy paste it. So we can just grab it. Let me just open up a code editor before I show you how we can set up the workflows. So just have a bunch of new stuff here. Let's just go in and say, so I open up my code editor here. Let's just go in and create a script called test RoboFlow.py. There we go. Let's zoom in a bit. We'll just throw in this directly. We have the API key. So here you just need to specify our API key as well. Then we can pass in our video for a construction site. We can also specify as 0 if you want to run it on our webcam. Or if we have RTPS stream, we can also directly connect it in here. From the model ID, it's going to pull this model automatically. If you have your own custom model and so on, you just need to specify your model ID and API key, and it's going to take care of all of it. So now we can just go in and save this code file, run it. Again, we have this inference pipeline, which is the main thing. It's going to start a pipeline, so it's going to run a background thread. Everything is synchronized. If you have multiple video streams, it handles all the video loading and so on. So it's basically just the best that you can get. If you deploy it on any system, like if you have CUDA device, it's automatically going to set it up for that. CPU, MacBook, Jetson, and so on, all of that is supported. I definitely recommend to set it up with Docker, which we're going to cover in a future video. Then we can just talk back and forth. It will basically just be an endpoint. So we're just talking back and forth between our Docker container and our application. So just run this test underscore RoboFlow. There we go. Let's see if it opens up the webcam. It should pull the model directly just from the model ID. Probably just take a few seconds here to start with. Try to rerun it. is making a request to RoboFlow. And on prediction, it's going to render boxes. So it's basically just going to take the bounding boxes, display them in the UI. We can also have another callback function where you can extract the results, use it in your custom applications and projects, as we're going to see once we pull up the workflows. So for some reason here, it takes a bit longer. Could be because of the API key and so on. So while it's loading here, let's just jump in and see the workflows. So on here to the left, we have projects. You can create a new project, object detection, classification, intersegmentation, key point detection, and so on. So you can basically just create a new project, do the labeling. Once you have that, we can create our workflow. Even just the workflows, you can use the pre-trained models out of the box. They have different templates that you can use, both for object detection, intersegmentation, multi-label classification, and so on. Now it actually started the video over here, so just drag it over. So you can see no mask, no hard hat, person, and also no safety vest. It looks pretty good when I'm moving around here. Looks very smooth. It pretty much gets all the detection, even though you can even see the top of my upper body. No mask, no hard hat, and we're detecting a person. Even when I'm moving around, you can see how fast it is. This is running on a CPU. So this is pretty awesome. Let me just pull up my code editor again. Right now it's not using CUDA or anything. It's running on a MacBook on CPU, and it works very fast. So let me just move around here. Like again, you can detect multiple people and so on. You can raise alerts, triggering and so on if people are not wearing a hard hat. It just took a bit of time here to pull the model the first time. Let me just try to run it again, and it should be faster. There we go. Now we can see it pretty much opened instantly. I should be able to see it connects to my webcam in a second. There we go. And now I can pull it over here. So this is pretty cool. It's just going to call this callback function. You can also have a custom callback function where you extract the results and so on. But we're going to see that once we have our workflow up and running. So let's jump back in here again. Build my own template. Detect, count, visualize. So this is just a whole pipeline. Could also be that you want to do SAHI divided into tiling windows. We have videos like covering all of it, so definitely just make sure that you check out those videos. Background removal, active learning, line counting, time and zone. If you want to track how long people are in a specific zone, I'm going to cover these templates, how we can use them, what it can be used for, and so on in future videos. You can do it for intersegmentation, classification, multi-label classification, and so on. Right now I'm just going to create a custom workflow from scratch. There we go. We have our input, which is just going to be images, can be image, video stream. We're just going to load in images from the video stream. Could also be a live webcam, as we're running on now for the other application. We can now go in and add a block. You can share workflows, you can deploy it, test the workflows and so on. But here we have all the different blocks: logic and branching, data storage, notification, video, transformation, classical computer vision, advanced, and we can also have custom blocks. So let's say that we want to send a notification once we detect that we're not wearing the required PPE requirements, or it could be any class, could be any model that you're using, could also just be a pre-trained model out of the box. Then we can go in and send different alerts, send e-notification, Slack notification, or a Twilio SMS notification as well. Let's now go and grab a model. Let's just take an object detection model. It works the exact same way for any of the other ones. We can even have the large language models connected to it. Let's say we want to create a license plate recognition pipeline. We take it, detect cars. We have another model that goes in and detect the license plates. Then we take the bounding box of the license plates, send it into one of these APIs with vision capabilities, and it will be able to extract or do the OCR part and extract the act like numbers and characters. All these are available. Gaze estimation, already have a video about that, but let's just grab an object detection model. So now we'll load all the models that I have on mine, and we also have public models. So if you want to use YOLOv8, YOLO-nas V11, V10, people detection, vehicle detection directly out of the box. So right now let's just grab the newest YOLO11 model. So let's hit save. Then we can see we have this stuff here over to the right. We have our model name, input image. So there will be an image. We can specify the model. You can change that as well. We can set a confidence score for a prediction. So let's just say 0.4. There we go. Class filter if you only want to detect a specific classes. So right now could be 0 for a person if you only want to take that from the CharuCo dataset. Right now, let's just take all classes. We can have active learning target dataset, where it's basically just going to like save images into. You can feed that back into your training pipeline, retrain your models, and they will just get better over time. So this is also a pretty cool feature. But everything here, no code, and we will get the code snippet after we have created this custom workflow. So we have our model now. It's just going to do the inference. We will get the outputs. We will get a dictionary with our model. Then we can just take the key value, which is the prediction, and we will basically get our output. We can extract it, do whatever we want with it in code. But if you don't want to do the code, if you want to iterate fast, if you want to create some pretty cool stuff, we can go in. Either here, you can fork it, and then you can create like 2 separate pipelines going in parallel, or we can add a new element here or block. Could be that you want to do detection filtering. You only specify a specific, you're only interested in one specific class, for example, for one side of the pipeline. You can create another side of the pipeline that happens like if another class is detected. Let's say that we want to detect people walking around. Okay, maybe we trigger an alert if we see a person. Then we can send an alert either to Slack or the other different types of communication like email notification that was also available directly in here. You can also create your own custom blocks. But if we detect a person, it's going to send the email alert. If we detect animals and so on, probably just going to visualize it or something else. So we can have these separate pipelines. Instead of writing everything in code, connecting the outputs and so on, we can directly do it here in the workflows, and it works very good. After we have deployed our app, if you want to make changes, you can just go back here in the UI, make the changes, hit save, and it will automatically like instant update it, and you can just rerun your code and it will have the new changes. So let's just start very simple here. Now we're going to add a bounding box visualization. Just going to draw a bounding box around the detections that we're getting. Our input image here will be our image, and the predictions that we want to visualize with our bounding box visualization, it's going to be our predictions. We add a coupler image. We can specify what color palette we want to use, depending on like whatever. If you want to have your visualizations, your label and so on in a specific format, specific colors and so on, you can specify it in here. We can also choose how bounding box colors are assigned, if it's class assigned, index, or depending on if you do object tracking as well. If you want to do object tracking, I'll show you a quick tip here. You can just hit plus. Let's just search for tracker, by track, and now we have implemented object tracking on top of our object detection models, and now we will also get IDs. So if we get in here to our predictions, instead of just taking our predictions from our model, so now we can see it splits it into 2 pipelines, because I just took this bounding box visualization, connected the output from the object detection model. Now I go back here again to track detection, and it's gonna pull it back, because then we're visualizing all the tracked objects that we have in our frame. So maybe just keep this object tracking here. Again, it's just gonna track all the bounding boxes and so on top of our object detection model. I'm also interested in visualizing the labels. There we go. And we can specify what we want to visualize for our labels. Class, confidence, class and confidence, index, dimensions, area, or track ID. So right now we visualize our class based on color. So let's now just go in and specify our track ID for the text in our label visualization. That's it. That's everything that we have to do. And if we go into the output now, we can see that we can both take our predictions, we can take our label visualization. So if we take our results that we get back from our inference in our callback function that we're going to have, then we can just take our output, take the key value, label visualization, and we can show that with OpenCV. We have our model predictions, and we can also add another output here. We can select any output that we want to have. We can even see an example in here when we test out the workflow. There we go. Let's say that we maybe want to take our, could be that we want to take like all properties, or we only want to have our track detections, already seen instances. So if we are still like keeping track of the same objects, we can take our model ID, inference ID, or just all properties from this object detection model. So we're not really interested in that. We just have our model predictions and our visualizations. So this is actually like the wrong one, because we want to have our track detections. There we go. So now we have a visualization image and we have our track predictions. So let's call it tracked predictions. Hit save. It's gonna save it here. We can either host it on the hosted API, so we can just test it out directly, test the workflow here. You can drop in an image, probably just pull out the webcam as we had before. So let's go in and run this application again. This is just going to run like with the other YOLO models out of the box. Just gonna open up the webcam, have it here. Let's just grab a screenshot, and I'll just throw the screenshot in here. We can now run our pipeline, and we should get our preview over here to the right with the JSON format that is going to output for every single frame that we throw through it. So here we get our output JSON. We can also like take the visualized. So right now we both have our track ID 1, 2, 3. The other bounding boxes are from the model that I just screenshotted. So you can basically just not look at those. We have our track predictions. I changed it from model predictions to track predictions in our output block, as we can see here, track detections. So this is why we have this key. We have our predictions, and we also have our label visualization with our image. This is pretty awesome. We can set up whole computer vision pipelines, drag and drop in this UI. Don't have to do anything, no code at all. Very nice structure. You can directly see it in here and test it out when it's running on the hosted API. You can also do a dedicated deployment. You can specify your name if you want to use CPU, GPU, development, or production environment. Local host if you have your own computer that you want to run inference on. You just need to pip install the inference CLI and also the inference server start. I'm going to cover like way more in the future, so definitely like stay tuned for that. Whole playlist covering all the cool features from RoboFlow, because we can use this for setting up whole computer vision systems. So we connect to the local host. It's just going to connect automatically to it. Then when we run it in here, it's going to use our own resources, and we can also do it on edge devices. So it supports real-time video, CUDA GPUs, all blocks running custom code. It requires Docker, but again, here you can have your server URL or local host. Right now, it's just running on hosted API. We have created a whole computer vision system. We now want to deploy it. We just press deploy here in the top right corner. We have a RoboFlow hosted API, run on an image or run on a video local. So we just get the code snippet and what we need to install to be able to run this code. So just run it on a video. I'm just going to copy paste this code snippet. First of all, we need to pip install inference. So make sure that you have that. Just close this application. Pip install inference. Already have it installed on my computer. Let's go back. We will just grab this code snippet. Everything that is happening here is just we import inference pipeline from inference, CV2. We have MySync here, which is just a callback function that is going to use every time we get a response for our image. So we have init with workflow. We set our API key to start with, our workspace name. We have our workflow ID, video reference, so path to a video, or 0 for a webcam. Specify the number of frames per second, max number of frames per second. Could be use cases where you only want to process 30 frames per second or the same FPS as your input video or stream. Then on prediction, it's going to call this MySync function, and you can do whatever in here. You can store the results, you can use them for visualizations, you can use them for triggers, you can call other functionality in here, you can store them, you can have global variables and all that, but here is pretty much the main stuff. So I'm just going to grab this one here and put it into our test RoboFlow. I will delete this API key here, so it doesn't really work. We have the API key, workspace name, have all of it down here at the bottom. Right now, we don't have our output image. If we go inside our workflow again, we can see the response that we have. So it's called label visualization. So I'm going to grab that instead. There we go. We're just going to import it with OpenCV and also print the results. So when we print the results, it's just going to throw out our track predictions and also our predictions. With our track ID, we get our bounding box, confidence score, and also our class ID. So this is pretty cool. Now we can just run it. It's automatically going to set it up. So let's run Python test underscore RoboFlow. We run it, should just pull the model. It opened up the webcam. And here we're running our predictions. So it works pretty fast. Again, this is just running on CPU with this whole inference pipeline. It loads it in very fast, real-time performance, even on a CPU. We get all the outputs out at the bottom, all the IDs that we need, detection IDs, inference IDs. We have parent IDs, label visualization, which is the image that we are visualizing. And we also get our bounding boxes, track IDs, confidence scores, and so on as we're used to, and we can extract it over here. So if you want to extract like all the different things here. I'm going to create another video where I'm just going to take this result variable that is the output and just extract everything. So we just have for loops running through this result, storing it into separate lists and so on. So we can take our bounding boxes, classes, confidence scores, use them in our own applications and projects. We can build out custom workflows in here, custom blocks of code and so on. But at some point you need to take the results from this pipeline, connect it to other systems, or like build your software system around it, create an API around it or whatever. But you can do most of the work in here, even custom blocks if you want to create templates that you can use later on as well. But it's running pretty fast. We have our track ID. Even though I'm moving around, we still keep track of me with ID 1 and the potted plant in the background as ID 2. This is pretty cool. Let me just show you how fast it is to update it. So I'm going to terminate the program, go back into Safari. Let's now say, okay, we don't want to do object tracking anymore. Then we have to go in and take this one. We just take our model predictions, and here we just take our model predictions again. Have our output. We don't have our track now, so we just take our model predictions directly. Have our label visualization. We hit save. We can go up to deploy again, but it's just going to be the exact same code. Jump into cursor, rerun the application here, and now we will not run with object tracking. Now we can see no track ID. We can jump into our pipeline again. Label visualization, instead of track ID, we're just going to set class. Hit save. It's still running here, as we can see. Gonna terminate it. Rerun it. Just gonna spin it up, and now we should see our class IDs instead. There we go. Potted plant, person. This is so awesome. Like, you can save a ton of time by just using this whole workflow, the pipeline, the inference, and so on. You can see how fast it is. It's running with the threaded in the background. We're going to build whole systems around this, templates. You can have your own custom templates. It has the whole computer vision pipeline. Take your data set, label it YOLOv8. They even have auto annotation tools. I have videos covering that as well, so definitely make sure to check that out. It's doing really awesome now, the video. Like, it's just going crazy now, my auto labeling tool, auto labeling video with YOLOv8. So check that out. Just drop in your images, specify, prompt it what you want to actually like label your data with. Could be cars, persons, and so on. It's automatically going to do it. Wait a couple of minutes and you have a labeled data set. Then you can train your models. We're going to cover that, how you can train models in here as well with YOLOv8. Upload your custom weights if you train somewhere else, and then do the whole pipeline in here. This is awesome. We're going to cover this way more in the future because this is so important. This is so valuable for computer vision engineers, machine learning engineers, and so on. You don't need any coding experience at all. Follow these guides. It's very intuitive, nice UI. We can then focus on building systems around it, focusing on getting the best models, like fine-tuning our data, trash in is trash out, fine-tune our models, get it out there, build software systems around it, act like solve business use cases. Because just taking your model, training it, doing fine-tuning, testing out different models, like training it, you can just train everything in parallel, test it out, extract the results, and so all those things are like just repetitive, boring things. We need to build software systems around it, and YOLOv8 have built this whole framework. I'm also going to build out like a whole Ultralytics playlist, YOLOv8 playlist, where I basically just have like 15 videos covering both frameworks in depth. Going to do comparisons, when to use what are the pros and the cons for the different frameworks. So definitely stay tuned for that as well. And then I'll see you guys in the next video. Until then, happy learning. Hey guys, and welcome to a new video. In this video here, we're going to do custom object detection with the YOLOv8 model. So this model was just released a couple of days ago. We're going to train it on our own custom dataset. We're going to use YOLOv8. We're going to actually like have a dataset which we labeled with bounding boxes around our objects. We're going to detect different mocks in our images. Then we basically jump into Google Colab. I'll show you how you can actually like train your own custom YOLOv8 models. It is actually like fairly easy to do. I'll show you the whole process. I'll show you how to export it and how we can actually like import in our own Python script. And then inside of a Python script, we're going to run real-time inference with our own custom trained YOLOv8 model. So I'm going to jump straight into Google Colab. I'm going to show you the blocks of code that you need to run to actually like run and train this YOLOv8 model. We're going to do validation on the model, and then I'm just going to show you how we can actually like export it. We're just going to download the model that we have trained here in Google Colab, and then we're basically just going to export the model. I'm going to show you how we can load it into our own Python script, so you guys can play around with it and you can actually like use it in your own projects and applications. So first of all here, I've just connected the runtime to the GPU. First of all, we'll just verify that we actually have access to the GPU for the training, because this will just speed up our process a lot. Then we need to pip install Ultralytics here, which will basically like be installation of YOLOv8. So inside of this Ultralytics, we have the YOLOv8 model. If you're not familiar with the YOLOv8 model, I have another video where I actually just went over the GitHub repository. I showed you how we can do live inference on a pre-trained model. But here we can see that we have now installed the YOLOv8 model, and now we are actually ready to use it. So here we can just import the different kind of modules from Ultralytics. We're going to import YOLO, we're going to import OS and some display here, so we can actually display our predictions with our model. So here we're just going to run this block of code, and now we should actually have all the modules imported that we need. So the new YOLOv8 model here from Ultralytics is actually set up really nicely. Because we just have this kind of like YOLO format, we just have like this whole code structure where we have the YOLO files, and basically you just run these YOLO commands here into the Python scripts. You can pass in different kind of like arguments to it, methods and modes and so on. So now we can actually just, first of all, before we're actually going to train our model, we will just see how to do inference on a single example with a pre-trained YOLOv8 model. So basically we just have this YOLO command here now from the YOLOv8 repository from Ultralytics that we just pip installed. Then we can just set the task here equal to detect. So then we will actually do object detection. We can also do instance segmentation and classification with the YOLOv8 model. I'm going to create another video where we're going to train our own custom instance segmentation model as well. And then we're going to use it in our own Python script. So then basically we just set the mode here equal to predict. We have the model equal to the YOLOv8 Nano model. We can also choose a small model, medium model, large model, and so on. We can set up a confidence score here. So we basically just filter out like predictions with a low confidence score. We can also like increase this. And then we just set the source here equal to the image that we actually want to make a prediction on. You can also do like, for example, a webcam here if you just specify 0, but then you will have to have it in your own environment on your local computer. But basically here, we're just going to run it to see a single example, and then we will train our own YOLO model on our own custom dataset. So that will be way more exciting than just showing this example, but here I'm just going to show you how we can do inference on a single example with a pre-trained YOLOv8 model. Then the results here are saved to runs /detect/predict, and then we can basically just go in and specify the file name here for that and show it as an image here in Google Colab. So here we can see the predictions. We get a dog, we get a person, which is actually like a really low confidence score for the dog. And it also like extends the bounding box all the way to the bottom. We also detect the car in the background. So again, we get some really nice predictions. We can like here, again, we're using the Nano model. We can also use like the larger models and so on. And we'll get way higher accuracy and confidence in our predictions. So let's now train the YOLOv8 model on a custom dataset. First of all, here, I'll go inside my RoboFlow account. You can basically just go in here as well, take one of my datasets, or you can go to the universe where you can basically like find all the public datasets. When we're doing object detection, you can just press like object detection here. And then you will get all the different kind of like object detections projects that is available here publicly in the RoboFlow universe. You can basically just go in, take one of them, export the dataset as I'm going to do now. But then basically we just go inside our RoboFlow project. In this example, we are doing cop detection, and I have this version 2. Then we can basically just go in here, hit export inside of our projects. We have the YOLOv8 format, show downloadable code, and then we hit continue. It will then zip our folder, and we can basically just take this code, copy it, and paste it into our Google Colab, and then we can specify the path to that folder inside of our notebook. So if we just go back here again to our training of the YOLOv8 model, we can then just specify copy paste in the dataset. Then when we actually want to do detections, I'm just going to run these blocks of code. So here we download the dataset, it will unzip it, and we will get it over here to the left in our directory. We can also then run the detection mode here. We can run train. So we want to do object detection. We can set the mode equal to train. We just specify the model that we want to train as well. So here we can actually just try with the medium model. And then for dataset, we basically just have our dataset variable from RoboFlow. So this will be our dataset variable up here. We can specify the location for that. And over here to the left, we can now see that I have my dataset. So we have cop detection version 2.3. We have a test set, train set, and a validation set. So this is basically all the images and also the labels for our objects that we want to train our custom YOLOv8 model for. So again, we just specified the dataset location, the number of epochs we want to train it for, and also our image size. Then when we want to train our model, we just run this block of code. Again, this notebook here will be available on GitHub. There's a link down in the description. So basically just go check that out, copy paste it, run it on your own custom dataset, export the model, and then use it in your own applications and projects. So this is actually really easy. It's really cool that we can set it up so quickly, run object detection models, and even like just train these models here, the datasets. You can just label your datasets with RoboFlow, export them, and use it in your own projects. So here we're just going to run it for 30 epochs. First of all, we get a summary of our model. We have a bunch of convolutional layers, concatenation layers, we do some upsampling and so on. We can see the optimizer. So we're using SGD with a learning rate of 0.01. And we can also see some data augmentations here. We can see the validation set, and then we will basically get the training down here at the bottom. So here we can see that we have epoch 1 of 30. We can see we get a box loss, class loss, and some instances. So how many instances are we actually detecting? We will also get some information about the mean average position of 50 and also mean average position 50 to 95 in intervals of 5. So this is the most important like metrics to look at. Mean average positions. So we can basically just see here that our mean average position is actually like increasing for each epoch that we're training. And again, we're using the medium YOLOv8 model. So now we will just let it run for 30 epochs. We'll go back in, show some results and how to actually export this model and also do validation of it. So now our model is done training for 30 epochs. We can basically just see the results here at the end. We get some really nice results. If you just go to epoch 30 out of 30, we have it up here. We can see that we get really high. We get really high mean average position 50 and also really high mean average position 50 to 95. We get around like an average position of 0.87. And over here to the right, we also get like 0.58 here for the mean average position of 5 to 95. If we just compare this with the benchmark of the YOLOv8 model on the CharuCo dataset, they get around like 0.45 in this metric here. So these are some really nice results. We can also just see down for all the classes that we're trying to detect in our object detector. We get some really nice results with really high precision. The results are saved in runs detect train, so we can basically just go inside that. So this is the file directory for that. So we have the content run detect train, and then here we're just going to show the confusion matrix. So in the confusion matrix, we will have our true labels down at the x-axis, and then we have the predicted labels on the y-axis. We can see that we get some really nice detections for that. We have some problems with this cup with a lowercase c, because this is like some kind of like redundant class. There's only like a couple of samples in that, so it's really underrepresented in our dataset. We can also go in and see that inside of our RoboFlow dataset. So if you just go down to the health check, we can see that this cup here only has like 9 samples. So this is an error in the dataset. You will go in and correct for that. And also just a standard cup here with the uppercase C. We only have 42 samples. So this is underrepresented. This is an underrepresented class in our dataset. But this is actually a really good confusion matrix. We can see the rest of the classes. It is really confident about that. And then we can basically just show the training results as well. So here we should be able to see the training graphs. You can also get all these files in if you go inside the runs, detect, and then we have our train. And then you'll basically see both the F1 precision recall curve, the confusion matrix, and then the results that we're showing right now. So you'll have that inside your train folder. So we'll just close this one here, and then we can see that the box loss is still decreasing and hasn't really converged yet. We get a really nice decline in our box loss and also the class loss. We can see the precision, it is really stable up here. We'll get the mean average position. It is kind of like converged here around like 83. Here for the other metric for the mean average position of 50 to 95, we can see that our average position is actually still increasing. So we could train for more epochs and get we can get better results, but We already have some really nice results, so we're just going to go with that. Here we're going to run the validation mode. So we basically just set the mode equal to validation, and now we just specify the weights that we want to do validation of. So this will be our train weights and then the best. So these are also the weights that we're going to export. I can just do that right now. And we just specified the path to our dataset. So if we go to the folder to the left, we can then see under our train, we have this weight file. We can get the best weights here, so the best results for the metrics while we have been training our neural network or our YOLOv8 model. So if you were going to train it for like 100 epochs and at some point like around like 50 epochs, it doesn't really learn more, or it starts to increase in loss and decrease in performance, again, you can just go in here and take the best model throughout the whole training process. If you just want to get the last model, you can also take that. But here we're going to go with the best model. You just right click and hit download. Then it will download to your computer, and then we can import that into our own Python file and run it with the new like YOLOv8 architecture in our own custom Python file. And we will actually be able to run it in real time, as you're going to see in just a second. So here we will just download this model to our computer. We can go inside and just run the validation mode. Again, I'm just going to run this block of code for the object detection. And here it's basically just passing all the images through our validation, or like through a model for our validation, and then we should get some outputs down here at the bottom. So again, we get some really nice mean error precisions on our classes for our validation. So after we have validated our model, we can now set it to prediction mode, and then we basically just do predictions on images that it has not been trained or validated on. We set the task equal to detect, and the mode we set that equal to predict now. We basically just, again, we specify the path to the best weights, and then also the dataset location for our test images, and we also set up a confidence score threshold. So here we're just going to run this code with this YOLO command, and then after that we can just go down, have a for loop running through a bunch of images, and show the results to us. So here the results are saved in runs detect on /predict2. If you want to get these images, again, you can go inside the folder, you'll get inside runs, detect, and then predict2, and then we will get all the images here. You can download them or just show them directly in the tab if you double tap. But here we're just going to show it with code. We're just going to show 3 examples, and then we can basically just run this block of code. So now we can see the results. We get a really nice prediction of the white cup here, even though it is seen from above. Another example here is the CharuCo cup, the standard cup with a really high confidence score. We have the hand-painted cup, Halloween cup, and the white cup. If I just scroll a bit up here, let's try a couple of more examples. So let's go with 5. And it will basically just run the predictions and visualize the results. So again, you can just see that these results here are really nice. We have the standard cup, we have the CharuCo cup, white cup, hand-painted cup, and the Halloween cup, and all of them has a like really high confidence score. So now when our model is actually exported, we can go inside our own Python script. Then we can actually go in and do live inference with a webcam. We'll just open up a webcam, do live inference on this custom object detection dataset, and then we're going to see some really nice real-time results. So we're not jumping into Visual Studio. I'm going to show you how we can actually run this live inference. I basically just export the model, I downloaded it, and just specify the path here to the model, and I just renamed it to cup detector. Here with this YOLO from Ultralytics import YOLO, we're basically just going to specify the path to our model, and then it will load in. It will load in the model, and we can call this predict method on it afterwards. We can specify the source. You can either have like a video, image, we can have folder with images, or we can specify this 0, and it will then use the webcam. We can set show equal to true. So this function basically just takes in all like the command arguments that we did in Google Colab as well. So we have the predict, we specify the source, show we want to visualize the results that we're doing on our live webcam, and we can also specify the confidence score. So if our confidence score for the predictions is greater than like 0.5, then we will visualize the predictions, and if they're lower than this threshold, we'll just discard the detections. So this is basically everything you need to do. In another video, I'm going to show you how we can actually modify this detection predictor class up here at the top, and how we can export the results ourselves using our own applications and all those different kind of things. So definitely make sure to hit the subscribe button and bell notification under the video so you can notified when I upload another video where we actually see how we can modify this code for our own applications and projects. I'm also going to create a video where we have a tracker where we basically track these objects that we're detecting in our image. But here basically we just run this predict function on the model, and now I'm going to run the program, and then we can just see the results. So this should be able to run in real time. I have an NVIDIA RTX 4090 card. We can see all the parameters. Here we can see the inference time. So here we have around like 5 milliseconds. So the 5 milliseconds, so that is around like 200 hertz. So this actually runs on 200 frames per second. And again, this was the medium model that we trained. So here we can see the predictions. We just have the webcam up here running. Sometimes it gets some false predictions. It detects this as a cop, but with a really low confidence score. I'll just take the webcam down here, and then I'll grab a bunch of cops or mocks, and then let's see if we can actually do live inference on the actual objects that we have trained the models on. So here, if I just turn the webcam around, we should be able to detect these mocks. So here we can see we have the hand-painted cup, we have the Halloween cup, and we also have the cocktail cup. We can see here we have the wine cup, and we should be able to detect the standard cup as well. This was underrepresented in our data set. Sometimes it loses track. Maybe we should try to take it a bit further out. So it's not really that happy about this, this standard cup. Just try to move it a bit over here to the left. So here we detect it as the standard cup, but with a really low confidence score. Yeah, so all these other cups here are really nice. We can see that we can run in real time. We at around like 5 milliseconds, so this is 200 frames per second. I have a 4090 RTX and from NVIDIA, so this is actually like a really crazy graphics card, but you can run this on like just standard GPUs, and you can even run it like CPUs. You can have different frameworks to export your models. YOLOv8 also supports that. These are just some really nice results. Let's just take this cup up and try to like play around with it, and we should be able to still get some detections. So we can see we have this cocktail cup detection. Let's see if we can get it from above. We can really detect it here. So yeah, we detect the yellow color here is the cocktail cup. It is really hard to see that this is actually a cocktail cup just from above here. But when we move it around, it is able to actually detect this as a cocktail cup. Again, really crazy model. Like these models here are so fast. You just saw how fast it was to actually like go in, train it in Google Colab, export the model, and then just throw it in here to your own Python script, and then you can play around with it. So this is actually like a really cool model. It can be used for a lot of different kind of things. I hope you guys are going to create some really nice projects on your own custom data sets. Definitely throw it down in the comment section if you have some nice ideas of what we should try to do with these YOLOv8 models, and also if you get some really nice results. So thank you guys for watching this video here, and again, remember to hit the subscribe button and bell notification under the video. Also like this video here if you like the content and you want more in future. It will help me and the YouTube channel out in a massive way. I'm doing these computer vision and deep learning tutorials where we go over the basics about computer vision, deep learning, how to train neural networks, what are the different kind of like high parameters, how is neural networks actually like trained. So if you're interested in that, I'll link to one of the tutorials up here, or else I'll see you next video, guys. Bye for now. Hey guys, and welcome to a new video. In this video here, we're going to use the new YOLOv8 model. It was just released a couple of days ago. And then we're going to actually apply a tracker on top of the YOLOv8 model. So we're just going to use a pre-trained model. We're going to implement the sort algorithm together with YOLOv8. You can also use deep sort and all those different kind of like algorithms. I'm going to show you how we can modify the code from Ultralytics and also from YOLOv8. Then we can basically just go in, take all the information. We can apply additional steps. We actually just extract information, put it through a tracker, and then we can track our objects over time. So this is actually really nice. It can be used for a lot of different kind of things in your own applications and projects. All my code will be available on my GitHub. So this is really exciting. We're actually able to run these YOLOv8 models with tracking in real time. I'm running like around 100 plus frames per second while we're actually like tracking around objects in the frame. Then we're going to do live inference on a webcam with the sort algorithm tracker. So first of all here, we just jumped inside the YOLOv8 GitHub repository. So we basically have this repository from Ultralytics. Here we can see some results for the new YOLOv8 model. We can see a comparison with the other versions of YOLO. We can see that this actually has really good performance, the same parameters, and it can actually run in real time. We can run update detection, instant segmentation, and all those different kind of things in real time. We can see some documentation of how to install it. I also have a video about that on here on the channel where I show how to install it. We go over the GitHub repository and how to set up these different kind of like parameters, and then I'll show you how to do live inference. So we're basically going to use that in this video. We're also going to use the predicted class from the YOLOv8 model, and I'll show you how we can modify the predicted class from YOLOv8. We can basically go in, extract information from our detections, feed them through a tracker, then we can track the optics over time. We can do additional post-processing steps. We can extract information. We can go in, store information, visualize the information if we want to do some visualization in another way, and all those different kind of things. So I'm definitely really excited for it. We're going to see some really nice results at the end of this video. So we're not in this Visual Studio Code. I've basically just cloned the GitHub repository from Autolytics that I just showed you. Then we have all these different kind of folders where we have the YOLO's architecture, we have the different kind of models, we have the scripts for doing detection, predictions, validation, and also training. So in this video, we're going to use this predict file. I basically just modified it where we have this detection predictor class, which is inheriting from this base predictor. And this is what is actually like handling all the predictions from our model. It will basically just take the images, feed them through the model, and then we get the outputs out. We can do some get annotator, so we can get the annotator. We can do some pre-processing steps. So this is basically just normalizing our values. We can do some post-processing where we do non-maximal suppression on our predictions. So this is basically just a detector predictor class that you can set up. And this is actually just a default one from YOLOv8. You can go in and modify it for your own applications and projects. So this is basically what I'm doing in this video here, where we go in and do the tracking. So we basically just add additional steps. So from our predictions, we go in and add a tracker on top of our predictions. We also have some write results here. So if we want to write the results out to a file, or if you just want to display them on our image, so we can have this live inference running where we can see all the predictions in real time as well. We can go in and set that up. So this is basically just the default code. Then we have this predict function that we basically call when we want to run our application. We want to predict with our configuration. So we set the model equal to a model that we load in. So a custom model. I'm also going to create some videos where we're going to custom train our YOLOv8 models, both for object detection and instant segmentation. And then we can basically just export those models from Google Colab after we've trained them. And then we can import it into here, into our cfg.model. And then we can do predictions in real time with our own custom object detector. Here we basically just set up all these different kind of like input arguments. So all the input arguments should be inside of this config, and then we can basically just pass in all the input arguments into our predict function when we call it, or we can just call it with command line arguments as well. So this is basically the file here. I just copy pasted the file, and then we went in, created this track.py, and then we have our tracker. I just initialized this tracker. So I have this sort.py. So this sort.py is actually like the exact same code as I've used in one of the other videos where we did optic detection and optic tracking with the YOLOv8 model. So this is basically just a sort algorithm which uses a Kalman filter to track the optics over time. So we both have a predict state and we also have an update state. And then based on new predictions, we can actually like update our estimate and our track of our objects. And then we can basically just track our objects over a number of frames. And then we can actually, like, even though we lose track of our, or like lose detection of our objects, we can still track it because we have knowledge about the past. So let's say that we have an object here that is moving, then we're just tracking that over time, and then we lose information or like we lose detection of it. Then we should actually like still be able to track it over time because we know how it has been moving before that, and then we basically just have our tracker with some good parameters which we're updating based on our measurements, and our measurements are based on our detections, and then we basically just have this update and prediction step, and then we can basically just have this Kalman filter tracking our objects around in the image frame, and we can store information, use that for like tracking cars, tracking different kind of like objects, and also just for when we're doing object detection, just add a tracker on top of it, just to make sure that if we're losing detection, we don't really like lose detection of our actual like detection in our image. So if we lose detection for 1 or 2 frames, because again, if we're running like 100 frames per second, if we just miss like one detection, we will like lose track of our object if we're not using an object tracker on top of our object detection model that we're running. So I won't really go into details with this code. You can check the other video out where I go over how it's implemented, this sorting algorithm. You can also apply the deep sort algorithm. I also have another video where we use the deep sort algorithm. You can just copy paste the deep sort algorithm and the code for that directly into it, as I've done here with the sort algorithm. And then inside the track file, we basically just initialize a tracker and do the exact same thing as we did in the previous videos. So if you want to know like how we can set up these trackers and how we can use them on top of our object detector, definitely make sure to check those videos out. Here we're just going to use it. So I just copy pasted this sort algorithm into our py file, and then we just go up here. So from sort, we just import everything that we have inside of that file, and then we import all the other things here. So all the other things here are basically just copy pasted from the predict file provided by YOLOv8. First of all, we need to initialize our tracker. We just set our tracker equal to, or we just set it as a global variable. We set the max age here equal to 5. So if we lose detection for 5 frames, then we'll like discard our detection. But if we lose, let's say we lose detection for 3 frames when we're actually doing and running our live inference on a webcam, then it will still keep track of the object in our image frame and we won't lose track of it. We can also set minimum hits here. So before we actually initialize our track of an object, we need to detect it 2 times. You can play around with these thresholds here. We also have an intersection over union threshold. So these are the 3 thresholds you will actually need to tune for your specific application and project to set up this tracker. And then we basically just initialize our sort tracker with the max age, the minimum hits, and also the intersection over union threshold. And then we basically just have our tracker here. We can then pass in the detections from our YOLOv8 model through the tracker. We will keep track of the object. We can store the information and then visualize the tracks over time. Here we're just going to create a function for like creating random color list. So we can just have random colors for our tracks and also detections in our image frame. We have these drawer boxes. So basically we just extract the information of our bounding boxes. And then we use OpenCV to draw like rectangles around the objects, so the bounding boxes, and then we also have this put text. We're going to draw a circle at the location of our act-like tracks. So after we have tracked our object, we will basically just store all the information, and then we'll draw dots of all the previous positions our object has been in, and that will basically just be the center of our bounding boxes. So here we just take box of 0, box of 2, divided by 2, so we just get a center of it. So we take the x value and the y value, so this will be the center of our bounding boxes. And this is basically what we're going to draw, so we can track and we can see how we have tracked the objects over time in our image frame. Then we return the image, and then the rest here for our detection predictor is basically like the class from the predict file. But we can also go down here and actually like set up our tracker function. So detections to sort, first of all, we just initialize them as empty. So if we don't have any tracks at all or like any detections at all, we're just going to throw in an empty array because we actually need to pass something into the tracker. But if they're just empty, they will not do anything. Then we basically just go through all the detections. So we have the detections here. They are on the GPU if you're using the GPU. So first of all, we convert it to the CPU. We get the X value, Y value, X2 value, and the Y2. So that will be the top left corner and the bottom right corner of our bounding box. We get the confidence score and also the label of our detected class. Then we basically just set it up in the correct format for our sorting algorithm. So this is the detections that we want to throw inside our sorting algorithm. Then we can call this update state. So again, we have an update state and then we have a predict state, where our predict state is basically just predicting where are we in the frame with our object. And then we have our update state where we get the new detections in, and then we update our previous predictions and our new state based on the new detections. Then we have the tracks. We will just want to get the track. We call our tracker.getTracks. So then we basically just get the results from our tracked object from this get trackers. We have the trackers, we can just have a for loop running through all the tracks. We have the image, and then we basically just display our tracked image. So again, we have the bounding boxes, and then we'll have our tracked positions. We're going to display that on our image so we can see how our objects in the image frame is actually tracked over time. Down here at the bottom, we can just specify like if the length of the track detections is greater than 0, then we're just going to draw the bounding boxes. So we're not just drawing bounding boxes. We only draw the bounding boxes if we're actually like tracking objects around in the image based on the parameters that we set to our tracker at the start. Then we basically just return the log string here, and now the rest of the code is basically just the exact same thing as in the predict.py file. So again, you can use any other algorithm. You'll just need to set it up in the same way as I have here. Or if you want to store the information, write it out to a file displayed on the image in some other way, you can just go in and do that. I basically showed here what code you actually need to modify to be able to do that. So let's now run the file here and see how it actually works. Let's see how we can track objects around in the image frame. So I've just opened up a new terminal and we are now ready to run our program. First of all, I'm just going to call the dir command so we can see what directory we are in. So first of all, we're just going to cd autolytics. Then I basically just copy pasted this command in. So we have our Python. So we're going to run this Python file. We go inside YOLOv8 detect, and then we have this track.py that we just created ourselves. We set the model equal to YOLOv8 and the medium model. So we can actually go in and modify that as well. So here we can choose the large model. So you can basically this is a trade-off between like inference speed and accuracy. And then we basically just have the model twice here. We shouldn't have that. And then we have the source equal to 0 because we're going to use the webcam. And then we set show equal to true. Then it will actually visualize the results as well when we run the program. So now we're ready to run the program. We just hit enter and it will run the command. And then it will run this track.python file. So first of all, it will download the YOLOv8 model if you haven't run the code before. Then it will open up your webcam. We can then see the results here, and then it should be able to track persons over time. So here we see if I'm moving, it actually like tracks me here with a certain color. I'm just going to take my webcam down here, and then let's see if we can track some other objects in the scene. So if I just turn around here, we can actually see this chair. If I move it around, we can see how it moves around in the image frame. If we lose detections, it will actually change the color, but now we can actually see that we keep track of this chair pretty nicely. And again, even though we're occluded by other objects, we still keep track of the object. If I'm moving it around, we can see that now it is in the top right corner of the image. So this is a really nice tracking algorithm. As you can see, we're still able to run in real time. We're running around like 10-15 milliseconds for the inference time, and also running this object detector or like tracker on top of it. We're running at around like 75 frames per second. So this is actually like a really awesome model. Here we can just see me as a person. It detects me as the sender. We can also have the mouse. So if I'm moving the mouse around in the image, basically I'm just moving the camera around. But again, we just keep track of all these points here. So this is basically just the sender of the tracked object or like the detected object, and then we just throw that information into our tracker. So this is just a really crazy tracker and object detector that we can combine, and we can get some really nice results. So you should definitely use this in your own applications and projects when you're going to create your object detectors in the future. This is really cool. You can see the results that we get. I'm going to create other videos where we're going to create our own custom object detector, both for detection and also for instance segmentation. So thank you guys for watching this video here. And again, remember the subscribe button and bell notification under the video. Also like this video if you like the content and you want more in the future. It just will help me and YouTube channel out in a massive way. I'm currently also doing a computer vision tutorial and a deep learning tutorial where we talk about like the basic things about computer vision, deep learning, how to get started with it, learn the basics, the theories, how we can train neural networks from scratch, how does the high parameters affect the neural networks while training. So all these different kind of things is really useful when creating these computer vision and deep learning applications and projects. So if you're interested in one of those tutorials, I'll link to one of them up here, or else I'll see you next week, guys. Bye for now. Hey guys, and welcome to a new video. In this video here, we're going to do a comparison of the new state-of-the-art YOLO-nas model. It has really good performance, as we're going to see. In this video here, we're going to compare it with the other YOLOv8 model. It is still a very good model, and it also has some advantages over YOLO-nas. Still, we're going to cover like all of it throughout this video here. We're going to see how we can actually like use it in code. So we're going to open up the two models with a live webcam stream here in Python. So we're basically just going to create the two Python scripts, open up, use a pre-trained model, and see the inference results directly from the pre-trained models. We're both going to look at the inference speed and also the performance, and then I'm going to talk about some of the benefits, disadvantages, and also advantages of the two models. So I already have a video about YOLO-nas and also YOLOv8 where I cover like everything from training it from scratch, how we can use our own custom data set, go in. We have a Google Colab notebook. We basically just run it through, import a data set, train these models here, and then we're going to export them and use it in our own custom Python scripts. So all I have videos about both of those models. So definitely go in and check those videos out if you're interested in learning how you can actually like go in, train these models on a custom dataset and use them in your own applications and projects. So when I jump into Visual Studio Code, I'm going to show you how easy it is to actually like set up these models. They have some really nice frameworks around the models. We can basically just go in and choose what model and what type of model we want to use. So first of all, here we have this YOLOv8 model. I already have videos about those, but in this video, we're just going to run the two models. We're going to see the results, compare them, and then I'm going to talk about like some of the pros and also some of the cons of using these two models. So just because a new version of the YOLO models come out, it doesn't mean that we can use the previous versions. They're still very good in some specific scenarios and also for data sets and also for different tasks, as we're going to talk about in just a second. But here we can basically just see that from Ultralytics, we can basically just go in and pip install Ultralytics. We can then import the YOLO class here from Ultralytics. We can basically just go in and then create an instance of our class. We can specify what pre-trained model we want to use. Here we're going to use the YOLOv8 small model. You can also take the medium model, large model, extra large model, and so on. But in this video here, we're just going to choose the small one here. We create an instance of a model, and then we can go in and directly call this predict method that Ultralytics has implemented. So we just call predict. We can specify the source. So this can either be like an image, the source of our webcam. So right now I'm just specifying like the second index here because I have multiple cameras connected to my computer. You might have to just like type in a 0 here if you're on a laptop. And then we're going to visualize the results here as well. We're also going to return them, but this is basically like the only thing that we need. We just need to create an instance of a model and call the predict method with our specific source. And then we're actually like doing inference on our images from our webcam directly with these YOLO models. So this is the YOLOv8 model. Let's just go in and take a look at how we can set up the YOLO-nas model. It is also very easy. Right now, again, we just need to go in and pip install super gradients, and then we can go in and import the model from the super gradients library and framework. Now we can go in, take the models here. So we basically just have a method for that. We can call the get method, and we can specify the version of the YOLO model we want to use. So we have YOLO-nas, we have the small, we can also take the medium and large again. Here we're just going to use the small one, but now we need to specify the weights that we want to use as well. So right now we're going to use the pre-trained weights here from the CharuCo dataset. So this is basically just the pre-trained weights as in the case with the YOLOv8 with the old YOLOv8 model in here as well, but here we don't have to specify the actual like weights that we're pre-training our model on. So right down here, we can just go in and specify if we want to use CUDA. We also need to do that with the super gradients with YOLO-nas. We can go in and call model.eval, and then we have another method which is called predict webcam. So this is exactly the same as YOLOv8. Here we just have to like specify a couple of more lines. With the YOLOv8, it actually like goes in and checks for the CUDA itself automatically. So if CUDA is available, it will use that compared to the CPU. So in YOLOv8 here, create an instance, call predict. Here we also need to like create an instance. We need to specify a bit more. And then we also need to like convert or push our model to our GPU if that is available. And then we can also call the predict webcam down at the bottom. So let's now just run these programs. Let's see the results here. Let's take a look at it. I have a webcam here that we're going to use, and then we're basically just going to see the results. So here we can see I have now the webcam up running. We can see that we're running the YOLO-nas model. I'll just take it up here as well. We can see that we're detecting a person, multiple persons here, also a chair. So this is not thresholded in any way or like no post-processing. So we can do like a bunch of other things for that. But here I'm basically just like moving it around. We have a clock here that is an incorrect prediction. Let me just turn it around here. We have a cup, mouse. We also have a mouse over to the right. We should also have like a vase here. That is not a vase. That is a speaker. We have my phone up there. Does it detect that? Nope. We still have like a TV here. We can see the inference speed here is around 15 frames per second. So I'm not really sure what these models here. So I've been playing a bit around with it. I've been using like both CUDA, my MacBook with MPS and also the CPU. But it still seems that these models here, they run a bit slower. Right now, I'm just like running it with their predict on webcam method. So we could actually like go in and export the model ourselves, try to write our own custom like inference script. So that might actually like speed up the process a bit more, because then we don't have to do like a lot of additional processing. We can basically just like import a model as we do in any other model. and then try to like create our own custom script. So we're definitely going to do that because I feel it's a bit odd that we only get like 21 frames per second here, or like around 20 frames per second, depending on like how many detections we get in the frame, because they actually like state that they are faster than the YOLOv8 model, and that is not the case in these situations here, as I'm going to show you with the YOLOv8 model in just a second. So here we have like around 20 frames per second. So let's just close this one here. We can just hit Q on the keyboard and it will terminate. Let's now go ahead and run the YOLOv8 one, and then we can see how fast that one runs. So I feel it's a bit odd that we actually get so low inference speed on the YOLO-nas model. Here we can see the YOLOv8 model. We get around like 8 to 10 milliseconds here in the inference speed, which is the same as around 100 to 120 frames per second. So this is actually like way faster. And you can even see it when I'm moving the camera around. It is just way faster compared to the YOLO-nas model. So I'll definitely have to do a bit more research on that, try to create my own custom script and try to see if I can actually like improve the inference speed. Because again, they state that they're better both like performance wise, but also significantly like faster in inference speed. So here I'm just going to move it around. We can see that we still detect the different kind of like objects. We have the cup, mouse. We don't really get the mouse over here in the background. You can see my mouse over here. We don't really detect that as good as the YOLO-nas model. So I think the predictions are better with the YOLO-nas model, but again, the inference speed, I didn't really like that. I'll definitely have to play around with that more. So it's a really cool model. It just doesn't run as fast as I would expect. So I'll definitely have to play around with that. Because then it is just such a cool model. Again, I'm running this on my 4090 GPU from NVIDIA, so this is actually like a pretty good GPU, and we would expect like crazy high frames per second, as we also get here with the YOLO-8 model. So I'm just going to put the webcam down here again, and then we're going to talk about like some of the pros, cons, advantages. When should you use YOLOv8 versus YOLO-nas? So it actually like depends on your application. Again, just because we get a new version of the YOLO models, it doesn't really mean that we can't use the previous ones. We can still even use the YOLOv8 one. So these models here, they're trained and they're benchmarked on like large data sets like the CharuCo dataset and also some other benchmark data sets, and they only have like a slight improvement over the other models. So it really depends on your data set and application. So you should definitely test out the other models. Don't just go for YOLO-nas or like YOLOv8 because they're just the nearest models. You should definitely like test out different ones. So we also have some other advantages with the YOLOv8 model still. Again, here we can run it easier, we can run it with fewer lines of code, and it also runs significantly faster than the YOLO-nas model. I'll definitely check that out. I'll try to optimize the YOLO-nas model and also get it to run in our own custom scripts, and then also to talk about these advantages and disadvantages in different situations. So again, the YOLO-8 model is still really, really good because it has both object detection, it is fast, it is easy to use, and it also has segmentation, which we're using in a lot of applications and projects. So thank you guys for watching this video here, and again, remember to hit the subscribe button and bell notification under the video. Also like this video here if you like the content and you want more in the future. I also have some courses here on my channel where we go over the YOLOv8 model for object tracking. So we're actually like implementing trackers from scratch. I go over the theory behind all the trackers. So that is actually like a really interesting course where we go all the way from the theory, how we can use these YOLOv8 models, and also how can we apply trackers on top of the YOLOv8 models. I also have some other courses with OpenCV with GPU support, so how can we utilize the GPU in computer vision applications, and also YOLOv8 custom object detection courses for different like types of inference, like how can we deploy them in our own custom Python scripts. So there's a lot of things going on. It is really interesting. I just hope to see you guys in the next video. Bye for now. Hey guys, and welcome to a new video. In this video here, we're going to talk about YOLOv8. We're going to take a look at how we can extract the information. I'm going to show you how we can create our own class with the YOLOv8 model. So they will actually be pretty easy to work with. In the previous videos, we've just been taking a look at how can we use the YOLOv8 model and how can we use like the framework and the code structure behind the YOLOv8 model. In this video here, we're basically just going to take the YOLOv8 model, implement it in our own class in Python, so we can use it in our own Python scripts, projects, applications, and so on. So I'm going to show you how we can load in the model, extract all the information so we can use it in our own applications and projects. We can save the information, display the information ourselves, or do whatever we want to do with the detections from the YOLOv8 model. So we're now jump straight into Visual Studio Code. I'm going to show you how we can actually like import and load in YOLOv8 models from the new YOLOv8 repository from Ultralytics. I'm also going to show you how we can use RoboFlow supervision to actually like display our detections with all the labels, confidence scores, classes, and so on. Then I'll also show you how we can extract information for our own applications and projects, where we can basically just extract all the bounding boxes, all the coordinates for our bounding boxes, the confidence scores, the classes, and so on. So we can basically just store that in our own list. We can use for whatever we want. If we want to write it out to a file, draw our own detections on the frames that we're loading in from our camera, and all those different kind of things. Or if you just want to like trigger some different kind of like systems based on the detections that you're doing with the YOLOv8 model. So first of all, here we're going to import the different modules. So we're going to use PyTorch. I have it working with my GPU. We also have NumPy, CV2, so we're going to visualize the things with CV2. We're also going to open up our webcam and video capture with OpenCV. Then we also have Ultralytics here. I'll also just import time so we can time how long it takes to actually like run inference. So we're going to be able to run in real time, depending on the model that we're using. We also import Ultralytics here. So from Ultralytics, we just import the YOLO model. So I'm going to show how we can use this to actually like load in our models. We can both use pre-trained models, but we can also have our custom trained models. I have videos about all of those different kind of things. So if you want to know how we can train your own YOLOv8 model, export them, download them into your own computer, and then you can actually like just upload them and actually like load them as I'm going to do in this video. So if you're interested in that, definitely check those videos out. I'm covering like all of it. I'm also having trackers and all those different kind of things. Then we also need this supervision. So you can basically just pip install supervision in the command prompt or in the terminal. And then we're just going to use from supervision here, we're just going to use some tools for actually like visualizing the detections and so on. I'm also going to extract all the information so we can visualize it ourselves, but this is just to show you an easy way to actually like get the visualization up and running, and then you can basically just extract information, do whatever you want with the actual like information after that. So first of all here, we're going to create this object detection class. So we basically just have a class. We initialize it with some different kind of like parameters. We load in the model, and then we also have some methods for actually like loading in the model, displaying the different kind of things that we want. So I'm basically just going to go over it, but we just create our object detection class. We have our init method here. So this is basically a function that will be called when we initialize an instance of our object detection class. So first of all, we need to pass in the capture index. This also works with videos. So if you have videos, you can basically just specify the path to that. But right now, I just have my capture index. I just set self.captureIndex equal to the capture index. So this will be the index of my camera attached to my computer. Then we set up the device. So if CUDA is available with PyTorch, we basically just use CUDA and the GPU, so we can run way faster when we do inference. And if it's not available, you can just use the CPU, or it will just use the CPU as default. Then we just print out what device we are using. Then we're going to have a function here called load model, and I'll basically just go down to that right now. So we have this load model function. All it does is basically just taking this YOLO class that we imported from Ultralytics, as we've been doing in all the other YOLOv8 videos. We specified the model that we want to actually use. So if you don't have these models on your computer, so if I go over to the tab here, I actually have these YOLOv8 medium, nano, small, and extra large model. But let's say you don't have the models yet, it will actually download it from the internet beforehand. So it will download the models, it will download all the weights, and then it will basically just create this model instance. Then we can fuse it, so we get the information about the model, and then we just return the model so we can use it later on for inference. So again, you can just specify, like if you have a custom trained model, as from my other videos, you can basically just specify the path to the model here. It will load in that custom model, and then you can run inference as I'm going to show you now. Then we just have some class names, a dictionary for all the class names that we have. So we have these CharuCo classes from the pre-trained models. You can also like create your own. So you'll basically just go inside the model and then take the names from the model that you have trained. If you want to do custom object detection and all those different kind of things, you can also use a pre-trained model and just go in and specify what type of class are you interested in. Then we're going to set up our box annotator, which is basically just an annotator for drawing bounding boxes around our detections. So this is what we're going to use this supervision for. I'm also going to show you how you can do it yourself. But basically, we just create an instance of this box annotator class. We set up the color palette here for the colors. So we just have different colors for the classes. Then we can just set up the thickness, the text thickness, and also the text scale. So these are just some of the parameters for the visualization. We already went over how to load the model. Now we can go down to the predict function. So again, this class here is actually like pretty simple. We just have a function for loading in the model. We just have a class for actually like having some kind of like structure that we can use. And then we have a predict function. And then we basically just have a display or plot bounding boxes function inside of this class. So this is a really easy way to use these YOLOv8 model and extract all the information. But basically in this predict function, we take in a frame and then we just pass the frame into a model. We do a forward pass in our YOLOv8 model, and then we just get the results out, we return the results, and then we can use that later on. So the last method inside of our class before we're actually going to go down into the call method, and then I can show you how we can have the while loop. We open up our webcam, our video capture, we read in the frames from our camera, and then we can basically just pass our frames through this model and this class that we just created. Then we basically have this plot bounding boxes. We throw in the results and also the frame that we want to visualize the results on. First of all, we just create these empty lists here. So these are the lists that will contain all the information that we're going to extract from the YOLOv8 model and the detections from the YOLOv8 model. So these lists here are the ones that you can use for your own projects when you have actually like extracted information. So let's say that you want to detect like persons, then all the person coordinates for the bounding boxes will be stored in this one. Also the corresponding confidence scores and the class IDs. So this is actually like how you would use the YOLOv8 model and extract information instead of just using like the code structure from Autolytics or some other different kind of like frameworks where they basically do like all the plotting for you. You can't really extract information, play around with it, use it in your own applications and projects. So that is what I'm going to show you guys in this video. So now we're going to extract the detection for a person class. So if you just want to like detect all the different kind of like classes that we have for the pre-trained models or for your own custom model, you will not have this if statement down here. You can basically just go inside into Google, search for like CharuCo class IDs, or you can basically just see what IDs does it return if you just print it out while you're doing inference. Then we basically just have class ID 0 here, which is a person. So if we're detecting a person in the frame, we're basically just going to append the bounding boxes. So the bounding boxes XY, XY for the top left corner and the bottom right corner. First of all, we're going to put it on the CPU and convert it to NumPy. So we're going to do that with all, with both the bounding boxes, the confidence scores, and the class IDs. So basically, we just returned these results. So these are the results that is returned by the predict method when we actually just throw the frame through the model. Then inside our results, we will have this boxes class. So we basically just go inside our boxes, and then we have a number of different attributes for our boxes class. We can extract the XY coordinates, the confidence scores, and also the classes. So this is the way you would do it. Again, here we just have a for loop running through all the detections that we have in our image. First of all, we just extract the class IDs, and if the class ID is equal to 0, we're detecting a person. We just want to store all that information. So this is one way you can actually just go in and extract the specific classes that you want to detect with your model if you're using a pre-trained one. If you're using a custom model that you're trained on your own dataset, you will of course you want to extract all the classes that we're detecting in the frame, and then you will basically just delete this if statement here and just append all the results to the lists. And then you can do whatever you want to these lists here. If you want to display the results, if you want to write them out to a file, make some other logic on top of that to actually do something in the real world. So let's say if we detect a person, do something. So now I've showed you how we can extract information from the results and the output from the YOLOv8 model. Then I'm just going to show you how we can actually set up the detections for visualization with the supervision framework from RoboFlow. So basically we just set up these detections or this detections class from supervision. We specified XY, XY, the confidence score, and also the class IDs. So we basically just extracted exactly in the same way as up here when we extracted information. Now we're just going to create this instance of our detections class. Then we have these detections over here to the left. We can just go through all the custom labels. So we basically just have a for loop running through all the detections, and then we get the individual class IDs and the confidence scores for all the detections. So we get all the corresponding bounding boxes, class IDs, and confidence scores, and then we basically just store it in this self.labels, because then we're going to use this to actually visualize our results. So we get all the bounding boxes, all the correct bounding boxes with the corresponding labels and confidence scores. So now we can go down and do the annotate and display the frame. So from this box annotator, so basically up at the top here, we created this box annotator instance. So now we're going to use that and we're going to call the annotate method on that instance. We throw in the frame that we want to do detections on, or like we want to display our results on. We throw in the detections we have and also the labels for the corresponding detections. This is basically everything we have to do to actually visualize the results with supervision. Again, you can we have extracted all information in these 3 lists. So you would actually be able to go in, like run a for loop, just displaying all these results here yourself with the rectangle, put text, and all those methods from OpenCV, as we've been doing in some other videos here on the channel. But again, I just wanted to show you guys how we can extract information from the YOLOv8 model. And for the easy part, we're just going to display them with supervision. Then when we have annotated and displayed the frame, so we're basically just visualizing the results on the frame, then we just return the frame and then we can show it with our imshow function from OpenCV. So now we have our call methods. This is basically like our main function that will run as long as the webcam is open and we don't terminate our program. So first of all, we're going to open up our video capture. So this is the exact same while loop as in all the other videos I have on the channel. So we open up our video capture. We just assert that our camera is actually open. Then we're going to set the frame width and the frame height, so the resolution of our camera, to 1280 by 720. We have a while loop, so while true here, we can also have while cap is open, but up here we just asserted that it is act like open. So we're just starting our timer. We read in a frame. Then we basically just call our predict function. We throw in the frame, we get the result out from our model. Then we have the results stored in this variable. We can throw it into our plot boxes function here. We throw in the results and we also throw in the frame that we want to visualize the results on. We end the timer, calculate the number of frames per second, and just display the number of frames per second as well on our frame, so we can see how fast can we actually run inference with this YOLOv8 model while we're extracting all the information and doing the visualization. Then when everything is done, we're just using imshow here. This is not YOLOv8, but this is YOLOv8. Then we just have the YOLOv8 detection and we throw in the frame, and then we're just visualizing the results that we get. If we hit Q or like escape on a keyboard at any time of the program in the window, it will basically just terminate. It will go out of this while loop. We will break out of the while loop. We release our webcam and we will destroy all the windows that we have opened up with OpenCV. So now we have the whole class here. I basically just showed you the whole class. First of all, we have some initialization we need to do. We have load model, predict, plot bounding boxes. That is the whole class that we need to use. And then it is really easy to use this YOLOv8 model in your own applications and so on. You can basically just have a file where we import this class, and then you can directly use it. You can like return these values here as well. You can basically just call a single function, return these values, and then you can play around with it in your own project and applications and fit it to your own needs. So now we have everything inside of our class. We can basically just go down and call an instance of our object detection class. We specify the capture index, we set that equal to 0, and then we just call the detector method, so our call method that I showed you here. So now everything is up running. We have the code. This is actually like really easy. We just have a class with around like 100 lines of code. You don't need to do anything. You can just directly use this. This will be on my GitHub. A link will be down in the description. You can just go in, copy paste it, use it in your own applications and projects. So now our program is running. We can see that we have opened up the model at the bottom. We're using the medium model right now, and we have fused it, where you can see the number of layers, the number of parameters, giga floating point operations per second. We're using Ultralytics version 8. We can see the Python distribution, the CUDA version, Torch version, and so on. So we can see that I'm actually using CUDA. So I'm using an NVIDIA RTX 4090 graphics card, so that is rather fast. But if I just take the webcam up here, we should be able to get some results. As we can see, we have a person. We kind of have a bicycle here, but this is not a bicycle. This is my microphone. But again, we can basically just take it up. We're detecting a person. I can try to like move the camera around. So here we have a dog in the dog bed, and we also have a chair. Also have a potted plant over here to the right. So here we have a chair, a potted plant. So these are actually some really nice detections. We can see that right now it actually like detects me as a person up here at the top. If I just take the camera up here, we can see we have a bookie in the background. But again, these wrong predictions, they have really low confidence scores, so it doesn't really matter like that much. We can basically just filter them out by looking at the confidence scores. We have a keyboard. We also have a mouse. Here we're detecting a TV, which is my computer. I have a laptop here for my monitors. So this is actually like pretty nice detections. Like the false positives we get, we can basically just filter those out by setting up a confidence score. We will just have an if statement checking on the confidence score as well before we are storing the values. So if I just hit Q here or escape here on my keyboard, it will terminate the program. And then I'm just going to verify that it actually like works with the different lists that we have extracted our information into. So basically here, I'm just going to print it. So we run through all our detections, and then I'm just going to print the XYZ. So we have the XYs, and then we're just going to print it. We can see the results down here in the terminal. So I'm just going to run the program. Then we can actually just verify that it works and that we're actually like extracting the information for a person. So right now we're not detecting any person. So right now we do. If I just take it over here, we don't get any information extracted into these lists. So they are just empty. We will only get information if we're detecting a person. So if I take it up here again, we can see that now we're detecting a person. We get all the bounding box values. So we have the top left corner and the bottom right corner. So that is what we can see here. And then if you have multiple persons, you would basically just have arrays inside of arrays. You can extract information, do whatever you want with it in your own applications and projects. So this acts like really nice. So that's it for this video. I've shown you how to create a class. We load in a model. We extract the results from our YOLOv8 model, display the results, how we can actually play around with the results in our own application and project. So thank you guys for watching this video here. And again, remember to subscribe button and bell notification onto the video. Also like this video here if you like the content and you want more in the future. It just really helps me and YouTube channel out in a massive way. I'm doing these computer vision tutorials where we go over like all the basic image operation techniques, algorithms, stereo vision, how we can like get depth information in our images, combine them with deep learning and all those different kind of things. So if you're interested in that tutorial, I'll link to it up here, or else I'll see you next video, guys. Bye for now. So in this video here, I'm going to show you how we can train a custom YOLOv8 model. This is a new one, YOLOv8.1, where we can actually go in and do oriented bounding boxes. So in the previous videos, I showed you guys how we can set it up. I basically went through the documentation and so on. We used the code snippet from the Autolytics documentation. But in this video here, we're going to grab a custom dataset. We're going to have some cups. You guys are probably familiar with that dataset that I've created myself. But we're going to use that dataset. I'm going to show you how we can use RoboFlow for that, how we can annotate our images, and also how we can export it. So right now we can just export directly. So I created custom scripts that can go in and format the annotations to the correct format with the new YOLOv8.1 model for our bounding box. So let's just jump straight into it. We're going to cover how we can annotate the images, export them, convert them to the correct format, how we can train our own custom model, and then we're going to run inference on a video stream to see the results of oriented bounding boxes. So we're going to jump straight into RoboFlow. This is the platform that we're going to use to annotate our images. I already have an annotated dataset. You can go and use that directly, or you can go and use your own custom datasets. I'm basically just going to show you the whole flow here. First of all, we can go in and see the results. So these are like some of the test set. I'm just going to zoom out a bit and run another example. So you can basically just see that I've tried to train a model here on RoboFlow. But basically you can go and create a new project on RoboFlow, upload your images, and then you can go in and do annotation. There's one trick here with RoboFlow to be able to do oriented bounding boxes if you go inside projects. So when we want to create oriented bounding boxes with YOLOv8 for now, this is how we can do it. So we actually need to go in and choose instance segmentation instead of object detection, because for object detection with RoboFlow right now, they don't support oriented bounding boxes. If you're using an annotation tool that already supports oriented bounding boxes, you can just use that. But here we actually need to do instance segmentation and then export it in another format to be able to use RoboFlow. So that's just one of the things right now. I'm definitely sure that RoboFlow is going to change this over time. So right now we can just choose instance segmentation, then you set up the project name, what you're going to detect and so on, but I have already done that. So I have this cup segmentation data set. We can go in and take a look at some of the images. So I basically just went inside the images. Once you have uploaded your data set to RoboFlow, you will get inside this annotation tool. You can choose new classes. You can go in and annotate the images. But to be able to do this with oriented bounding boxes, we need this polygon tool. And then you can just draw these masks here around your object that you want to do object detection of with the new YOLOv8.1 for oriented bounding boxes. We know the traditional bounding boxes here is just like a rectangle or like a square, which is fixed. So it's not like rotating with the object. So let's say that we want to have our cup here. Then let's go up and take an example. So right now I'll draw a bounding box around the cup like this. But in reality, if we actually want the best detections possible, then we should probably like have our bounding box in this example here rotated a bit to the left, so we're fitting the object better, and that is really useful in a lot of different applications and projects. So let's just go back here again and delete this annotation, but this is the tool that you can use, and it's really easy to work with, and we can also see in just a second how we can export the data set. So yeah, then you'll just go in and label the images. You're going to use the polygon tool, so you'll just draw like a polygon around your object. So right now I've just done that for all the images, so you just go around it like this, around the edges. Once you have labeled your whole data set, you're ready to go. Let's go back here again. We have different versions. We can also go in and generate a new data set. So with RoboFlow, we can go in and do pre-processing. We can specify the size of our image that we want to use. So right now we're just going to use 640 by 640. Auto orientation, we can also go in and do other pre-processing options, but don't play around too much with that. Just using raw images is often the best one to do. We can also apply augmentation steps here. So again, if you only have like a few examples, you have like 50 images or so, you can go and apply data augmentation on top of your data set, basically just to generate more data that varies a bit from sample to sample. So we can do flip, horizontal, vertical flip, zoom in, like we can crop out an image if we want to have like some zooming effect, and this just helps our model generalize better. We can also apply augmentation or like rotation and a lot of other options in here. So I've just chosen these three here. That is normally what I use. We can hit continue, and then we can create a new project specifying if you want to like 3x, 4x, 5x, 2x our data set. So right now we have just like 5x, I think, but I've already generated a couple of versions here. So if we just go inside the versions, this is the model that I showed you in the start. We can try it out directly with RoboFlow. But once we have labeled our data set, we can go inside our versions. Again, this is still instant segmentation, as you guys are familiar with, but we're trying to do object detection with oriented bounding boxes. But this is just how we will have to do it with RoboFlow for now. You can use whatever other like annotation labeling tool out there. If they support bounding boxes like oriented bounding boxes, you can probably export it directly in that format. Maybe you'll need to do some conversions because YOLOv8 is using a specific format and their own format for actually like training these models. So right now, let's go ahead and export our data set. We can select the format that we want to choose. So previously, if you're just doing standard object detection, YOLOv5, YOLOv7, YOLOv8. But now we actually need to go up and choose this YOLOv8 oriented bounding boxes. And this is not really the format that we can use directly. I'm going to create a custom formatting script that takes this output here from text files and convert it into the specific one that they're using from Ultralytics. You can either download a zip folder to your computer or show the downloadable code that we can copy paste directly into our Google Colab notebook. So this is what you'll get. You'll also need to do this to actually get the API key for your RoboFlow account. You can also use the terminal or raw URL, but we just copy this and throw it directly into our Google Colab notebook. And we can export our dataset, run our training script, export our model, and use our own custom Python scripts for our own applications and projects. So we'll just jump straight into the Google Colab notebook and walk you guys through that. So first of all, make sure that you actually connect to your GPU. You can go up to the runtime, change runtime type, and then you can specify if you want to use a GPU here. We want to do that when we're training these deep learning and machine learning models. So let's just run this NVIDIA SMI here to start with, just to get some information about our graphics card, the GPU that we're using, and also just to make sure that we're actually utilizing the GPU for training. So here we see that we have the Tesla T4. We can see the number of gigabytes that we have in our GPU RAM and all of this information here. So that is always pretty useful to do. Then we're going to import our OS here just to set up a home directory that we can use later on, because we're going to do a lot of with our directories and so on, because we need to do the mapping and the conversion formatting of our data set. Then we're going to install YOLOv8. So we're just going to pip install Ultralytics. It's going to download the newest version, and that is pretty much everything that we need to install. It will take care of all of it. Then we just need some additional ones here for displaying our images after it's done training and so on. And we also need to be able to import YOLO as the architecture. So let's now just start the installation. Then we're going to import these different modules and dependencies that we need later on. Ultralytics, they have some different like CLI basics that you can go and use as well. So we can just call this YOLO command, and then there's different tasks. So we have detect, classify, segment, but now we also have oriented bounding boxes, train, predict, validation, export. We're going to use these different modes throughout the notebook, and you can also specify the model. Instead of specifying, for example, like seg now, we can just go in and specify OBB, and that is also how you can go in and use pre-trained models already for that and do inference on videos, YouTube videos, webcam streams, images, and so on. I already have a video about that, so definitely check that out. But we're also going to do it later in this video here, so definitely stay tuned for that. We're going to run it on a live video stream. So now we have the setup complete here, as we can see. Now we can go down and set up our custom dataset. So first of all here, we need to make a directory for our dataset. We need cd into it. So this is how we can call command lines from the Ubuntu terminal. From RoboFlow, we're going to import RoboFlow, and this is just a code snippet that I've copy pasted from RoboFlow. So right now I'm not showing my API key, but I'm just going to copy paste that in. I'm going to run this program here, or like this block of code, and then we're going to see the directory over here to the left and see the file structure. So here we can see that it's downloading RoboFlow, setting that up, and also exporting our dataset, and that should be done in just a second. So right now it's just setting up some OpenCV stuff. Let's join the C, loading RoboFlow workspace, loading the project, and then it's zipping this dataset here to our environment here in Google Colab Notebook. So let's go inside our directory. We have the dataset that we created, COP segmentation 2, and then we can see we have our test, train, and validation split. We also have the data YAML file down here, as we also need. If we go inside each of these individual folders, we have all the images, so all the images, raw images, and then we have our annotations in this YOLOv8 oriented bounding box format. So start with here, I'm just going to rename these folders. So we're going to call it images and labels. I'd like to just do that. Labels, and we also need to do it for our validation. Okay, so now we have our images and we also have our labels. If we just go inside and see one of the examples, we can see it over here to the left. So right now, this is the format that they're using when we're exporting it from RoboFlow, and now we need to convert it to the correct format from Ultralytics that they're using to train the YOLOv8 model on. So we have our X1, Y1, X2, Y02, and so on, all the way up to X4 and Y4. So this is basically the corners of our oriented bounding box. And then they also have the label. This is not the correct format for training this Ultralytics model. So if you just go inside the documentation now for oriented bounding boxes, this is all the documentation that you're going to go through. They have some examples that list the different models. They have nano, small, medium, large, and extra large model, how you can train it. So this is what we're going to use in just a second. But here we have the dataset format, which is really important. So OBB dataset format can be found in detail in the dataset guide. So let's try to go inside that one. Oriented bounding boxes, datasets overview. So this is the supported OBB dataset format, the YOLO OBB format. So here we have class index, where before we had class label, and this is not the correct order. And then we basically just have all the corners of our bounding boxes. But YOLOv8 here also uses normalized coordinates to the image dimensions. So we also need to take care of that. And I've just created like a script here, or like a block of code where we can do all of that conversion. So here you can see the different kind of like representations that we can use as well. So this is how ideally it should look afterwards to be able to train these models. So this YOLOv8 here is the dataset that they have pre-trained their models on, and they also have a script for converting it from the Dota dataset to the YOLO oriented bounding box format. So this is a custom format from Ultralytics, so we need to create our own script that can convert and format our files. Even though you're using another annotation or labeling tool, you most likely need to go in and export it and write your own custom scripts to go in and do this formatting of your data. Again, if you're using the Dota format, you can just go in and call this function directly. But yeah, we're going to write a custom script that can actually go in and create this format instead of the one that I just showed you in a second before. So here we see we have this format. Let's just close that and let's go down and take a look at the script that we have done. So first of all here, we can't really have any spaces. So let's make sure that we don't have any spaces in our data. So right now I'm just going to go inside our labels. So again, we saw in here with our labels, we actually have this dash here. So we need to make sure that we have that throughout the whole data and also in our YAML file. Just close this. We have our data.yaml. So here we actually need to add this dash. So let's do that to start with. And again, you guys can follow this through exactly step for step, and this is how you can train the models. Then I also like to go in and just take all of these paths individually. So let's copy this path here, train, validation, and test, because sometimes it doesn't know that it's inside like content in a Google Colab notebook. So here we have our train. We have our validation, so that will be valid. And then we have our test images here as well. So this is basically just a data set, or like the data file that specifies like the config for our training. So now we have that, we can close that. We have all the labels, we have the images. So right now I'm going to create this block of code that is going to do the conversion. It doesn't really do too much. It's just taking the class names. You can take that directly from the data YAML file that you got from RoboFlow. Just make sure that you actually add these dashes. So that's all you have to do there. Then we specify the image width and also the image height of our images, because we're going to normalize all the values to be able to train our models, or else it won't work. Then we can specify the folder path. So again, you can also just create a for loop running through all of these folders, but right now I'm just going to do it individually for all the 3 splits. We also need our class indices, because again, we have individual like labels, so we don't have the labels. We actually need class indexes. So that's how we can go in and create a dictionary with our class name, so we can map that to specific values, which is the format that we need to use for Ultralytics and YOLOv8 for oriented bounding boxes. So we specify the folder path here, content datasets, cop segmentation 2, valid, and the labels. So we only have to actually convert the labels, the images, or just raw images. We don't have to do anything with that. We have a function for normalizing the values. You basically just take the coordinate and the image value, or like the coordinate, the bounding box values, then you divide it by the maximum values, which will be the image height. Then we can go in and create a for loop here, basically just running through all the different files in our directory and in the folder that we have specified up here. Then we're going to take all the text files. We're going to take the specific file path. Then we're just going to open up that file, read in all the lines. Then for all of the lines, we're just going to have a for loop running through all the lines. So if you just go inside our labels again, we just want to extract each of these individual lines and have a for loop running through each of them, doing the conversion and also just saving them again into a new text file in the correct format. So that's pretty much everything that it's doing. So if length part is equal to 10, which means that we have a correct and a valid annotation in our labels. Then we're going to extract the labels, which will be the second last element. We have the coordinates, which will be the first 8 elements. And then we're going to do this mapping from our dictionary, from the class labels to class index. We then check the class index. If that is valid, we go down and normalize our coordinates. Then we can create a new line here, which is just taking the class index. So this is the first index, or like the first value that we want in our YOLOv8 oriented bounding box format. And then we're basically just going to join all the different normalized coordinates together. So we have our x1, y1, all the way up to x4, y4. We're just going to join all of that together with spaces in between. Then we can append this to the new lines list that we have up here. Then we can open up a new file and just write out each of these individual lines that we have just extracted and converted, and then we have everything. So let's now just try to run this. Let's start with our validation. So that is our test setup here. Let's just run this block of code and we should be able to do it. It did run. Let's go down and check our validation. If we go inside our labels, let's take the first one here. So now we have our class index, and then we have all the values here for our bounding, or in the bounding box right after that. So this is the correct format, and now we can actually go in and train our model. But first of all, we need to make sure that we actually do it on each of these folders. So we have a test, and then we also need to train. Again, you guys can just like create a for loop running through all of this, but again, this took like around 2 seconds to do that. It will take me 5 seconds to create a for loop. So I'm trying to optimize my time. So yeah, let's go and check the other ones here. Let's just take train. We did that at the last one, the label in the correct format. So now we have everything. We have our whole data set. We have annotated our data set, exported it, done the formatting, and now we can just go in and train it directly with the commands from Ultralytics. So let's now close this one. Now we can go inside custom training. We have our task OBB for our in the bounding boxes. We set it into train mode. We can specify what type of model we want to use. Again, they have these 5 different models depending on the size that you want to use. Set the data, dataset.location, and then we need to specify our data.yaml file, which is just mapping to the directories with our images and also our labels. And that's also why I called the other folders for labels, because it's going to extract that. We can specify the number of epochs, the image size that we have exported our data set into, and then we can also specify the batch size. So just change the batch size here to 8 because we have 640 images. So we should be good with that. Now we can just run this block of code and it will start the training. It's going to set up the whole model, going to download the model, start the training loop, and so on. And then we can follow the metrics and follow the progress throughout all of the epochs here. So here we can see that it has loaded in 330 images for training, validation, 19 images, 0 corrupt labels. So it is actually able to go in and extract all the information correctly. So that just verifies that all of our annotations, all of our formatting and so on to the correct format is actually done correct, or you'll get like a ton of warnings here. So definitely make sure that you check that. If it looks like this, you're good to go and your model will start trained. We can even see here, like after the first iteration or like the first epoch, we have a mean error precision 0.50 of 0.583. So that is already like pretty good. But again, we're training on cops, and that is already in most of the pre-trained models and a relatively easy task to do. But now we already have like a mean average position of close to 1, so that is the ideal value. So we can see that already here after like the second epoch, we already have like a model of 0.98 in the mean average position 0.5, so that is close to 1, which is the ideal value. And we can also see the mean average position 0.5 to 0.95 in intervals of 0.05. So it looks pretty good. Our model is already like pretty much converged, so it doesn't really matter like too much to train for longer. Maybe our class loss is decreasing, as we can see here. So yeah, it kind of like makes sense to do that until our class loss act like decreases. So let's just let it run here, and then we can take a look at the results afterwards. So our model is now done training. We can see the validation results down here at the bottom. We can see the number of images that we have in our validation set. We can see the inference time and so on, and we can also go in and see all the different metrics. So again, this looks very good. Our model has basically converged and is very accurate at predicting these cups that we have in our data set. So let's now go over here to the left. Then we have our runs directory now, OBB, train. We have the weights. We can go and extract the best weights here. Let's go in and download that so we can use it in our own custom script. We can also take our last model, but in this example here, they're probably like both pretty similar. We can then go over and extract both our precision recall curve, F1 curve, confusion matrix, and so on. We can also see the number of labels, results, but we can also just go in and use these lines directly. So then we can go in and take the different images here, both our results, our validation batch, and so on. So this is how we can see our model is decreasing over time. So we're taking a look at the class loss that's decreasing, pretty much converged at the end. We can see the metrics for our precision, it's going up, our recall is going up. So our precision recall curve is very nice. Class loss is going down for our validation set, and also the mean average precision is going up. So we have a really good model, it has precision close to 1 and also a recall close to 1, so we probably can't get a better model for this. We can take a look at a validation batch here for our predictions, and this is basically the RN bounding boxes that we get for our cups. So now we can actually see it fits these bounding boxes, it rotates and orients these bounding boxes around our optics now, compared to just our traditional bounding boxes that we know. So this is very awesome, very useful in different applications. Let's say that you have like cars from aerial images driving around. Now we can actually like follow the cars better around. We can get these fitted bounding boxes. So this is kind of like segmentation, but fitting our bounding box around it. Very easier to label and so on. If we have like an annotation tool that can do RNN bounding boxes directly compared to setting up instance segmentation and so on. But this is the validation results, look very good. Again, like 100% accuracy here, 70% confidence score, 90% confidence score. So here we can see all the different labels, white cup, Halloween cup, hand painted cup, and so on. And this is the cup that we're going to use now. So now go down and validate custom model. We can just directly run that. We're just going to change our validation. So I have to stop this because our task is actually like OBB. So task is OBB, do validation, and then we just need to specify the directory for our best trained weights. So it's going to run that and use this model for validation. And we can do the exact same thing with our predict. We just specify the mode, set that equal to predict, and we need to change this to OBB as well. Train 1, because we only have one train run. Confidence score, where we want to have the images from, the source, and if we want to save them as well into a directory so we can take a look at it. But again, this is just the exact same thing that we get after training, so it's running validation after the training. Then we can do inference with our custom model. Right now, we're just going to run through all of our test images, so we can go in and visualize all of that. Then I'm just going to have this for loop running through all the predictions so we can visualize the results. I usually like to do that before we export the model and using our own custom scripts, because just to make sure that our model actually like generalizes, we get good enough predictions, or we want to iterate back, fine tune our data set, retrain our models, test and tune some different parameters before actually like going in and using it in our own applications and projects. So now we have that, we can go in and run this directly. So this will be all the images that we're just running through. Let me just zoom out. So now we can see that we have these RNA bounding boxes, look very good. We're basically detecting every single cup out there. So here we can see that because we're actually like annotating the handle as well, it's just trying to do the segmentation mask and fit the bounding box around it. So that's why we get some weird bounding boxes in this example. But again, you can use your own data sets, whatever data set that you want to use out there if you're with your labels. So here we actually like get a double label here, both hand painted cup and also like a white cup. So that's a bit odd. But we can see that is fairly like pretty good in general across all our chest images. So we downloaded the model, we took the best weights, I have then imported it into my new directory here for a custom project that we're going to set up. So this is all the code that we need to do from Autolytics. We're going to import YOLO, we can create an instance of our YOLO model. Then I've just renamed my best model here to cup YOLO-9 for oriented bounding boxes. And this is how you can use a custom model. You can also go in and specify the YOLO model for the pretrained models, use that directly, but I have videos about that here on the channel. So you only need these 3 lines of code. Import YOLO, set up an instance of a model, and then run predictions. We can either like throw in a YouTube URL here, URL to like whatever image on the internet, video, webcam stream, non-binary, PLL image, and so on. We have a number of different parameters that you, and also arguments that you can find on the Ultralytics documentation. But right now I'm just going to show the results and also save the results for later use. So everything that we need is this file here. We need our custom trained model, and then we also need a video that we're just going to throw it through. So this is the video that I've just created. This is not the exact same background and so on that I've trained the dataset on. The camera is also probably like a bit closer compared to the dataset, but the model still generalizes pretty well. So this is the image and this is the video that we're basically just going to throw through the model. Let's just do it. Let's open up a terminal, run the program, and see the results. So let's open a terminal, new terminal. I'm going to open a command prompt, conda activate, Python OBB.py. Let's run it now and see the results. It's just going to create an instance of our custom trained model, and now it's going to run the video. I'll just drag it over here. So we have the hand painted cup. It also detects the Halloween cup here as well. Again, this is not the exact same data set and background and distance, camera, and so on that has been trained on. So that is probably why we get these false predictions for some of them. But we can see the hand painted cup. It does a really good extraction of that. It does the bounding box. It rotates it fairly nice. Again, we're not doing any tracking at all. So right now I'm just going to put it here on the table, and now we can see the results are a bit better. So now we can see the results. It does detect something here on the left with my AirPods, so it thinks that that is a hand painted cup. But again, this is not similar. This is like very far away from the data set that we annotated, but it is a bit old data set. So here we see like when I'm actually taking the camera further away, it detects it as a cup, but if it's too close, it doesn't really recognize it as the hand painted cup any longer. So here we see that our in bounding boxes, it is following the object around, so that is very nice. Now we can also go in and see inside our runs, predict free. Then we also get the results extracted. So you can use that video later on because we have this argument set equal to true for saving the video and the results. So this is very awesome. We have the RNA bounding boxes that rotates around. We get all these extractions. You can extract all the results. Again, this is just like an arbitrary video. We can go in and fine tune our data set, make it more general, have different backgrounds, have different distances. So again, sometimes you can see that the video or the camera was just too close to the cup to be able to detect it because it was like trained further away and also with a different background, orientations, and so on. But you saw the validation results when we trained the model. So that's pretty much everything. We've been through the whole pipeline for training these oriented bounding box models for YOLOv8. So I hope you guys have learned a ton. Definitely try it out. I'll throw the Google Colab notebook under the video here in the description. Check it out, try it out in your own custom data set. This is really useful for object detection applications where you want to have like these bounding boxes oriented, rotating together with your objects instead of just having these statics and non-dynamic bounding boxes as we have been used to with YOLOv8 and also a ton of other different object detection models out there. So I hope you have learned a ton. Definitely try it out. I hope to see you guys in one of the upcoming videos. Until then, happy learning. Hey guys, welcome to a new video. In this video here, we're going to take a look at how we can do object detection on small objects. So I know a lot of you guys have struggled trying to get object detection to work on smaller objects. You might have your pre-trained models, you try to run it also with your own custom models, but once the objects get to a certain size, you can't really detect them any longer, or if they're very far away from the camera. So I have a solution here that we're going to go over. It is a framework called SAHI. I'm going to create a bunch of videos just trying to test it out with YOLOv8, YOLO-nas, a bunch of different object detection models. We're going to see how to run it on a single image. We're going to go through some Google Colab notebooks. So I'm also going to create a video where we're going to grab a video, basically detect every single object in every single frame for the whole video. And the last cool thing that we're going to do is going to run it on a live webcam later on. So definitely remember to hit the subscribe button under the video. So let's just jump straight into it. Let's get started and see how we can do object detection on very small objects. So we're just jump straight into the SAHI GitHub repository. So this is the framework and library that we're going to do object detection with to be able to detect small objects. So just scroll down, we can see an example. We can also see all the code that we have in here. The main idea behind it is that we're going to take our image, going to divide it into a number of tiles, and then we're going to have a sliding window going over our whole image. So before, when we're just doing traditional object detection on a single frame, we just take our full image, throw it into the model, we get our outputs out, draw our bounding boxes, and then that's pretty much it. So we're just doing a single pass to our model, but this is not really sufficient. We can't do that if we have very small optics. So if we just scroll a bit further down to start with before I explain a bit more. So here we can see a comparison with YOLOx and also YOLOx with SAHI. For YOLOx, we're only able to detect a few cars here driving on the freeway. So again, we're only able to detect the larger cars, even the one here in the middle. We're not able to detect that because it just gets too small to be able to run from a single image. When we're doing inference with our object detection models, we often use 640 by 640 image resolution. So that's not really a high resolution, but when we're going to do these tiling windows, we're going to be able to detect these very small objects. Even here in the background, I can't see the cars for myself. I can only detect the cars here on the freeway, but we have some cars over here in the background. I'm not even able to see that because we have the SAHI method, which just zooms in, does the tiling windows, and it's able to extract way more information that I can even see here on the image. So this is pretty cool. It's very useful if you want to detect very small objects in your images, and I know a lot of you guys have had problems with that before, but there's one bottleneck and one downside. Everything comes with a trade-off. So right now we get more accuracy, but that also reduces the inference speed. So all the code behind this framework is not really complicated. Under the hood, everything that it does is just take a window, a sub window in the full frame. So let's just start in the top left corner, and then it's basically just going to slide a window. So it's just going to take a subset. We can take a relative resolution, upscale that image as well, and so on. But we're going to take a sliding window, and then we're just going to slide it from one side to the other, go one down, slide it again. So this is basically how a convolutional layer works in a neural network as well. So when we're dividing it into tiles, we can also have overlap. So we can have overlap in between our tiles, which act like just means that we won't get double detections. We can filter that out as well, but we won't end up act like just cutting right in the middle of a detection. So we split it in two. That is also resolved in here with the SAHI framework. You can use it out of the box. But the downside, let's say that we divide our image into 5 tiles. It is going to take 5 times as long as just doing it on a single image, maybe a bit lower because you can actually just downscale or have lower resolution for your tiles. But the main idea is that we're, instead of just taking a single image, we're going to take 5 images, pass that through the model, extract the results, combine them into the global frame. So once you have done it on a tile, we also need to rescale the coordinates back again. So the whole code behind it is just divide it into tiling windows, slide it over. You can just have 2 for loops running with a tiling window. Make sure that you're actually handling the overlaps as well and so on. So we need some resizing. Then take the coordinates, take the predictions, scale it back into the full image frame again. So that is all the technical stuff going under the hood for this framework. You can see a lot more examples in here. Google Colab notebooks for running it with different object detection models. Again, I'm going to go through one of the notebooks in this video. We're going to create some other ones where we're going to grab it, extract it into our own custom Python script to run it on videos and also a live webcam. So we'll still get pretty good performance if you're running it on a GPU and so on. You'll still get very high inference speed. It will just be way slower compared to just doing it on a single image, but the resolution, the accuracy is significantly better, and now we can be used for a ton more use cases in our computer vision projects and applications. So that's enough talking. Let's just jump straight into the Google Colab notebook. First of all, let's just connect to the runtime. We're not going to use a GPU in this example. Let's just run with the CPU. First of all, we need to do some preparation. We need to pip install Torch, SAHI. The SAHI framework can just be pip installed directly. Here with SAHI and also YOLOv8. You can also use YOLOv8 or whatever model that we want to use. First of all, we're going to import some different stuff from SAHI, how we can download the YOLOv8 models from Ultralytics, auto detection model, read image, download from URL, and all those things. We specify the model path, set out the model, download the model to our local environment or here in our Google Colab notebook. We can download some images from a URL. You can also drop it directly in here, or if you're using your own local machine, just specify the path to the image that you want to run inference on. So just go in, pip install it, let's run it. We have connected to our runtime. We're just going to run these blocks of code that we already went over. So now download our images. Now we can do standard inference with YOLOv8. So we have our auto detection model from pre-trained. So this is basically using like Hugging and Face under the hood. We specify the model type, model path, confidence, and the device that we're going to run. So either CPU or GPU. If you're running a Google Colab notebook, you can also use the free GPU directly. After that, we can go in and get a prediction. We just need to specify the source that we want to get a prediction from and the model that we want to use. for doing the prediction. We can also go in and do it in other ways. So here, for example, we load in our image, we read in the image as a numpy array, and then just throw it through our detection model, and we will get the exact same results back again. So right now I'm still doing some setup up here at the top. If we go inside the SAHI GitHub repository, let's try to see if we can find the file where it does all of this slicing. So right now we can see that we have this slicing.py, we have prediction.py, predict.py, auto model, and so on. So this is everything that is going on under the hood. We also have some utils, but slicing is for dividing the images into tiles. We have the predictions for doing predictions with the different models. So it both supports like the different YOLO models and so on. We will go more into details with that in another video, where I'm going to show you how we can swap it at the model, run it on videos, and also on a live webcam. So this slicing.py is what is doing all of it. So get slice boxes. So this is the tiling windows that I talked about. Annotate inside slice. So let's say that we want to draw the bounding boxes. We also need to rescale our coordinates back into the original image. Process COG annotations if we're using that. We create a class here of a sliced image. So we're just going to have a list of sliced images. You can have a for loop just running through each individual sliced image inside of that array. And then you can do your predictions. So you can also use your own models, the Autolytics framework, and so on. You just get a list with all the images, take a for loop, run through it, do inference, take the results, rescale it back, and you're good to go to use it in your own applications and projects. And I will have all the code available on my GitHub, so definitely check it out under the video here. And then you can use it directly in your own applications and projects. So yeah, pretty much starting pixel here. So where the sliced image is actually like starting, how you can get an item from it, sliced image. We have some different input parameters. So like the overlap height ratio, overlap width ratio, the slice height and slice width. So that could be like 640. Let's say that we have a 1280 by 1280 image. We want to slice it into a number of different sizes. So that could be like 400 by 400. It's going to do all the calculations, all the slices automatically, and we can also specify the overlap size. So let's say that we want to have 50% overlap in all our slices when we're doing our tiling windows. So we have a bunch of different arguments that we can set in here, and it's going to do all of that automatically. Let's go back into our Google Colab notebook. We have to restart the session, and now we can then set up our SAHI framework, download our images and the model, and then we can run our detections. So now we have our results. Let's just try to go down and print it out, and let's see what we get. There we go. We run this block of code, misspelled it. So we just have results and not results. There we go. So now we can see that we have this class SAHI.prediction. So once we have our prediction, we can also just export it so we can see it in the CharuCo dataset. So to CharuCo annotations. There we go. We can just call this functionality on top of it. And now we should be able to see all the bounding boxes. We have the image ID, the bounding box. You see the bounding box here, the 4 values. So the top left corner and the bottom right corner. This might actually be the width and the height. Yeah, that is the width and the height in the CharuCo dataset. We get our confidence score, the category ID, and also the category name. So we're detecting cars in this image here with a pretty high confidence score. And this is how you can extract all the results. Now we just get a list with these dictionaries where you can go and extract all the individual keys. We can also do it directly on a numpy array if you already have it in OpenCV. So this is how we can use it in our own custom Python script. So let's say that you're using OpenCV to load in a video, webcam. Again, as mentioned, I'm going to do a video where we're going to do all of that. The code will be available on my GitHub, and it will be out in just a few days. So yeah, we can also go in and run this directly. It will give us the exact same results. Now we can go and export the visuals for the results and just create an image. There we go. So results.export visuals is going to do all the annotations on top of our image. And this is act like the results that we get. But again, this is without SAHI. So these predictions are act like just the predictions from the full image. So as we know from traditional object detection, but now we can see that we're not able to detect all the cars in the background, even some of the cars over here to the left, even though they seem to be relatively easy to use. So now we can go down and do sliced inference. So we can get slice prediction directly from SAHI. So we import this function from SAHI. And all it's doing is taking the image, dividing into slides, sliding it over with for loops, taking care of all the overlaps, the rescaling, upsizing, transforming the coordinates from the sliced image to the global frame and so on. But that is also pretty easy to do yourself. So you can specify the path here, the detection model, the slide height, the slide width, and also the overlap. So right now we're just going to go with 20% overlap in between all the individual tiles. So let's run this, let's get the results, and now we can see some more down here at the bottom. Again, we can go in and print the results. So result.toCoco annotations. Run the function, and we should be able to see our detections as well. But now we get significantly more detections, as you can already see. So now let's go down and just run this one, export visuals again, and now we should be able to get our inference results with the SAHI framework. So now we're detecting a bunch of trucks here that have relatively low confidence, can be filtered out by having a threshold for a confidence. Now we can see that we're detecting all the cars here in the background. They have slightly lower confidence score compared to the ones in the foreground, but these objects are very small, and some of them it is even hard for just a human eye to distinguish between the cars and the objects from this view. So this can be useful in a lot of different applications and projects where you have very small objects. Could be like dense objects as we have here, but it could also just be like sparse objects so far away that your object detection models are not able to detect it. So now we can go down and predict our results. So get our prediction results, how we can extract it and use it in our own applications and projects. So this is basically what we have been doing and what I just printed before. From our results, we can get our object prediction list. There we go. We can take the 0th index of that, get our bounding box, mask, score for our confidence score, and also the category ID. And then inside of that one, we can just specify which one we want to take. So So say that we want to take our bounding box, we can just specify .bbox, and we should be able to extract the bounding box directly. So now we both have a width and a height, and also the coordinates of our bounding box. So these are just some of the operations and functions that you can call on top of the result class or the instance that is going to generate from the prediction of the sliced windows. So right now, result.toCoco annotations, we're just going to visualize the first 3 of them. Exact same thing that are printed up at above when we actually did our prediction. Can also be converted to Coco predictions. So to Coco predictions, image ID equal to 1, and we take the first 3 predictions. We get a dictionary, we just get a list with dictionaries. We can go in and take each individual key, so we can just index it directly. So let's say that we want to take the 0th element of that. So instead of 3, we just want to take 1. I need to specify 0 here. There we go. We're going to take the first index, and then inside of that, we just have a dictionary. Let's say that we want to go in and grab the bounding box again. Then we can just index it like this for our key and to get our value. There we go. We have our bounding box. And I think we can also extract the class ID. I'm not sure how that looked. So let's just copy that one, run it again. And here we can see to extract the score. We can just type in score. It's going to get that, and you can just have a for loop running through all the predictions. This is just showing a single one, but you can just have a for loop running through all of this, extract the bounding box scores. You can visualize them yourself or use them in your own applications and projects to extract the results. So we can also go down and convert it to different annotation formats, but I don't really care too much about that. I normally just use the Coco format. So now we can also do batch predictions. Again, right now we're just running a single image through, but you can also have batches with multiple images. I'm also going to show you how you can do it on videos and webcams, as I mentioned throughout this whole video. Again, we're going to do the exact same thing. Now we're just going to have an image directory with a bunch of images instead of a single one, and it's going to take care of all of that. We can just call our predict function, specify the model type, model path, the device of the model, model confidence threshold, source image directory for all the images that we want to process in a single batch, slice height, slice width, overlap height, and also the overlap width ratio. We run this block of code, it's going to do the predictions, it's going to perform inference on our images. So right now we can see it's doing inference on 3 images. It's going to divide each image into a number of slices, so performing prediction on 20 number of slices. So each individual is going to be sliced, and then we process all of them in a single batch. So right now we can see the first image has been sliced into 20 slices, the second one 15 slices, the third one 15 slices as well. And now we can see that our images has been processed. Prediction results are successfully exported to runs predict exp, as we have with the YOLOv8 and YOLOv8 models. So runs, predict, experience, visuals, and we can go in and grab these ones. So it's just going to be PNGs. So right now we can see this example looks pretty cool. Small vehicles, we can go in and see the example, and terrain.png. So here we can see the trucks. We might not be able to detect the truck here in the background with just traditional object detection models. So right now we can see that this is pretty similar, but we're able to detect small objects with this SAHI framework. So I hope you learned a ton in this video here. I know that you guys want to learn how you can do object detection on smaller objects, and this is the way to go. I've not seen any other approaches where you're actually able to detect the objects like here. So thank you guys for watching again. I'll hope you see you in one of the upcoming videos. Until then, happy slicing. Hey guys, welcome to a new video. In this video here, we're going to take a look at how we can do object detection on very small objects. So in one of the previous videos, we went over the SAHI model and the SAHI framework, so you can actually just divide your image into individual tiles. Then we have a single tile just sliding over a whole window, and then we do inference on each individual tile. Of course, this is going to take longer to process each individual image, but now we're able to do object detection and detect even the smallest objects in our images. So this is very useful in a lot of computer vision applications and projects where we don't really need that real time. We're still able to squeeze out a couple of frames per second, but we won't get like 30, 60, 90 frames per second because we have to do the processing on each individual tile. Then once we have the tiles and the predictions in each individual tile, we just need to rescale the values back into the global frame, and we pretty much have all our detections. So let's just jump into the code. I'm going to show you how we can do it from scratch, so we're not using the SAHI framework, and also how we can run it on videos and a live webcam. So let's just jump straight into the Python script. I'm going to show you how we can do this tiling window inference on a live webcam and also stream, where we're going to go over the code, the functionality, and also how we can divide our image into tile, rescale our coordinates back into the global frame as well. So this is pretty much all the code. Doing that, you can modify it, you can process it on your own. We don't have any framework at all. This is custom implementation. We're going to process this video here, and we're also going to see how we can run it on a live webcam. So if you're just running this through a YOLOv8, YOLOv9, you can take whatever object detection model that we have out there. It is only going to detect the cars and also the trucks in the front of the image here, and the ones up here at the top. It's not going to detect those. Those are just too small, even though with the human eye, we can easily see them. So this is kind of like the trade-off when we're doing object detection and so on, and it really depends on the objects that you want to detect. So right now we can still visually see these cars, but there could be instances, there could be classes and objects where we can't really see it with the human eye unless we zoom very far in. So we really just go down on a lower pixel level when we're doing inference with our object detection model by using tiling windows. So let's now just go back to the code again. Let's go over it step by step so you guys can know how to implement it, how it works under the hood, and then we're going to see how we can run it and see the results. So first of all here, we're just going to import the different modules and the dependencies that we need. So OpenCV, from typing here, we're going to have the dictionary, list, optional, sequence, tuple, and so on. This is basically just for the format of our function. So we specify the input arguments, the data types for inputs, and also the outputs. Then we have PLL here. We need to convert it to PLL before we can go in and process it. We can also have like a for loop running through all of the code. We're going to use autolytics, so we can just take a YOLOv8, YOLOv9 model, and then we're going to process that on each individual tile. So we can go down on an even lower level and do this implementation ourselves, but then we need to take care of a lot of things. We can't do automatic slicing and all of those things. Right now we just have a single function. It takes in the image height, image width. So these are just two integer values. We have the slice height and also the slice width. So this will be our tile window size. So it's basically just one large image. We divide it into sub images, and then we just slide that over a whole image and basically just do a scan. Now we can also set the auto slice resolution. So if it just needs to figure out by itself how to do auto slicing directly in here, if you don't specify the slice height and also slice width. Another cool feature that we have is that we can specify the overlap width and also height ratio. It's basically just how much should each individual tile overlap each other, because if we just do detections on one tile here and another tile, we might end up cutting the object right in the middle. And to be able to get around that, we just need to have this overlapping region between our tiles, and it really depends on the size of your objects, types of your objects, and so on. But it is always pretty good to have like these overlaps. The code here will take care of all of that, so you don't go out of boundaries. You get the exact amount of slices. It will take care of all of that. You can also do the implementation yourself with just like 2 for loops, where you're just running through the whole image. You specify the slice width and also the slice height, and then you can do slicing with NumPy on each individual image. But then you can't really have like overlapping regions. You need to take care of like your slicing height and also slicing width. It should be within the boundaries. We can't really like have 1000 pixels in the X direction and try to slice it in 4 slices with 300 pixels in each, because that is going to overflow and go out of boundaries with 200 pixels. So this code here is taking care of all of that. So you can use this code here directly. It will be down in the description on my GitHub link. So first of all, here we just have all these different parameters, and it's going to return a list of lists with integers. So this is going to be our slice bounding boxes for our image. So first of all, here we just have our slice boxes. So we're going to find the boxes which we're going to do our slices for. We need to take care of our coordinates all the time. So the top left corner, we always look at the top left corner when we do our slicing in each individual image for the tiles. Then we just check here if we actually have something for the slice height and also the slice width. Now we're going to take care of how much overlap do we need to have in the Y direction and in the X direction. And that is just integer value of our overlap height ratio multiplied with our slice height. The exact same thing with our X value, so for our width. Now we have taken care of that, we can then go down and have a while loop just running through all the Y values. So right now we're just going to have our Y values. We set our X value equal to 0, and then we have our Y min plus our slice height. So it's basically just going to run through each individual pixel in both directions. So instead of just having, you can also have like 2 for loops instead of 2 while loops. But right now we just run through a whole image with the individual slices. Then we can go in and append the slice boxes. So right now it's just going to extract the values. So the min and also the max for our values. So we need the top left corner and also the bottom right corner. And then we have the slicing bounding boxes for our tiling windows. Then we go in and just append that to our slice underscore boxes, and that's pretty much it. So it's just a for loop, or like 2 while loops, 2 for loops, just running through the whole image, finding these slice bounded boxes. When we have that, we can go down and create a class. So right now we just have a class instance where we have an image and also starting pixel, because for every single tile, we need to know where that tile is starting, or else we can't really project and remap our coordinates from our predictions to the global frame again. And we want to do that. We don't want to just have individual predictions, because if you just have one tiling window, let's say it's 50 by 50, then you will get all your values, all your detections within that range. So between 0 and 50. But if you have like an image, which is 1000 by 1000, we will just have all the detections in the top left corner. So we need to take all of those detections, add it with the starting pixel, because then we basically just project and rescale all our coordinates back into the global frame. So right now we just have a class for a sliced image. So it's just going to contain the image and the starting pixel, so we can always retrieve that. Then we have our sliced image results, which is basically just going to contain our whole image. Then we can have a for loop running through that. So right now we have original image size and image directory. We can have multiple images. We can have a single image. We can just pull an image from a video or a webcam with OpenCV, convert it to PLL, and then it's going to take care of all of that. Then we have our sliced image list, which is the one that we're going to return. And then we can have a for loop running through each individual tile that our image has been divided into. Then we just have a function for adding a sliced image to our list down here. So a sliced image underscore list dot append, and the sliced image that we're going to get as an input argument to this function. Then we have our property functions down here at the bottom, which is basically just going to both return our sliced image list when we want to do inference on our tiles. We have our images here. So if we just have like an image list, we can just go through all of that. We can take the image. So right now inside our sliced image, we both have the image, but also the starting pixels. So this is if you just want to return a list with all the individual images. And then we also need our starting pixels. So these functions are the exact same thing. The only difference is that we now get the starting pixel instead of the image. We can also extract the file names. Same code, just a for loop running through all our sliced images, retrieving that information, both our starting pixels, the file name, and also our image or our tile. Then we can go down and create a function for getting an item. So once we want to get an item, do a next iteration in our list, it's just going to return a dictionary with our image. Then we just need to specify the index of the image or the tile that we want to extract from our class, and then it's just going to return a dictionary with the image and also starting pixel. We go in and index the images and also our starting pixels, where these lists here, they come from the other functions where we extracted all the information from the image and also the starting pixel. Then we basically just have some checks for if it's a numpy array, If it's like an integer value, then we can just call these functionality that we have up at the top here. For example, here we just check if our instance or index right now is a slice. And if it is slice, we're going to get the length of it. We're going to get the indices with our start, stop, and step. So this is just like the range of the for loop that we're going to run through. And then we can prepare the ith dictionary with our images. So we'll say that we have 10 slices that we want to run through. Then we have like a 1, 10, and then we have a step size of 1, and then we can prepare each individual tile, and then we just extract a list, return the list with each individual tile, or like our dictionary, because it's going to return this one up here at the top when we call prepare ith dict. Then we can go inside the dictionary and extract our image and starting pixel. So that's pretty much it. We can also extract the length of it. If we just call the length, we get the number of tiles that we have divided our image into. Now we have our slice image here, which is just going to use all of the classes and functionality that we have above. So we have our image, slide height, slide width, and so on. So these are the exact same parameters. It can also go in and do auto slicing based on the resolution if you want to use that. Then we can specify the minimum area ratio for the tiles that we want to use as well. So all of this functionality is already in there. We don't need to take care of that, and it's very useful. So right now it's just going to take the image, take the PLL image, get the image height and also the image width. You can probably convert it to NumPy directly as well, so you don't have to do conversion later on. But this really depends on if you're doing like single image processing, or batch processing could also be like on live video streams as we're doing in this video here, just to show you guys, okay, how can we actually like set up the whole code base here? How can we just take an image, doesn't matter where it comes from, how can we take an image, process it with this tiling window method, the method behind SAHI, and do object detection on very small objects. So now we're just going to call our function, so get slice boxes. We get our slice boxes, which we're going to use later on. Now we can go in and create our slice image result depending on the original size. So that's what we have here. Then we have our sliced image results, which is just a list of all our images. Then we need to have a for loop running through all the slice boxes. We have our full image, we have our bounding boxes for our slices. Now we need to go in and actually like slice those with NumPy. So right now we're just going to have a for loop running through all of it. We have our top left corner, our bottom right corner, the XY value for those. So that's pretty much everything that we need. Then we have our original image. We go in and do the slicing. So we take the top left Y value and go to the bottom right Y value. And then we do the exact same thing with our X value. So it's basically just how do we extract the range for our image inside the tile. So this is how we can do slicing with NumPy. And it's going to take the window. So this will be our image sliced for the first sliced box that we have extracted. And then it's just going to do that for the X number of slices that we want to divide our image into. So that could be 10, 20, 5, 3, whatever you want to use, depending on the resolution and also how small objects you want to detect. Then we have our slice width and our slice height. We create an instance of our sliced image with each individual slice that we have. And then we just append that sliced image to our sliced image result, and we can return that. So right now here at the bottom, it's just going to return a list with each individual tile inside that list. Then we can have a for loop or index that list directly to extract the individual slices. So that's pretty much it. That's the whole functionality behind SAHI. I've extracted the code here, basically just to show you guys like how can we run through it, how can we just take an arbitrary image, throw it through the whole pipeline and get the results instead of wrapping this around like multiple different frameworks. If you're using SAHI, it only works on a single image. It is not really general. You have to do specific modifications depending on the object detection models that you want to use. Right now, we just need to take the image, throw it into it. Doesn't matter what object detection model, segmentation model, whatever you're using, you can throw it directly into this code. Now we set up a video capture with the video that I showed you guys at the start. We create an instance of our model with YOLOv8. We have our while loop, just opening up our webcam. And as long as that is open, we're just going to iterate inside our while loop. We take the capture, we read an image from our capture. It could be a video file or a live webcam. We start our timer here just to see how many frames per second are we actually able to process. We convert our frame to a PLL image, we extract the height and the width, and now we specify the slide height and also slide width. So that is really a parameter that you need to specify on your own. Right now, I'm just dividing the image into 4 parts. So basically just take the height and the width, slice it by 4, and then we're going to get our tiles based on that. Then we call a function slice image. We specify the parameters. Right now, it's just going to use some overlap as well. You can also just specify 0 depending on the use cases that you have. Let's just start with a small overlap here, and then you normally If you have double detections, you will go in and use non-maximum suppression to filter those out. But let's just have some overlap in this example. We get the number of tiles, so we can show that later on. Then we have our results list for the bounding boxes, confidence score, class IDs, that we can use it in our own applications and projects, how we can extract the results from the prediction from Autolytics. So now we have a for loop, we have an enumerate, we enumerate through our sliced image results. So we both get our I for index and we get our image slice, which is actually like slice inside our image. Now we can go inside our sliced image. We have a dictionary, as you remember, we have the image and we have the starting pixel, so we know how to convert it back to the global image frame again. We have our window, start X, start Y. We do our prediction on our window. We can specify the confidence score here directly. We can probably just have that a bit higher, so 0.20, default is 0.25. We now have our results variable and we need to know how to run through that. Inside of Autolytics documentation, you can find how to actually extract them if you're doing segmentation, tracking, object detection, and each individual class and attribute in there. So now we just have a for loop running through each individual result. We extract the bounding boxes. So when we do object detection, we need to go in and extract results.boxes. Then we get our boxes where we can go in and extract the XY, XY. So it's the top left and bottom right corner, the confidence scores, class IDs for each individual prediction that we have. So to be able to extract the XYs, XYs, we need to go in and take XY.xy. So this is just an attribute to this box class. We convert it to CPU. If you're using GPU to process our image, we need to convert it from GPU to CPU. And then we convert it to NumPy, so it's just easier to work with OpenCV. Then we check if the size is equal to 0, because again, if we're not detecting any boxes, we just want to continue to the next result that we have inside our results variable. We extract the XY, XY, we get our confidence score, we do it in the exact same way. We can extract the class ID. There's also a bunch of other attributes that you can extract. You can find all of that on the Autolytics documentation. Then we're going to have a for loop running through all the XYs, XYs. So this is pretty much just all our bounding boxes, and for each individual bounding box we can also extract the confidence score and the class ID. So we extract the X1, Y1, X2 and Y2 because now we need to go in and actually scale it back. So right now we have the global frame, then we just have a small tile. We take the top left corner and we need to actually just rescale it all the way back by adding this start value for our window. So this is something that we have to do to be able to have our detections in our original image. Convert it to integers again, and then we can go in and append a list with our bounding boxes to the boxes list, confidence scores and class IDs. And now we have all the results extracted and we can use it in our own applications and projects, either to do some triggering, alert systems, whatever you want to use it for, tracking systems, counting systems, and so on. So that's pretty much it. We have extracted all the results. We're ending the timer because right now it is just like looping through the results, visualizing them, or if you want to do something else with them. Now we have a for loop again, just running through all the bounding boxes. So this is just for visualization. Bounding boxes, we take the ith elements. So we're just going through all of them, extract the bounding box, confidence score and class ID. And then we just have a rectangle with our bounding box on top of each prediction. And then we just put some text out here. We specify the class ID and also the confidence score, number of tiles in the top left corner together with the number of frames per second. At the end here, we just use OpenCV to show the frame where we're drawing all the results. If hit Q on a keyboard at any time, you're going to break out of this while loop and terminate the program. So that's pretty much it here. We went through all of the code line by line so you guys can understand what is going on under the hood when we want to detect small objects. And I'm not just talking small objects, I'm talking very small object on very low detail. So we're operating on pixel level now, where normally if you're doing object detection, let's say that we have like a full HD image or like an HD image, so it's 1280 by 720. When we pass it through an object detection model like YOLOv8, it actually like downscales the images to 640 by 640 or like 640 by 480, depending on like what you specify. Could also be lower or higher depending on the model that you're using, but it actually like resizes and downscales the image a lot, where we lose a lot of information, and that's why we can't detect very small objects. So it's always a trade-off between like accuracy and speed. So now we just open up a new terminal here. I'm going to use Anaconda and we can just run the Python script directly. So tiling.py, and we're going to use the video that we specified up at the top. Now I'm going to run it and let's see the results with YOLOv8. So here we can see the results running. We can see it pretty much detects every single car, even the cars driving up here, which is pretty hard for just us to see. We can lower the confidence score. We can also like use a larger model, but pretty much all the cars here, they have a confidence score at around like 0.80 to 0.90. So that's pretty cool. Now we're able to detect every single object in the frame. If you're not using tiling windows, it wouldn't be able to detect any objects above this line here. So all the cars in the background, it will not be able to detect those. This is really helpful for a lot of use cases and applications within the computer vision field, especially if you don't want to run real time. Right now you can see it processes around like 5 to 6 frames per second. I probably also have too many tiling windows or like tiling windows. So right now the frame is divided into 27 tiles, also because we have the overlapping region with 20%. We could probably lower this significantly more, maybe just like have a few tiles and it will still be able to do all the detections. 27 tiles being processed 5 times per second. So this is pretty awesome. Again, you can optimize the models. You can use smaller ones depending on the hardware as well. Right now I'm running this on my 4090 GPU. We can see the image resolution that it throws into the model. You can see the inference speed and so on. So right now it processes it with only 4 milliseconds for each individual image that we pass through the model. So this is multiplied by 27, and then we basically just take a look at how many of those batches can we process per second, and that is around 5 on a 4090 GPU. So you can probably not expect more than a few frames per second, probably like a bit higher if you're using like a lower amount of tiles. It doesn't have to be 27, could just be a few tiles and you'll still get significantly better performance compared to just using the single image. Right now, just to end off the video, I'm just going to run it on my webcam instead, just to see how it performs on that one. We also have multiple different classes that we're detecting and not just cars. So we should just be able to specify a 0 for opening up our webcam. It should open up in just a second. There we go. I can just turn around. Of course, we're going to have a lot more detections. So this is only like a 640 by 480 image. We can also increase the resolution of that by just specifying the parameters inside, or like the settings inside of OpenCV. But let's not take too much into account with that. There we go. Let's delete the overlapping region as well, just to have less tiles. We should be able to process it. Right now it's a very small frame that we're basically just going to divide into a number of tiles. But we can see it's able to detect everything here. We get some double detections here and there because this keyboard will be basically divided into multiple different tiles. You can combine them, but this is mostly suitable for smaller objects and also if you have like very large image resolution. So just processing this video stream here would actually be doable with just a single pass. So we don't really need to use tiling window on this, but I just want to show you guys how we can run it on a live webcam, on a video, on an arbitrary image. You can take whatever you have. Right now we can even see it processed around like 25 to 30 frames per second with 6 tiling windows. So it's going to take 6 windows, divide the image into 6 windows, throw it through the model, and it's doing that 25 times per second. So there's a lot of processing going on, and we can see it detects all the objects here pretty nicely. I can just move it around, get on top of it, TV, cop, person. We pretty much get all the classes in here, which is kind of like expected with the pre-trained model. So thank you guys for watching this video here. I hope you learned a ton. Definitely test this out if you have problems. I know a lot of you guys have reached out and have problems with detecting smaller objects in computer vision applications. So this is how you can do it. Use the code directly. It is pretty cool and you will get way better performance. Of course, you won't be able to run this in fully real time. So check it out. Everything will be on my GitHub. Go through it again. We went into details with every single line of code. I really like to create these technical videos where we really dive into code, explain step by step how does these models work under the hood instead of just using high-level frameworks where we need to do modifications here and there and we don't know what's going on under the hood. So I hope you have learned a ton. I hope to see you guys in one of the upcoming videos. Until then, happy learning. So we also have an AI career program if you want to learn how to land AI jobs and get AI freelance work. I teach you everything in there. We have programs, all my technical courses, weekly live calls, personal help, and I'd love to have you guys in there, help you out in any possible way. You can check out the program down in the description and the community, and then I'll just see you guys in there. So in this video here, we're going to see how we can train a custom YOLOv8 model on our own dataset. I'm going to show you the whole pipeline, how we can take a dataset, upload it into Google Colab notebook, use the free GPU in there, train a model, train the YOLOv8 model with the Ultralytics framework, so it is now supported in there. That means that we can train these YOLOv8 models in just a few lines of code. I already have another video where we go through the whole pipeline, how you can generate the images and so on. So definitely check that video out. And then we use the code from the YOLOv8 GitHub repository. But in this video, we're going to use the Ultralytics framework, so we can do it in just a few clicks. So let's just jump straight into my RoboFlow datasets. Let's just go in and take this cup dataset that I already had used in some of the previous videos. So right now I just have a bunch of images in here. You just need to capture them. I have tons of videos about that. I even have scripts on my GitHub, different repositories. So right now we just have a bunch of images that we have labeled. Here we have around 200 images, and we have even used some data augmentation. So this is basically just a model that we want to train to be able to detect these cups. You can use an arbitrary number of different objects. You can test out on your own dataset and so on, but RoboFlow is really easy to use and also annotate. So right now we can go up and export our dataset. We just need to choose the YOLOv9 format, and we can show the downloadable code. We just get a code snippet here. We can throw it directly into our Google Colab notebook. It will take care of all the dataset, download it, export it into our notebook, and we're good to go. So now I've just copied it. Let's go inside our Google Colab notebook. So this is just a Google Colab notebook from scratch. I'm just going to copy paste this one directly in here. Before we connect to the runtime, make sure that you go up and choose the free GPU available. So we have a T4 GPU, so we can train our own custom YOLOv8 model in here on a GPU. So now I'm going to hit save. We connect to the runtime, and we're pretty much good to go. We're going to pip install RoboFlow and set up our project with our dataset. And the only thing that we need is to pip install Ultralytics as well. So I'm just going to write that code here. Or we can just do it up here as well together with RoboFlow. So now we're connected to the runtime. Let's just hit start. So we pip install RoboFlow, we pip install Ultralytics. It's going to set up our whole project and also dataset. While it's doing that, let's just jump straight into the Ultralytics documentation. And now we have our train mode. If we go inside the modes tab up here at the top, we then have training. If you scroll a bit further down, you can also go in and see all the different models, but you can either call the command lines or the Python scripts. With Ultralytics, we only need to specify a few lines of code, and it will take care of all of it automatically for us. We also have a bunch of videos in here, so I'm creating the videos for Ultralytics as well. So definitely go in and check those out and subscribe to the Ultralytics YouTube channel. If you go inside the different models, you can see all the models available, and we now have the YOLOv8 model, which is the newest version in the YOLO family. If you just go a bit further down, we can see all the benchmarks and so on, and also how you can use it, both for training and also prediction on new images. So I'm just going to grab this code. There we go. You can also use the command line directly. Let's go back in here. We have now extracted our dataset. I'm just going to copy paste the code. We can specify the Nano model, but right now here we're going to use PT because we want to use a pre-trained model. There we go. And then we just need to specify our YAML file from RoboFlow. Train for 30 epochs. Let's go over inside our data directory. We have our cup also dataset one. We have our test, train, and validation split, and we also have our data YAML file. So inside each of these folders, we have our images and also our labels. So here we can see we have all these images, and these are the exact same ones as I showed you inside the RoboFlow website. We have our labels in the YOLOv9 format. So we have the class, and then we have the bounding boxes here normalized to the image resolution. If we go down into our data YAML file, I normally just like to copy paste the paths here, so we make sure that these are correct. So here we have test, and we actually need the images. Just copy that path. There we go, and we have our train, and we also have our valid. So we just change the paths here. We have valid, and then we have train. Then we're 100% sure that we won't get any errors in here. If you're getting errors, it is most likely because of the path here. So now we have our data YAML file. The only thing that we need to specify is copy paste the path, throw it in here instead of the CharuCo8. There we go. We can now start training a model. We import YOLO, we create an instance of our YOLO model with new YOLOv8 Nano model. Model.train, specify the data, epochs, image size. There's a bunch of different arguments that you can specify, but we can see all of that inside the Ultralytics documentation. If you go inside train and just scroll all the way down, we have our model, data, epochs, time, patient, batch size. All of that can be specified in here. Maybe we should specify the batch size to 8 as well. Let me just make sure that this is actually like the correct. So batch, there we go, batch, and the default is 16. If you run out of memory, it is most likely because of the batch size. So just change that to 8, should be good enough. So yeah, this is all we need. We have our data set. We have our Google Colab notebook with a free GPU. Let's now hit start training. Here we got an error. So let me just make sure no module named Autolytics. Let's just make sure that this is act like I misspelled it up here. Just for in here, ultralit text. There we go. And then it's just going to pip install that module. Make sure that you're running on the newest version. So if you already have it installed on your local environment, make sure that you actually upgrade the pip package or uninstall it and install it again. So you make sure that you have the newest version with the YOLOv8 model support as well. So yeah, let's just wait until we have installed Autolytics. After that, we can just directly run this block of code again, and we should be good to go. It will start training our model. We can then download our model, take a look at the results, the training graphs, export our model, use it in our own applications and projects. So now we can see that the model has started training. It will download it automatically. Check for your data set. So here we can see that we have 184 images in our training set, and it's going to do the exact same thing for our validation set. Set up all the optimizers, all the high parameters, and it will start the training. You can see the live results in here for every epoch. So now we can see that our model is done training. If we just scroll all the way up to the top, we will be able to see all the different epochs per epoch. Just going to drag it up here. There we go. Then we can basically just see we start up here at epoch 1. We can see the mean hours position, the losses and so on. They're basically just decreasing over time. So we just run it for 30 epochs. At the end here, we're going to be able to see all the results. So the mean hours positions, you can see them coming up here, basically just converging at the end. So this is actually like a pretty good model, but again, it is also relatively simple objects that we want to detect. If we scroll all the way down to the bottom here, we can see all the images. So this is the validation that is going to run afterwards. We have 13 images in our validation set. We can see our precision and recall, which is pretty good here. Ideally, we want it as close as possible to 1. The mean hours position 0.50 and also mean hours position of 0.50 to 0.95 is also pretty good. If you go over to the left, we now have a new folder. It's called runs, detect, and inside our detect folder, we have our train, weight. So this is the exact same thing as with all the other YOLO models from Autolytics, but this is the new YOLOv8 model. Then you're going to download your best weight file, and then you can use that in your own applications and projects. You also get all the different curves here. So you get your F1 curve, you get your precision recall curve, which we want ideally all the way up here, but this is still very good results. We're going to take a look at the results PNG. So these are the losses and the mean hours positions, basically just increasing over the number of epochs, converging here at the end. We can also go down and take a look at the validation batches. So this is a validation batch 0, where we just does this prediction. So these images, the model has never seen these images before. Those are from a validation set, and we do a pretty good job. We pretty much detect all the cops in here. I already have videos covering like how you can take the model, throw into your own custom Python script, write all the code, extract the results. So definitely check those videos out. If you just want to test it out fast and just throw in a few images, you can just go in and do that with Autolytics as well. Or else go in, check out the other videos that I have on my channel. But if we go inside our predict mode, you can scroll a bit further down. Here you can see how we can extract the results, but we can just grab this part. There we go, paste it in here. We get the path. So we copy paste the path. Instead of using a pre-trained model, we now have our own custom best weights model. And for the image here, we just need to specify the source. Let's go up and grab one from our data set. So let's take one from our test set. Images, let's just copy paste the first one. There we go. And now we're pretty much good to go. We can just hit save. True, and we might even be able to show it directly in here in our Google Colab notebook. If you're using a Python script, it will show it automatically if you set show equal to true. So let's just run the program here. So right now we can see that it doesn't support imshow, but we can see that the results are stored inside this runs detect predict folder. We have detect, we have train, and now we also have predict. So let's go inside predict, then we have our prediction here. So it's just going to take this image here, throw it through the model, display the results, and we're pretty much good to go. So this is the output from a model. We have trained a custom object detection model with the new YOLOv8 model. Definitely check it out on your own data set. You can use RoboFlow to annotate your images or any other labeling tool out there. This is how easy it is. With just a few clicks, we can have a whole custom YOLOv8, but you can do the exact same thing with YOLOv9, YOLOv8, and all the other models directly available from Autolytics. So this is pretty cool. Take your data set, refine it, evaluate your model, Few clicks, we're good to go. We can now set up whole computer vision pipelines and applications. Definitely go ahead and check out the other videos I have on the channel where we run like live inference with custom models, how we can apply object tracking on top of it as well. And then I'll just see you guys in one of the upcoming videos. Until then, happy training. If you want to get into an AI career, you should definitely check out my AI career program. The program is basically all my experiences from how I went from an average student to where I am today. The program consists of 3 main categories. We have my technical courses, my personal branding course, and then the AI career path. We have a whole community in there with like-minded people supporting each other, and every week we will have weekly live calls where I support and help all of you guys. Over time, more courses, resources, code templates, and so on will be added to the program. You will give lifetime access. So the sooner you join, the more value you will get for your money. Let me help you take your AI career to the next levels. So in this video here, we're going to do a comparison between YOLOv10, YOLOv9, and YOLOv8. So we have all of these models available now, all the members in the YOLO family, and we're going to do a comparison both performance wise but also speed wise. So this new YOLOv8 model is very interesting because it does some optimizations and removes some post-processing steps that we're going to take a look at. So it is actually like significantly faster compared to the other 2 models. But let's go in and see if we actually like take a hit on the accuracy. So to start with, before we jump into some video examples, let's just go inside the YOLOv8 GitHub repository where we can see these comparisons on the CharuCo benchmark dataset. And if we take a look at it, it is clearly the best model, YOLOv8, but later on we might go in and see some other things once we see some image and real world examples from video. So we can see first of all here, it is significantly faster compared to the other models. We have YOLOv9 here in the other red and also YOLOv8. So this is the green one up here. So it is act like twice as fast compared to YOLOv8 and comparable performance. Even the largest model here, it outperforms it on the CharuCo dataset. Also, number of parameters is significantly lower, so that is also pretty cool. And even for pretty much all the models here, it doesn't really increase that much for the large and also the extra large version, where some of the other YOLO models here, you can see that the number of parameters here pretty much just increase exponentially with this size of the model, where it's a bit more linear here with the new YOLOv8 model. So this is pretty interesting. Let's now go in and take a look at what are the differences with the new YOLOv8 model. And if we go inside the Autolytics documentation, we have all the YOLO models in the YOLO family, all the way from YOLOv3 to YOLOv8, but we also have SAM, Mobile SAM, Fast SAM, Real-Time Detection Transformer, and so on. So you can go and read about all the individual models in here, see how you can use them, take them with just a few lines of code and use them in your own applications and projects. So YOLOv8 here, the main difference is that they remove the non-maximum suppression in the post-processing. And what that means is basically like when we have our object detection model, it acts like outputs a ton of different bounding boxes at the output layer, which is basically just guesses of where the bounding boxes are. So we can probably have like 5, 6, 7, 8, 10 bounding boxes on top of each other, having different overlap. And then we go in and do non-maximal suppression, which basically just means that for all the overlapping bounding boxes with some threshold with intersection over union, we're just going to remove those bounding boxes and merge them together. So we just have a single one covering our object. So this is the step that they're removing for this new YOLOv8 model, and that is act like where it gets a lot of the speed ups from compared to the other ones, but also some other optimizations in the layers. So they also have some design optimizations in, for example, the classification head, which is a bit more lightweight compared to the other YOLO models, but also when we're basically just talking about like the layers, they have some downsampling layers and so on here and there, which is a bit different compared to the other models. But again, removing this non-maximum suppression in the post-processing reduces the processing speed significantly, because this is actually like a very expensive operation, especially when we're talking about like milliseconds. And often if you export the models and so on, make sure that you actually like include the non-maximum suppression in the model and also does optimization on that part, because if you're just optimizing the model and then you need to do non-maximum suppression on your own, you won't even be able to run in real time if you're doing this non-maximum suppression in Python. So those are some of the differences for this new model, or at least the most significant ones. Let's now go in and see some results on videos for all 3 models, compare them and talk about the results. So I just have these videos here where we have the YOLOv8 model on the left side and the YOLOv8 small model on the right side. Let's go in and see if we can see any differences on these real world dataset. So this is basically just videos running. So this could be real world and real life scenarios. And then also have the video for YOLOv9 just to see if we can do some comparisons and see if there's any differences. So let's just play it here and let's take a look at the results. So right now, just initially, it looks very similar. I can probably see that it's a bit more dense with the prediction just on a high level for the YOLOv8 small model compared to this YOLOv10 model on the left side. So here we see that we're detecting a person. Sometimes we're also detecting like a traffic light down here for the YOLOv8 model, where we're not doing that with the YOLOv10 model. So right now, just initially by watching the video through a couple of times, so it looks like the YOLOv10 model has less false predictions. So again, we don't have any persons here, we don't have any traffic lights. Even though this is a traffic sign, it shouldn't be labeled as a traffic light. So right now, let's just play it again. We can see directly that YOLOv8 does a better job on smaller objects compared to the YOLOv10 model. And this could be because they're reducing the number of parameters and they're also having a more lightweight classification head and so on. So this is my experiences with YOLOv10. It is not as good on smaller objects compared to YOLOv8, but again, there's always a trade-off between accuracy and speed. When we're lowering the parameters, when we make the models faster, we will always lose some accuracy and so on, at least for the YOLO models when we're comparing it right now. So these are my general experiences. Like we can see, we'll miss a lot of cars over here to the left and also some of them driving to the right here on the highway. We basically just detect all of them up here at the top right corner with the YOLOv8 model, and we do the exact same thing with the YOLOv9 model, which we're going to see in just a second. So YOLOv8 better on smaller objects. YOLOv10 is significantly faster compared to YOLOv8. It is up to 1.5 to 2 times faster, maybe like 50-100% faster. So it really depends on your applications and projects if you really need to detect small objects or you prefer to have a faster model. If we take a look at it down at the bottom, again, we can see, of course, we can go in and lower the threshold more for the YOLOv10 model. We will probably get more detections. So it looks like initially that for YOLOv10, we need a lower confidence score compared to YOLOv8 to get more predictions. And that will probably also introduce some false predictions here and there. But these are actually running with the exact same confidence score just to make the comparisons as even as possible. Down at the bottom video, we can see that we detect a person here again. That is not correct. We detect an umbrella with an okay high confidence score. We even have some buses up here at the top, which is obviously cars. That is pretty easy to see. But the problem is we detect it as bus with YOLOv8, but with YOLOv10, we don't even detect these as cars. So these should be pretty clearly cars. Again, we can probably lower the confidence score, but the confidence score is 0.25, so that is still very low. Of course, these models will be significantly better if they're fine-tuned on a specific class. So if you take all the cars, label them, and train the YOLOv10 model, fine-tune it on specifically cars, it will be able to detect all these cars, no problem. These are the pre-trained models on the CharuCo dataset, and we have 80 classes. So let's just run it here and let's see if we see some other differences. Right now we also got the person detection down with YOLOv10, and we also have some other wrong ones here. So these are trucks, so label 7 is trucks. We have buses here on the right side again. Now we can see we get some trucks on the right side with YOLOv8 as well. We have the persons here, it's flickering back and forth. It thinks that this is a person, but it also does that now for YOLOv10 sometimes. So yeah, again, these models are pretty similar. You can't really just take one of them. We can't just say that, okay, now we have a new YOLOv10 model. This is the best model. It shows the best performance on the benchmark. And because of that, I'm just going to use that in my application and project. It really depends on your dataset, the problem that you're trying to solve. If you want to detect smaller objects, if you're running this on lower end hardware, so you really need the speed. If you can get away with just like 10-20 frames per second, probably even more depending on the hardware, you can get away with YOLOv8 and then have a bit more accuracy. Of course, you can always go up to the medium model, compare the medium model to the small model for YOLOv8, and you'll probably be able to get more detections. But again, you can see here, it pretty much just misses these cars. It shouldn't do that, and the confidence scores are also generally lower. But this comparison here is pretty much just even confidence score. Every single parameter, even the models here, are the exact same ones. But again, I'd probably rather go with the medium model for YOLOv10 if I were to use it over a YOLOv8 model. If we take a look at the YOLOv9 model, just to see the results from that one, it does a pretty good job with detecting smaller objects here in the top left corner. And we also get some false predictions here and there, but that is kind of expected. The YOLOv9 model, I feel like it's a bit better on small objects, also on all the other experiences, videos, and all the models that I've trained on my own. It looks better when we're actually like doing this on smaller objects. So this is pretty cool. Definitely go and test it out in your own applications and projects. I'm just going to let it run here for the video. So we have some false predictions with traffic light, person, but generally it detects pretty much all the cars. We can even see the cars at the top coming into the frame, significantly better compared to the YOLOv8 model. And again, this is a really hard edge case. This is probably like the hardest that I can come up with for a real world scenario, but it shows pretty good comparisons between all the different models, and it is the exact same experiences that I'm showing now that I've had with all the other models, even custom models and so on, that I've tested out. If you want to know how we can use these models, definitely check out my channel. I have tons of videos covering all of them, even how we can apply object tracking on top of these object detection models, how we can use it with Autolytics, train our own, generate our custom data set, run inference in a custom Python script, even export them and do optimizations. So thanks a lot for watching this video here, guys. I hope this has given you some insights into which model are the best right now. And again, there's no answer to that. It really depends on your application and project. YOLOv8 is not the best model just because it is the newest version. Make sure that you test it out on your own, and then I'll just see you guys in one of the upcoming videos. Until then, happy learning. So we also have an AI career program if you want to learn how to land AI jobs and get AI freelance work. I teach you everything in there. We have programs, all my technical courses, weekly live calls, personal help, and I'd love to have you guys in there, help you out in any possible way. You can check out the program down in the description and the community, and then I'll just see you guys in there. Hey guys, welcome to a new video. In this video here, we're going to take a look at how we can do object tracking with the new YOLOv8 model in just a few minutes. So let's just jump straight into it and see how we can do it. So we'll just jump straight into the code editor. The first thing that we need to do is import YOLO from Autolytics. These are the only lines of code that we need to be able to both run object detection and also object tracking on top of it with Autolytics. We create an instance of our YOLO model. We can either specify YOLOv8 Nano or YOLOv8. We have the Nano, small, medium, large, X large model. You just need to swap it out here. So that's large, medium, small, and Nano. Right now, let's just go with the Nano model. Specify YOLOv8. It will download automatically. We create an instance of our YOLO model. Then we can just call either model.track or model.predict directly on our YOLO model. Then for object tracking, we just need to specify our source. So that could be an image, NumPy array, or our webcam. Could also be an RTPS stream. We specify that we want to save the video stream, show it directly once we're running the program, and we can also set the confidence score. So right now, let's just go with 0.2. This will return a results generator. You can extract all the bounding boxes, confidence scores, class IDs, and so on directly from that and use it in your own applications and projects. Let's now go in and open a new terminal. First of all, I'm just going to activate my conda environment. Conda activate, Python 3.9, that's only what I'm using. Then you need to go in, pip install Autolytics. If you already have it on your computer, make sure that you upgrade it. So we have the newest version with YOLOv8 available. I already have that on my computer, and we can just run this Python script. So YOLOv8.py. We run the program. It should open up my webcam on the MacBook here to the left. So here we have the wrong index. Let's try with a 0. So now we can see that it pretty much just opened up my phone here in front of me. So I'll just pull up my webcam from my MacBook to my phone. We can see the mouse here, laptop, also a person. We have an ID. We can move the mouse around and we still keep track of it. So this can be used for different kind of systems and so on. We also have the keyboard, person. I can move it around and we have ID 15. Even though I'm moving around, this is running on a CPU with the Nano model, so the YOLOv8 Nano model. We have videos here on the channel how you can fine tune your own custom models, take your whole data set, set up the computer vision training pipeline. You can use those models directly. You just need to swap out the path here. You're good to go. You do object tracking with YOLOv8, YOLOv8, all the different YOLO models from Autolytics in just a few lines of code. So this is pretty cool. It's running very fast here. We can go inside the terminal and see that we're running around 80 milliseconds, so that's 13 frames per second on a CPU. So that's pretty much it for this video here. This is how you can do object tracking in just a few minutes. Very easy, few lines of code. You can use it in your own applications and projects. Thanks a lot for watching this video here. Hope to see you guys in one of the upcoming ones. Until then, happy detecting. If you want to get into an AI career, you should definitely check out my AI career program. The program is basically all my experiences from how I went from an average student to where I am today. The program consists of 3 main categories. We have my technical courses, my personal branding course, and then the AI career path. We have a whole community in there with like-minded people supporting each other, and every week we will have weekly live calls where I support and help all of you guys. Over time, more courses, resources, code templates, and so on will be added to the program. You will give lifetime access, so the sooner you join, the more value you will get for your money. Let me help you take your AI career to the next levels. So in this video here, we're going to talk about model pruning, how you can actually go in and reduce the size of your model and still keep the same accuracy, the mean error position and so on when you're talking about object detection models. But you can pretty much use an arbitrary PyTorch model out there, prune it directly, which just means that we're reducing the layers and also some weights. So we're just removing redundancies, removing redundant weights and layers in our models. So this can actually reduce our model size with up to 10-20% without losing any accuracy at all. In this video here, we're specifically going to test it out on a YOLOv8 model. You can use any of the YOLO models from Ultralytics, any PyTorch model out there. It is the exact same method. You just have to load in the model and call a couple of functions. You're good to go. We can do benchmarking, do a comparison before pruning and also after pruning. So let's just jump straight into it and see how you can do model pruning on PyTorch models. So to start with, let's just go inside the Ultralytics documentation. If you go inside the models tab, we have all the different object detection models, segmentation models, and so on available over here in the left. You're going to use the YOLOv8 model. We have a bunch of videos in here as well. You can see the comparison tables here. These are the benchmark on the CharuCo dataset. We're also going to see the new YOLOv8 model, which is significantly faster. But we basically just want to go inside our layers and individual weights from our neural network. So we want to go and use statistics to figure out what weights does not really affect our output at the end, because again, we might have some dead weights just sitting around here and there, and we can just basically just skip them, reduce our network, and then we can increase the speed of our model because our model size will be significantly smaller, and that's going to like speed up the whole model, make it smaller, run fast. So it's pretty much just free to do, and we won't really lose any accuracy. Of course, you can still like just bump it up, like just reduce 50% of the weights in your model and you will start to lose accuracy, of course. So we need to figure out the right balance with how much pruning we can apply to a model before we lose accuracy. But to pretty much all models out there, we will be able to apply some kind of pooling. So in here, we can basically just see the model architectures and so on. This is just how we can pull it, but it's really easy to work with. It's just a few lines in code. So let's just jump straight into the code editor and actually see how we can do it. I just used the YOLOv8 model just for simplicity, but you can use any object detection model, segmentation model, any model that you implemented in PyTorch. You can just load it in with PyTorch. We have the PT files. You can create your own custom networks where you basically just have it layer by layer implemented, and then you can apply pruning after that. So first of all, we need to import torch from PyTorch, and we also have this nn.utils.prune. And then we can import that as prune. So this is the main functionality that we're going to use, and they have some different algorithms, statistical algorithms that goes in and calculates how does the weight, individual weights and so on, how does it affect the output of our network. Then we import YOLO from Ultralytics. We set up our function to prune our model. So the function input here is the model that we want to prune and also the amount. So right now the default is just 30%. It's probably a bit in the higher end. So let's just go with 10% to start with. We can always like increase it when we're calling the function. Then we can run through all the modules inside of our model. So it's basically just going layer by layer. Right now, we're just checking if each individual layer in our model is a convolutional 2D layer. You can actually choose the specific layers that you want to go in and prune. So it could be in the backbone, in the neck, or in the head. So depending on if you want to have like just standard artificial neural networks. So that will be linear layers, convolutional layers, 1D, 2D, 3D, and so on. You can just specify that in here. You can even just go through all the layers instead of just checking if the instance here is a convolutional layer. But right now we're just checking, we only want to prune the convolutional layers in our YOLOv8 model. Then we can go ahead and call prune.l1_unstructured. So we have a bunch of different statistical methods that can prune our models. So the most common one here is the L1 unstructured. So it's just calculating the L1 norm. So that's just like a metric that we can set up. And then the value, the absolute value with the lowest L1 norm score, it is basically just set to 0, so we just reduce that weight. So the L1 pruning is just on individual weights. If you want to prune like full layers and so on, we can also do that. And we even have random pruning as well, where it's just going to like randomly choose some weights in your model and then go in and prune those. Pruning can also help with generalization, so the model can be more robust and so on, because could be that you have some overfitting, then you can go in and prune your model, and it might actually like go in and help with that and reduce the overfitting in your model, because we just randomly remove some weights. There's also the L2 norm. So that will be like on a module level, so the whole layer by layer that we can go in and reduce the weights in there, but also just whole layers in general. So it really depends on what you want to try out. You can test out all the different methods. Instead of L1, you can just specify L2 and so on. You can find that in the PyTorch documentation. But right now, let's just go with the L1 norm. Then it's just going to set the lowest values equal to 0. So the 10% lowest L1 norm values, we just set that to 0 and reduce the weights by that. Then we can just go in and remove each individual weight in our module, depending on the L1 norm scores that we have calculated. So this will be returning our pruned model. We're pretty much good to go now. This is everything that we have to do. We can just call this functionality from PyTorch. Again, it's implementing PyTorch, so we can take an arbitrary PyTorch model as well. So now we're going to set up our model. We're just going to use this YOLOv8 small model, and we just have the instance YOLOv8 small. You can choose medium, nano, and so on. You can find all the details on the Alteryx documentation. We can even go in and take the YOLOv10 model as well. But let's just take the small model, the YOLOv8 small model. We have the CharuCo 8 YAML dataset. So this is what we're just going to do the evaluation on. So we can calculate the mean average position before and after we have done the pruning. You can use your own custom dataset in here as well. So this is basically just how you can evaluate it with Alteryx. If you're doing evaluation with PyTorch and your own models, you just need to call that functionality. So right now, before we do any pruning at all, we're just going to get the results. So we get the mean average position of our pre-trained model. You can also have your own custom models. Just specify the path to your custom model that you have trained. Then it's going to open that up. You can have your own custom dataset with the YAML file to your dataset folders. And then you can do it perfectly fine on your own dataset as well. So that might be a bit more helpful if you're trying to solve for some specific things. Then we go and extract the PyTorch model from our Alteryx model. So we just call model.model and set that equal to a PyTorch model. Then we can print the model so we can see how it looks layer by layer. Then we can see how many convolutional layers we have and all the other different types of layers. So we can go in and check for that in our pruning function. If we scroll a bit further down, then we can see that we can just print pruning started, and then we can call a function that we implemented up at the top. So prune model, we throw in a PyTorch model. Again, you can take an arbitrary PyTorch model, and then we need to specify the amount. So we're going to prune it by 10%. Then we're just going to print that our model has now been pruned. We extract the PyTorch model, or basically just set our Alteryx model equal to our new pruned torch model. And after we've done that, we can go in and save our model, but also run the evaluation again, so we can do the comparison before and after. So this is pretty much everything that we have to do. Then we can just save it. We just save it with our PT file. So this is just PyTorch that we're doing it with. And we can then go down, load in our model. So we just save a new file with the prune model. We load in with Alteryx again, just to show you the whole pipeline and how you can use it in your own projects and application. And then we just do another evaluation run. You can also go in and fine tune your prune model. So instead of using the pre-trained model, you can just prune the pre-trained model and then train it on your own custom dataset that might have some advantages and so on. So you can just test that out for your specific use cases. So this is a really cool tip that you really need to know if you want to deploy models into production, because it has a really significant impact on both the inference speed, but again, also the cost over time. So let's say that we are able to run like 8 frames per second and we can reduce it by 20%, then we pretty much can squeeze probably like 10 frames per second out of a model instead, or basically just have it running 20% more efficiently. So let's just go in and open a terminal now. I'm going to open up my Anaconda prompt. There we go, and we can just run our pruning. Let's just run it now, and we'll be able to see all the results down in the terminal. So first of all, again, we run the evaluation after we've loaded in the model. Right now, we're just using it on the CPU. We have this CharuCo 8 dataset, so it's not really that many images that we have, and then we print out the model. So if you just scroll up to the top here, we're going to have them side by side with the comparisons. So this is the whole YOLOv8 model, layer by layer. We see all these convolutional layers, and these are the ones that we go in and prune. Let me check if we have some other. We have some bottleneck here. So we have some activation functions after that. So it's mainly just consisting of convolutional layers, at least in the backbone. But this is the first evaluation that we're doing. We can take a look at the mean error positions. So they're pretty high. We can see for a person, we have a bit lower mean error position. We can see the precision, recall, the number of instances, and again, also the images. So we don't really have that many images in our CharuCo 8 dataset. So definitely test it out on your own as well. So we see the mean error positions here. They're pretty good. Let's now go down and do the comparison and see how much is it actually like dropping by just doing pruning with 10%. If you just take a look at the overall mean error position, it is 0.72. So let's just round it up. So 0.72, remember that. We have the whole model architecture that we're just printing out. You don't really need to do that, but then we can see all the individual convolutional 2D layers that we are pruning. Just scroll all the way down to the bottom. And now we can see that we get some sequential models here with our convolutional layers. So now we're pruning a model. Our model has been pruned. We're saving a model. And again, our prune model has been saved. We can then load it in again and do the exact same evaluation. We see pretty much here, we're good to go. The elephant here dropped a bit, but let's go in and take a look at the overall mean error position. So right now we can see that it actually like dropped significantly. So from 0.72 to 0.60. So this is actually like a pretty significant drop that it's doing in this example here. But again, it's also a very small data set. And we pruned it with 10%. Let's just try to bump down to 0.5 and let's rerun it again and take a look at the results. So I've done this on both custom data sets, custom models, and so on, where it doesn't really drop. Probably the highest that I've been able to squeeze out is 20%. So let's see how it works out now. So now we get 0.72 if we only prune it by 5%. Looks pretty much the same as we had before. So right now we're pretty much getting the exact same mean error position, even though we're pruning it with 5%. But this is also still pretty important. Like, reduce the model with 5%, we make it run faster. It is also smaller and we don't lose any accuracy at all. We just need to call a single function. So this is just something that you need to have in your pipeline and know about this tip and trick. Let's just try to bump it up to 20% here just to end it off, just to see how bad it is, because right now after that we dropped it by 0.6. Let's see here. Get the results 0.37, so that's pretty bad. So again, it really depends on your data set and also your model that you're testing it out. Either you're doing it before training or fine-tuning on your prune model, that you can also do that just by reducing the weights and so on, if you want to have a model that can run significantly faster. Again, as I mentioned before, I've been able to squeeze out like 20-25% without really losing that much mean error precision, probably like 0.01 or something like that. So this is a really cool tip and trick that you need to know when you're training your own computer vision models, either for segmentation, object detection, and all those different tasks. So I hope you have learned a ton from this video here. Definitely going to use this in your own application and projects. And then I hope to see you guys in one of the upcoming videos. Until then, happy pruning. Here we get a confidence score of 0.81. We're detecting the mock. Again, we're detecting the mock. We're drawing like really nice bounding boxes around the mock, and they act like really close to the ones I drew in RoboFlow. Hey guys, and welcome to a new video in this neural networks and deep learning tutorial. In this video here, we're actually going to create a small project where we're using the YOLO-v5 neural network, where we're going to create a custom object detector. So we're going to do everything from scratch here. It's actually like really easy to set up. I'll provide the Colab notebook, so you can actually just go to my GitHub link in the description. Go get the code, train your own custom object detector. I'm going to show you from scratch how we can actually generate a data set, how we can annotate and label the data set, drawing bounding boxes and so on, how we can load in the data set into Google Colab and then train our YOLO-v5 neural network to do object or like custom object detection. But first of all, remember to join Discord server. I'll link to it down in the description here. You can join the channel, chats about computer vision, deep learning, AI, and so on. You can also become a member of the channel if you want to support the channel with a small monthly fee. Everything will go to create more and better quality content here on the channel. Also, if you have some problems in your own projects or applications, you can also become a member of the channel and I can help you out and guide you in the right direction. So thank you guys. So first of all here, we're just going to start in the YOLOv8 GitHub repository here from Ultralytics. So here we can see the nearest model here of YOLOv8. We can get a short description of like what is going on, some documentation, how to set it up, and what different kind of like libraries and frameworks can we use it with.
So here we can just see that the YOLOv8 is a family of object detection architectures and models pre-trained on the CharuCo dataset. And then we can actually use transfer learning to train it on our own objects and so on. There's a lot of different kind of variations of the YOLOv8 models. We can use some like small models, large models, depending on your application and also the complexity of your objects that you want to detect in your images. We can see how to install it here. We can just like pip install it from the requirements here from GitHub. We can see inference here, how we can actually like implement and deploy the models that we have trained our YOLOv8 model on, both with OpenCV, NumPy, Pill, and so on. So basically we can just load in our model by using PyTorch, and then we can just have our images. Then we can just call model and then pass in the image into that model, and this will actually like be the result. And then we can just print the results. We'll get the bounding box of the objects that is tracked or like detected in the image. So in another video, I'm going to create another video where we're going to create a project. We're going to load the model into OpenCV so we can actually like do live object detection where we're tracking around objects from our YOLO model around in the image frame. So also just to show you how we can actually like implement and deploy this in our own projects and applications after we trained it on our custom data set. We see there's a lot of different kinds of tutorials here on the GitHub as well, both for inference training, but also some tutorials here how to train a custom dataset, as I'm going to show you throughout this video. We can see tips for best training results, weight and bias logging, how we can actually like log those during the training of our neural network. We also have some multi-GPU training, RoboFlow for dataset labeling and active learning, as I'm going to show you as well. So we're going to use RoboFlow to actually like upload our dataset too, so we can then label it and annotate our data, so we can actually like draw bounding boxes around all the objects that we want to detect in the image frame. So then we're going to generate our data set with RoboFlow. We're going to load it into Google Colab, train our actual like YOLO model here on the GPUs from Google Colab, and then we can actually export those models after we have done like validation and also seen the results of our object detector. We can also use transfer learning with frozen layers, some hyperparameter evolution, and so on. We can see the different kind of environments. We can see Google Colab, Kaggle, and so on, integrations. So, and then we can also see all the different kind of models down here. So we both have like different types of YOLO models if you want better performance, or if you just want to have it to run faster. So there's a trade-off between like accuracy and also the speed. So you need to choose the model that fits best for you. Down here we can see the metrics for all the different kind of pre-trained models here. In this video we're going to use YOLOv8 and the small model. We can see the pixel size that it takes as input, and also all these different kind of metrics here, both the speed and also the accuracy, the number of parameters, and so on here. So we can test out different kind of models depending on your application and also how complex your application or project or objects are. Also, if you want to detect multiple objects in your image compared to only like one object. In this video here we're going to detect a mock, so we will only detect one object in the image frame, but you can just have multiple objects. You just need to label them with RoboFlow, as I'm going to show you. So now we're jumping straight into RoboFlow here. You can just go in, sign up, and get like a free trial. Then we can use this mock detector. I already created a project for that. Then we can go into the overview here, see some different kind of things, and also the upload. So we can upload images, new images from our dataset. We can go in, annotate them as well. We can see here that I've already annotated or labeled all these images. We can then split it into a validation and training set and also a test set. But if we just go into one image here, for example, we can see that I have drawn this bounding box here around here the cup. When you go in here, you can actually just change it. We can just go in here, for example, and then we can generate the tool. Then you just get this tool up here, and you can actually just draw a bounding box here around it. Then you get up some couple of different kind of like options up here, so you can just save this class. So in this example, I just called it mock, and then when we hit enter, it will just create this class here called mock. If you had multiple objects in the image frame, for example, if I wanted a person too, so we can create a new class called face. And then when I hit enter, we will just create this face class here as well. And then it will just do all the stuff for us. It will generate the different kind of files that is needed, like the format files needed to actually like train the YOLO model. But this video here, we're just going to take the mocks. I already did the annotation on all the images here, so we can just go through them. We can see the bounding boxes here that are drawn around this mock that we want to detect on. So here we just have 70 images in our test set. So this is actually like fairly good. We'll get some really nice results only with 70 images. You can also generate more, but this is just to show you guys how we can actually get started with creating a custom object detector with YOLOv8. So after we have actually like uploaded our images and annotated them, we can go into our dataset, and then we can just generate a new version of our dataset. I've already created one here, but now we're just going to create another one just so I can show you how we can actually like do it. First of all, we just need to choose like the train and the test split. So in this example, you can just go up here and rebalance it. So right now we're just choosing like 20% for validation, and all the other images, we want to use that for training because we don't really have that many images in our dataset, and we're not going to use anything for test because when we're going to test it, we're just going to use our validation images. But if you had like several hundred images, you can split it into another, like, so you have actually have more validation data and also test data and so on. But in this video here, we're just going to go with 70 train images and 8 validation images. And even though we have this low amount of number of images in our training set, we will still get a really nice object detector, as you're going to see. So here we're just going to hit save. So this is our train test split. Then we go down here to the pre-processing, and we can actually to choose some different kind of pre-processing step. So right now it just also automatically do auto orientation and also resize this. So resize the images to 416 by 416. So it actually this is just input size to the YOLO model that we need to. We can also add some other different kind of like pre-processing options if you want to do that in your image. For example, we could grayscale all the images before we're training our neural network to make it faster and also to reduce the complexity a bit. If you, for example, right now we have this mock here which is yellow, so we might benefit from having actual like RGB images compared to grayscale images when we're going to do this object detection, at least when we have this low amount and number of images. So after we've done the pre-processing, we can go down and choose some different kind of augmentation steps. You can just go in here, choose, for example, we want to do horizontal flip, or if you want to do vertical flip in some way. It doesn't really make sense in this example because we don't want the mock to be on the upside down. So in this example, we're just going to use flip as a data augmentation method. And also the rotation here, we can choose the angle here that we want to rotate our images on here as well in our actual augmentation. And it's really important that you use augmentation if you have a low number of images. In this example, we only have 70. But as you're going to see, we're going to get a lot more images when we're actually using augmentation, and we will also get more variation in our images that we're going to train our neural network on. Just to show you some other different kind of augmentation options we have, we can also rotate our images 90 degrees. We can crop them if we want to crop our images, or zoom in and out if we want to have our models generalizing more on that. If it really doesn't matter where the object is in the image frame. In the depth, for example, we can use crop. We can also shear, grayscale it. We can play around with some of the different color spaces. We can flip it, crop it, and so on. So we can do a lot of different kind of things. We can also apply blur and noise on the images if we want to have a more robust solution, or a more robust neural network when we're actually training on neural network. So here we're just going to hit continue. We're going to go with flip horizontally, and also we're going to rotate it between minus 30 degrees and plus 30 degrees on our images. So now we can just go down. The last step is to generate our actual data set. We need to choose the maximum version size here. So again, for the free version, you can get up to 3x the number of images that you actually have when you're applying data augmentation. If you had some other different kind of plans, you can see you can get a lot more images here from using data augmentation. But right now we're going from 78 images up here from the source images to 218 images after we have actually applied data augmentation on our images, so we create a more robust and general model. So now we're just going to hit generate, and it will actually generate our whole data set. We can just go up here, call it mock dataset 2. We're going to save the name. It just processes and generates the images here. So again, right now it took 5 seconds to generate the whole data set here with the data augmentation and so on. We can also see all the different kind of images that we have. The 216, these images is actually flipped. And we can also see here that we have these images that is rotated. So right now we have all our images in our data set. We have 208 images in our train set. We have 8 images in our validation set. So this is not really that many images in our validation set. But as we're going to see when we're going to test it, we're still able to detect the mocks in our actual images, even though we have this only 208 images that we're training on. But But right now we can actually like both train here in model here, but it actually costs money. But we can just go into Google Colab. I can show you how we can train a custom YOLO model with this dataset here from RoboFlow. So right now we have our dataset generated. Then we can just go in here and export it. So now when we export here, we can just go into show download code here. We're just going to choose the format, and in this format, when we actually like training YOLOv8, we need this YOLOv8 PyTorch TXT format. Also, if you're using some datasets from the internet or like from Google and so on, and you've just downloaded to your computer, make sure you know like what format it is on. You can actually like convert it here in RoboFlow as well. If you just upload the dataset, you can, for example, convert from Pascal VOC format to YOLOv8 PyTorch text format, so you can actually train your custom YOLOv8 model. You can both download the dataset to your computer in a zip file, or you can just show the download code that we can then directly get in Google Colab and download into our notebook. So here we're just going to show the download code. When I hit continue, it will just start with start out with zipping the files, and then it will download them. Then we just get this code snippet here. We can just copy this. We will get an API here that is just like a private API key here. So it just goes in, gets the dataset from RoboFlow here, and then we can actually like store our dataset and this variable in our code. So this is all we have to do in RoboFlow. We have downloaded the code, and now we have this code snippet that we're just going to copy paste. And then we're going to copy it, and then we're going to paste it into Google Colab. So now we're jumped into Google Colab, and now we're going to do the whole like update detection, custom update detection with the mock. So we started from scratch. We generated the images on our computer, and then we just used RoboFlow to do annotation, label the images with all the bounding boxes. We did some data augmentation, generated a data set, and now we have copied the code snippet, so we can like download our data set into Google Colab. As we can see here, we have no files in the directory right now, but when we actually like download both YOLOv8 and also the dataset, we will get all of these things over here in our folders. So right now we're just going to set it up. First of all, we're just going to clone the GitHub or like clone the repository YOLOv8 as I just showed you on the GitHub repository. So we're going to clone that. We're going to install the requirements. So these are just the code snippets from the GitHub tutorial from YOLOv8. Then we're going to import Torch, OS, and also IPython display, so we can then display the images later on with the actual like update detection of the mock. If we're actually able to use CUDA here, we're going to use the CUDA device or like a GPU to actually like train our custom YOLOv8 model. You need to make sure you go up to runtime, change runtime type, and then you need to choose the hardware accelerator here as the GPU. Then it will train the model on the GPU, and it will take it will just go way faster than using the CPU. You wouldn't be able to train your custom YOLOv8 model on a CPU. So just use the GPU here in Google Colab. So we're going to run this blob code. We will download YOLOv8. We're just cloning the repository. And then when we go into the files over here to the left, we can see we actually like get this YOLOv8 repository. We see both the data, the models, some requirements that we're going to download, how a training script, a validation script, and so on. And also to get up some setup detection, so we can actually like do detections with just a Python script. We just call it with some different kind of like arguments to that Python script. So now we're just going to go in here, go to the next block of code. So now we're just going to open up like the RoboFlow here. So we're going to create our RoboFlow. We're going to use the model format, which is YOLOv8. So this is just the format that we stored our dataset in, and also the notebook here will just be Ultralytics. We're going to run this block of code after we've completed the first one. And now up here we can see that the setup is complete. We're using Torch 1.10.0 plus CUDA here 11.1. We also get the information about what GPU are we actually like training on. So now we're going to set our environment here to the dataset directory. So it will just be content/datasets. So this will just be the folders that we have over here to the left. So we're going to set our environment up, and then we can actually like just go down here and paste in our code snippet that we got from RoboFlow. We already installed RoboFlow, and we have also already imported it. So we're just going to delete those lines of code. This will be the private API key. You can also just use it if you want to use the exact same detector or like the mock detector as I did. If you don't want to generate your data set beforehand and you just want to test this mock detector here on your own images and so on. So then we're just going to set up the project, And then we're just going to take the data set here. So we need to choose the version, and the version here that we're going to use is 1. So this is the first version of our mock detector, because I already had one, which will be version 0. So I already had one, but we created a new one that we're going to train on. So now we're just going to hit enter, or like we're just going to run the flow of code. We can see that we're loading the Robo workspace, we're loading the Robo project, then we're downloading the dataset here in the zip file into content/dataset/mock detector 1 to YOLOv8 PyTorch here. We can also see the progress bar. So now we have actually like downloaded, and we also extracted our dataset. So if we go over to the folder to the left, we can now see that we get our datasets folder up here to in the top. We can see we get mock detector 1. We can go down here, we can get all the training images, all the images, and also all the corresponding labels with the bounding boxes inside of that. We also have our validation images, so these will just be the exact same ones, but in the validation we only have 8 images to show. If I'm going to open this one, we can just see the images that we actually have that we're going to do validation on. But this is all we need. We also get all the labels here. If we just go down, we can just take the validation labels. So if we go in here and open this file, we'll just get the bounding box that we have actually like annotated in RoboFlow as I showed you. So we're going to close the folders here again. So now we have our data set. Now we can just go in and train the YOLO model with this training Python script that is provided by YOLO as well on the GitHub, and that we cloned into the repository. So we're just going to run this Python training script. Then we're going to set the image dimensions, the batch size that we want to use, the number of epoch that we actually want to train our model on for, and then we need to specify the location of our actual data set. So this will be dataset.location/data.yaml. So this will just be, this will actually just be the directory for the labels of our data set and also the images. Then we need to choose the weights. So in this video, we're just going to use YOLOv8S. So this was the small model that we're going to use. There's a smaller model, one smaller model, but in this video, we're just going to use the small one. We just have the PT here, and then we need to specify cache, because we just want to cache the images in the GPU when we're training, to actually speed up the process when we're training it, and also benefit from it when we're running 100 epochs. So right now we're just going to run the script, or run this block of code. It will just train the whole YOLO model here. So again, we can see that it's just downloading some different kind of stuff. It sets up the hyperparameters with the learning rate, momentum, weight decay, warm-up epochs, and so on, and also all the other different kind of things. It will download the weights, the biases, and then it will actually train the YOLO model. So now we can see down here that it has downloaded, and it has now started training the neural network. So first of all, we just get a summary here of the model. So this will just be all the convolutional layers in the actual YOLOv8 small model, as we can see. So we can go in and get the exact dimensions of what is going on, all the layers. We have some convolutional layers, some upsampling layers, some concatenation layers, and so on. But if we go down to the bottom here, we actually get all the epochs that we're running. So now the training here has actually started, and we just get out this information about the GPU memory that we're using, some of the different kind of object boxes, the classes, the number of labels, the image size, and also the precision over here to the right. So these values here, 0.5 and 0.95, is the confidence scores of the bounding boxes that we're actually predicting on our images. So these values here should actually increase over the number of epochs. We can also see that it actually takes around 7 seconds to run through each of the epochs. So it doesn't really take that long time when we're using the GPU to train a YOLO custom optic detector on a dataset that we just created by ourselves, and we actually will end up with some really nice results. So this just takes a couple of minutes to train the neural network here, and then we can just do predictions on it later on. So now your custom YOLOv8 model here is actually done training. We can see that 100 epochs here completed in 0.23 hours. We can see that the optimized script here for both the last weights and also the best weights. So we can actually go in here, and then it is validating the best weights that it found during training. We're also going to see the training results down here in a second, but we can see we get a model somewhere here of 213 layers. We can see all the different kind of parameters and so on, the images, labels, and so on. So we can see the results are saved to runs /train/experience. So if we go in here, we can actually go into our YOLOv8, then runs, train, and then into our experience, and then we just get all the weights here actually. So we both get the best model and also the last model
during our training. So when we're going to do inference and do predictions on new images, we're just going to use the best model that it found during training. We can also get some other different kind of information about the results, training badges, validation badges, some labels, confusion matrix, so we can actually see the results. But here we're just going to go out of the folders here again, and then we're going to use TensorRT to actually log the different kind of metrics and values that we had during training. So here we're just going to load in TensorRT, and then we're just going into log here and then runs. So we're just going to display and show all the training results that we got during training of our YOLOv8 custom object detector. So here we're just going to run this block of code. It will then launch TensorRT, and then we'll get all the different kind of metrics and graphs up here of our training results. So as we can see here, it is loading up. We get all the different kind of metrics. I'll just zoom out here a bit so we can see what is going on. So this is all the metrics that we got from the experience. Down here, it will just be the first training. So we see here we start at epoch 0, and then we go all the way up to 100 epochs, and then we can see the results over time. So we can actually see here for the precision, or like this metric MAP with a confidence score of 0.5, we actually have a really nice convergence here at the end where we get a value of 0.99.5. So we have a really high accuracy on this metric here. We can also see for the confidence score of 95% confidence here that it is actually like a bit more fluctuating here in the training process, but we can also see that we get a really nice result. We end up with values of 0.80 in the precision. We can also see the precision over here. It also converges towards 1 at the end here after around 50 epochs. It is the same with this metric over here to the left, MAP. We can also see it converges after maybe 40, 50 epochs, and the same down here with the recall matrix. We can also see these results. So these are just the training results that we got from training our actual neural network, and it only took like 10 minutes, 15 minutes to actually train this whole neural network here on our custom dataset. You can do all of it yourself and so on, and use the GPU here in Google Colab. Everything will be down in the description. I'll link to my GitHub. You can go get all the things and also the dataset from RoboFlow. So now here we can also see the box loss here. It keeps decreasing. Our loss function here is actually just constant, and our object loss also just decreases over the number of epochs. So the losses here, we want to get them as small as possible. As we can see here, it actually still decreases a bit after 100 epochs. We could maybe run it for 120, 150 epochs, but again, we're still at a very, very low loss, so it wouldn't really matter that much. And it's also just the box loss, so it would just be the precision of the bounding box that we're drawing around the object, and not really if we can detect the object or not. So down here, we're now going to do predictions. Again, we have a prediction script provided by YOLO. So here we're just going to run this detection Python script. We set the weights of the neural network or the model that we want to run the predictions on. So again, we just go into our train, runs, trains, experience, weights, and then we're just going to choose the best weights from our whole training process of 100 epochs. We're going to set the image dimensions and also the confidence score. So if we actually have a confidence score that is over 0.1, so if there's a more than 10% chance that this is actually a mock, then we're going to say that this is actually a correct prediction, and then we're going to display it. We can play with around with this confidence score here. We can set it to 20%, 30%, 50%, and so on. But right now we're just going to maybe go with 0.2, and then we're just going to choose the source here of our images that we want to do predictions on. And again, we don't have any test images, so we're just going to run our predictions on our validation images. Then down here, we're just going to have this for loop where we're just running through all the images in our actual detections. So first of all, we just run this block of code. It will do the detection on all the images that we have in our validation data set. So again, we had around 8 images, as we can see here. So now it has done the prediction on all those images, and then we can actually go down here and display them. So right now we just only have 8 images. We can see the results are stored to runs /detect /experience, and also the speed here and so on. So we get all the information here, how long it took to process each of the individual images, and also how many mocks did we actually detect in the image frame. So we can see here that in all the images we were able to detect 1 mock. If we had maybe 2 mocks in the image, it will probably return 2 here, and it will draw perfectly bounding boxes, perfect bounding boxes around those mocks as well. We can test that when we're actually going to deploy the neural network. So make sure you hit the subscribe button and also the bell notification, so you will get a notification when I upload a new video where we're actually deploying these YOLO models here with OpenCV. We're opening up the webcam,
moving the mock here around in the image frame, trying to track it around in the image frame, and also maybe have multiple mocks, so we can actually see, okay, we have only trained our neural network on images with one mock. Is it actually able and capable of detecting multiple mocks in an image, and how reliable and robust is the solution? Even though we only have 200 images, or like we started out with 70 images, we augmented the images, so we now have 200. Then we trained a model here for 15 minutes. So it took like 20-30 minutes in total, and then we actually have a custom object detector that we can then use to deploy in our own projects and applications. But now we have run all the predictions here, we've saved the results. So now we can actually just go down here and go into content, YOLOv8, then runs detect experience, and then we're just going to take all the JPEG files inside of this folder, and then we're just going to run through and display them with the corresponding bounding boxes. So now we're just going to run this block of code, and it will then display all the images here in our validation set. I'll just scroll up to the top. So now here we can actually see it detects a mock up here to the right. We can't really see the confidence score here because it's out of the image frame. But here we're actually detecting this mock, even though we can only see this mock here because my hand is kind of blocking the mock here in the image. But we still get a confidence score of 70% in this image here. So it's actually like a really nice object detector that we created, but only having 70 images. So this is really efficient and really robust neural network and model that we can use. Here we get a confidence score of 0.81. We're detecting the mock. Again, we're detecting the mock. We're drawing like really nice bounding boxes around the mock, and they act like really close to the ones I drew in RoboFlow, where I act like annotated and labeled the images with the bounding boxes here as I showed you. Again, we can see we're able to detect the mock in all the images here, but we get a lower confidence score if we can't see the whole cup or like the whole mock, as we can see up here in this image. So here we will have a lower confidence score than compared to, like, for example, if we can see the whole mock in the image. But again, we're going to save the model here, as we can see here, so we can go in, runs, train, experience, weights, best. We're just going to take the best model, and then we're just going to download it into Google Colab. We can then download it from Google, or like from Google Drive here, from our files, and then we can just deploy them in our own Python script with OpenCV or some other different kind of frameworks or libraries for loading in like NumPy arrays, and then just displaying them with a live webcam, for example. So we're going to do that in another model, in another video. So we're just going to save the model here. We can see that we're downloading the best model. It will download it to your computer. We can just download it, and then we can import it later on in our own Python script. So that's it for this video here, guys. We've been through how we can actually like generate a data set, label a data set with the different kind of bounding boxes, how we can import that data set into Google Colab, get a custom or like get a YOLOv8 model, train the YOLOv8 model on our data set, and then do predictions on new data that it hasn't seen before. So it took 20-30 minutes. We created a custom object detector. You can use arbitrary objects. You can have multiple objects in your image frame. Like you can actually have just 100 objects that you want to track in the image frame. You just need to label all the objects that you actually want to detect, and then you need to train your model on that. So it's really nice, it's really cool, and we're going to create some really nice applications and projects with it on this channel here in the future. So again, make sure to hit the subscribe button and bell notification under the video, and also like this video here if you like the content and you want more in the future. It really helps me and the YouTube channel out in a massive way. As we can see down here at the bottom, it has now downloaded the best model. We can just show it in the folder, and then we can just import this PT file here later on in our own Python script. So if you're interested in other tutorials about deep learning, computer vision, and so on, I'll link to one of my tutorials up here, or else I'll see you next video, guys. Bye for now. So in this video here, we're going to talk about how we can create AI, machine learning, and computer vision system. We're going to talk about different phases from going from a business use case, a project with a bunch of requirements, to act like creating a system that we can scale and so on. This is where most of the work is. It is really important that we focus on act like planning out the architectures, the different software, frameworks, and so on that we're going to use, but we also have multiple different phases when we are creating computer vision from scratch into an end solution that can act like solve business use cases, one that we can both deploy, test, and also scale to multiple systems and so on. It is not enough that we just have it working in our own local environment. You probably, if you're working with computer vision and so on, it is very easy. Just use Autolytics,
object detection models and so on, and we can pretty much have an object detection model up and running on a video stream on our own local environment in pretty much like 30 minutes. We actually need to know how we can go from a Jupyter notebook out in the real world and also scale our systems, because this is the most essential thing if you want to apply and solve business use cases. At the end of the day, everything is about making money, solving problems, like helping out other people and so on. So we take a problem, we solve it, and then we get paid for it. And this is pretty much like what's pushing technology, but also just how the whole world works. Most people, they're focusing on the theory, knowing how to change the layers in a neural network, all the hyperparameters, what is the math and statistics going on behind the algorithms, where it's more important to know the framework, how to deploy the systems, how to come up with a software system so a model is running. Because when we have AI models, machine learning models and so on, it is just a very small part of the whole project, and also the software architecture in general. Yes, it is what is doing all the groundwork and so on, solving the problem. But if we can't take that, wrap a software system around it, or take a small AI model, integrate it into an already existing system, it doesn't really matter at the end of the day. So yeah, it is basically the model and the algorithm that solves the business use cases, but the model itself is nothing if we don't have the whole software system around it. So when we're talking about software systems, first of all, we need to have project requirements, business problem that we need to solve. A lot of people, they get started with software projects, AI projects and so on. They want to create AI startups as well, but they don't really have a business problem. They just have a cool model that they want to explore, play around with and so on, have some data that they have found. Yes, it is good for learning purposes and so on, but we also need to take it to the next level if you want to get out there, get a ton of opportunities, but also provide value to the real world. So this is the first phase in a machine learning, computer vision, AI project in general, but also just in general software engineering. So yeah, we have that phase. Then we have an initial research and basically just coming up with a game plan. We need to plan our system architecture, the different frameworks that we want to use, how are we going to generate the data, train the model, what can we do in parallel and so on. Like most systems, we can build up the business use cases, the groundwork and the structure for the code base in parallel with generating the data. Then we can start to explore some models, test some models out, train some models, do some evaluations. Once we have that, we both have the business use case, the ground structure for our system. Maybe we're building a simple front end, some backend systems and so on. We have the AI models, and then it's just all about gluing the different components together. So this is really important that we plan this out in our initial research, test out some different approaches, method. The first thing, when you just have the project requirements, the more experience you get, the more problems you have solved, the better you are at coming up with the initial frameworks, the software architecture, the approach to take and so on as well. But you can never come up with the best solution in the first run. So explore different approaches in initial research phase, figure out what is the best to approach and so on. It is not a bad idea to go down different directions, different paths. We just need to make sure that we're not going down the wrong path for too long. And this is happening if you're not doing your initial research, if you don't have enough experience with solving business problems and use cases. So then when we have done our initial research, we can come up with a game plan, basically just a master plan for the whole project, for the next phases, the pipelines, the approach that we're going to take, how we're going to do the planning, finish the work, glue it all together and so on, which is very important. Now we can get into the real developer work where we have implementations, code, algorithms and so on, but don't get into that phase before we have thought about it, done our research and come up with the best approaches. But if you're in the early stages of building projects, you want to learn the fundamentals behind AI and deep learning, Simply Learn can help you out. They're basically an online learning platform offering a wide array of bootcamps and different courses designed to empower individuals in their career journeys. So it doesn't really matter at what stage you are in your journey. The AI career program is particularly impressive. It is basically a comprehensive 11-month online bootcamp that covers everything from the basics to all the advanced topics, concepts and so on that you need to know before you start building these individual phases that we're talking about in this video. In the courses, you'll dive into machine learning, natural language processing, deep learning, and even cutting edge topics like generative AI, which is some of the newer stuff. It's created in collaboration with IBM, so you get industry aligned curriculum, tools, and so on, but also practical experience. You will get the IBM certificate and all of that included as well. The learning experience is top notch live online classes led by industry experts, hands-on projects for practical use cases, and a capstone project to solidify your skills. And you'll also get lifetime access to self-paced learning content. The program, it has excellent reviews from past students who have enrolled and also transformed their careers. Also, Simply Learn is reviewed and recommended by Forbes. Many have landed exciting new jobs or received significant salary increases after completing this course. So if you're serious about getting into AI or just leveling up your existing skills, this is like a full comprehensive program. Go ahead and check it out on the website, explore the full curriculum, watch some of the sample lectures, and see if it's the right fit for you. Then we do data generation. Could be image data, time series data, or whatever, but we need some initial data. Could be that the project requirements or the business problem already provide some data, so we need to do data preparation, annotation, labeling, and so on, so we have our ground truth data. Once we have that, again, this will pretty much be like an iterative phase. We will also like always add more data into our data set, retrain the models and all that. We have the data flywheel. But once we have some initial data, we can start to do some model training and also just model development in general. When we are solving business use cases, it is much better just take existing models out there, open source models, or whatever models that is suitable for your application and project. We just want to create our models, test our models as fast as possible on the actual like business use case, because if you just figure out all the way here on the initial data, it's not going to work, or we get a good indication of what is the accuracy going to be of our system, how does the model perform. We can test out way more models if we're just using them out of the box. The probability of you coming up with an architecture that is better than existing models out there is very low, but it also takes significantly more time. And when we're creating computer vision projects, machine learning AI projects, and so on, solve business use cases, could be that you are inside a job. We can't spend months on actually just trying to come up with model architectures, and especially if you're doing freelance work. If you want to get into that and so on as well, I have the AI career program. I pretty much just teach each of these phases here. How can we do it in the best way? How can we get customers, clients, land machine learning AI jobs, and so on. So definitely check that out, because most of it is actually just networking, building your own personal brand, putting your work out there and get credibility. I help with all of that in there. So once we have that, we already have a good understanding of how's our initial system performing on the data set. We can start to build the code base, also with the business logic on top of it. So we can have some assistant frameworks that we're using and then just applying the specific business logic, business rule base, and so on, depending on what system we want to solve. Let's say that we have a computer vision system with a conveyor belt. We want to count the number of objects, could be specific objects, and so on. So that is the business logic that we're applying on top of the outputs from the AI models. Once we have that, we kind of like have an initial system. Maybe you have a video stream up and running on your own local environment where it works and so on. But this again is only 20% of the work. We have project requirements, business use cases, research, come up with a game plan that is totally different compared to actually just getting a demo up and running. But then we need to do system deployment. We need to set up our system, connect the cameras to the servers, depending on if you want to have a cloud deployment, edge deployment, we have a desktop computer running or whatever, local server. All of those things we need to know how to actually deploy the models to that system. Also be able to scale it. Could be that we want to have multiple cameras over time and so on. So we need to have that in our mind while we're setting up this system. Once we have deployed the system, depending on all the optimization frameworks and so on, I have tons of videos covering that on this channel as well. We need to do system testing, monitoring, and so on, make sure that our system actually works good enough. Again, we won't have the perfect project, we won't have the perfect solution in the first run. It is very important that we have this iterative loop. We keep on improving our model, doing model optimizations, adding more data into our data set, retraining the model, and then we have this whole data flywheel. This is very important because when we're sitting in our Jupyter notebook, we're testing, validating a model and so on, doing model evaluation. We might get good performance, but it might act like drift once we take a model and put it into production. This is very often we get like model drift, data drift, and so on. It is not the exact same as we expected it to be, so we will need to do some changes, scale it to more data so our model generalizes better. Maybe we're overfitting to our training set or our test set, and our data is a bit different when we actually deploy it into production. Then we can do some minor system changes and optimizations and so on. And then again, we basically just hook into the flywheel. So after system changes and optimizations, we go in and evaluate, okay, so what is the performance? What can we do different? Can we make some changes? Can we add more data and so on? And we'll always be adding more data because now our system is up and running and we basically have a full scale deployment. Just store some images, label them, retrain the model, and we have this whole flywheel. So this is pretty much all the different project phases that we have in machine learning, AI, computer vision projects and so on. And this is basically like the best approach to follow. We have the AI models. This is only like 20% of the work. So don't focus 90% of the time on doing the model development, data set and so on. Like the data is very important because, as I usually say, trash in is also trash out. So if we don't have good data, the model doesn't really matter too much. But data is the most important thing, and then also being able to build a system around it. So now we actually have our system here. This is just the AI module of it. We also need like an UI if we want to connect that to it. We want to have databases with our backend systems. Might be that we want to have something being added over time, deleted over time and so on. We need to have APIs doing different kind of things, maybe storing it to a database, retrieving our information as well, showing it on a dashboard, which is the other part of the work. I have videos covering all of that, like how we can actually build software solutions, what you should focus on and so on, and also just architectures in general. But this is a pretty standard project pipeline for machine learning, AI, and computer vision projects. Have you ever wondered how we can build real-time, scalable computer vision systems, but also systems that can work in the real world? This is actually like a very hard problem, and when we're building computer vision systems, projects and so on, we want to apply it on real business use cases. It doesn't really matter if we have a model working in our Jupyter Notebook, we have our OpenCV window up and running with all the detections and so on. We need to know how we can actually create real world projects, how we can scale it to multiple cameras, run it in real time. How does the hardware work? How do we do monitoring? How do we connect it to databases? Build systems around it, because again, AI, computer vision and so on is just a very small part of a whole project. We need to know system architecture, software development in general. So this is a very good thing to focus on, because most people, they just focus on the model part of it, all the theoretical stuff and so on, and also probably because the universities and so on, the traditional education, they just teach all the theory and so on. They don't teach the practical stuff. If you're taking an AI degree and so on, you don't know as much about software development, how to actually deploy systems out there, how do we scale systems and so on. And most likely because like the professors and so on, the teachers at the university, they have no clue how to actually build software architectures, real software systems that work in the real world. So I'm going to create this video here. I'm going to create a bunch of videos in the future, basically just covering this, because there's a huge gap going from traditional education into the real world. There's a large gap, so we need to know this, because this is where 80 to 90% of the work is. The model side, all the algorithms and so on, like you can just have an object detection up and running with Autolytics, the YOLO models in pretty much like an hour. You can apply some basic algorithms on top of it. You do tracking, you can do object counting and so on. Just prompt Claude or ChatGPT to come up with the algorithms. Then you basically have your system up and running on a pre-recorded video file. But the hard part is to then take your model, deploy it into production, and be able to scale it to multiple cameras. If you just ask yourself this question here, I give you a problem, you need to solve it, you need to solve this for a business use case. How do you actually take your model? I'm telling you, deploy this model here to 20 systems. I want to do monitoring of my warehouse inventory, for example. I need to track all the data, need to store all the information and data and so on in the system. I want to create a dashboard, UI. I want the whole system to talk together. We can't just have a pre-recorded video working in our own local environment. And also, when you want to scale it to 20 cameras, could be that you're running 10, 20, 30 frames per second on your laptop or on your local GPU, but it's a whole nother world when we want to connect to cameras in real time, have 20 cameras working at the same time in real time as well. Like processing 20, 30 frames per second on 20 camera is a very hard problem. We need to know all the frameworks where we can actually go in and do that, because then we need synchronization. We need to take into account all the cameras, all the metadata for each camera, build the software around it. We need to have APIs for our backend system. We want to have a front end showing all the results, the visualizations, talking together with the backend, so that we don't just have a backend and a front end or a standalone AI system. We actually have these three components talking together, and it's only going to be more popular in the future. Like all systems will be built with AI, like integrated with AI into existing systems and so on. So this is really important to know. How do you take a model system, deploy it with Docker, then you can both deploy it on the cloud, locally, or in whatever environment that you want. So we need to know way more than just how to build models, because at the end of the day, also if you want to get out there and get a job, I'm teaching all of this inside of my AI career program. Basically what I'm doing, how to get freelance work, how to stand out there. Basically just put your work out there. You need to build trust, you need to build your own network, credibility for other people, and you will get a ton more opportunities. But the most important thing is that you know how to actually like solve business use cases. At the end of the day, the whole world is about making money. Like if your models is not making money, like no one is going to hire you, no one has resources to just have you sitting there, like try out a couple of layers, try to do some high parameter tuning on models, or come up with your own model, spend like 3-6 months on that. Like that's hundreds of thousands of dollars. Like no company has resources, just throw that out the window. Then we're talking about Meta, Google, and so on. Real world use cases, we need to be able to solve it, and you will stand out, because most people, 90% of people, maybe even 95% of people, they focus on 20% of the work, where they should actually like put the focus and the dedication into the 80%. Probably 80-90% is actually like systems, deploying stuff, like getting it out there. It's so easy to create these nice quick Python scripts that can do pretty much everything. But again, you can't just send this to a client or a customer. I have this Python script working in my own local environment, so it works, but that's not how the world is working and running out in the real world. So when we're talking about the different tools and technologies that we need, like for development, we have Python, C++, PyTorch, whatever framework that you want to train your models on. We then convert it to ONNX, TensorRT, depending on what framework, hardware, and so on that you're going to run it with. So we need to know this as well. You need to be very good at how do we export the model, run it into production. Depending on the hardware, the system that you're building and so on, it doesn't need to be real time. It's a cloud-based system. Most computer vision systems that I work with is actually like on the edge, so we need to run real-time video analytics. So this is pretty much everything. We have OpenCV, PIL, all those different frameworks, standard frameworks. But again, most people, they just focus on the development part, which is only 20% of the work. The hard thing is to scale systems and act like make money with your models, set up whole automated pipelines, architectures, and build software systems around it. And also, how do you communicate? If I gave you a problem, you have an AI model running, tracking algorithm, you do counting systems and so on. Yes, you have it up and running, but if I gave you the task, how do I connect it to my system? I have no idea about how your AI models work. I have my backend system here. I just want this AI feature. How do you actually take that, integrate it into my existing systems? Like most people, they would have no clue about that. How we can actually communicate different messaging protocols, how do you deploy the models, what are the best options, hardware, all these considerations. Like you should basically just have a list. It's basically just a list. When you know this, you can deploy the exact same thing, the exact same system to pretty much 90% of the use cases out there. So when we're talking about infrastructure, Docker, you need to know that, very good for deployment. Kubernetes, if you want to have orchestration, if you want to scale your systems and so on, and especially if you want to run it in the cloud. AWS, GCP, Azure, and so on for cloud-based solutions. But again, 80% of the work that I'm doing is pretty much on device, on local servers, processing real-time computer vision on multiple cameras. Then we need to know some messaging protocols, messaging frameworks, and so on. So we have Redis, we have different databases and so on that you need to know. Could be MongoDB, Postgres, SQL, SQLite, and so on. Really depends on your system. If you have some lightweight systems where you can store it locally and so on, might be that you don't want to send your data somewhere. You can use SQLite, basically just for fast processing. It's very lightweight and easy to work with. And also some messaging protocol, messaging broker, and so on, depending on your system. Could be RabbitMQ, MQTT, and so on. But also a very cool one for real-time video analytics is ZeroMQ. So it's just very lightweight. It's basically just a queue. You can send the data in there. You can connect to it on your network. You can deploy it in cloud-based solution systems as well, and then you basically just have that as your messaging broker or like the protocol. You can connect individual nodes and so on. So it depends on the messaging. Some of them have like server and node, so each node sent to the server, and then it basically just works as a network. With ZeroMQ, we can connect communication directly between two nodes. It's very lightweight. We can connect images, metadata, and so on. So this is also very important to know, and I bet that 90% of people, like, they have no idea about all of these things, because most of it is actually like software development, backend engineering, and so on, but we need to know it as AI and computer vision engineers as well, especially if you want to build standalone systems and be able to stand out there, because most people don't know this. Then we can go and do some monitoring. We can use Prometheus, Grafana, and so on for dashboards. So basically just how we can stream our data, show visualizations, could be object counts and so on for our real-time counting system. That is very good to just have a dashboard. We can also build some custom UIs. I'm using Streamlit a lot as well, just for making quick proof of concepts. You can stream all your data there. It works locally. You can also build custom UIs and so on. So this is pretty awesome. Basically just we need some dashboard for monitoring of our computer vision system. Most of them is running locally, so it's really easy to just have some dashboards. Grafana, custom dashboards, and Streamlit is very powerful. Then we need some API development. Also, depending on your UI, you can have very specialized, very custom UIs, and even high level ones as well. But we also need the backend system. We need to connect to databases. We don't just want to throw our information out of the window. Like most of the time, we just get our results from our system. We show it inside our video stream. We just show the count in the top left corner in our pre-recorded video, but we actually need to store that data in our database somehow. And if we want to show it in a UI, we need to have all these APIs up and running. So Fast API is very strong for that. gRPC, also very good, just how REST APIs work in general. WebSockets, you can just connect WebSockets if you work locally and so on for communication back and forth across the internet. All of these things here, we need to know them as computer vision engineers, because this is 80% of the work. If we don't know any of this, we can't put our models into production, act like applied on real world use cases. And this is very important, because I feel there's a huge gap between going from university, traditional education, or basically just if you're learning it by yourself and so on, you might not think about these things here. You might just be very focused on actually knowing, okay, what does this activation function do? What is the theory going behind our network, backpropagation? How do I write out the formula for backpropagation? Like if you're in university, you go to an exam for machine learning AI, like they're going to ask you to write out the backpropagation formula. It doesn't matter at all in the real world. We just need to know high level, how does it work? Okay, backpropagation, this is how our network works. It's way better to know Docker, Kubernetes, Prometheus, Grafana, Fast API, how we connect systems together and build full system architectures. So I hope you learned a ton this video here. I'm definitely going to create way more videos about this in the future, because it's so important, and we're also going to dive into more details. I'm going to create full courses. We already teach this within my AI career program. We have a focus on building real world systems, because this is the way to stand out, do freelance work, get better job offers, and basically just grow your network, get out there, stand out. Because most people, you don't have to do a lot, because most people, they just focus on the theory, or at least put 90% of the effort into the theory, where you should put 90% into the software architectures and systems. When you're building computer vision applications and projects, it's very important to choose the best camera. There's tons of different options out there, and it's actually very hard to find a specific camera that you can use. It really depends on the use case, the problem that you're trying to solve, and there's tons of different options out there in the camera world. So in this video, we're going to cover some of the details, why you should choose one camera over another, but also just in general. We will highlight some different areas that you need to take into account, and also think about when you're going to choose a camera. Do we need depth information? Do we need RGB camera? This is standard camera. Are we going to use CCTV cameras for some monitoring systems? Do we need a machine vision, like a real industrial camera? What lenses, what sensors? All of these questions here, if you're not familiar with it, even computer vision engineers and so on, they struggle a lot with finding the best hardware, cameras and so on, because they're just stick to doing all the development, Jupyter notebooks and so on, coming up with the systems. But when we want to take computer vision system models and so on and put them out in production and have real world impact, we actually need to have physical cameras. It's much more computer vision engineering. It's much more than just running YOLO models, running detection models, and so on. We need to build systems around it, but also be able to deal with hardware. So right now, the first factor that you need to take into account is basically just, do I need a specific camera? In most cases, you can get away with a standard camera. You can pretty much use whatever. Are you going to use a video stream? You just have a camera. Like, are you going to have a live stream, USB stream? There's a lot of cameras that just runs on USB. You just plug it into your device that you're going to run it on. Could be an RGB stream that you stream over the network, but just a standard RGB camera. Most often you don't need more than 1080p, because when we run our computer vision models in real time and in production, depending on your use case, for example, could be that you want like very high detail, you don't care about real time, you can get 1080p, 2K, or like even 4K resolution. So if you want to run real time, most applications and projects, it's real time computer vision, 30 frames per second at least. Then we can actually get away with even 720p, but most cameras today is at least 1080p. So that's 1920 by 1080p, which is basically just full HD. So most camera, they come with that. It's more than enough for most use cases and applications. We don't need anything specific, and you can get away with that. Low-end cameras like 50 to 100 bucks, you have a very good RGB camera that can capture like video stream, and you can start run applications and projects on top of that. Just for testing it out, like just if you're learning stuff and so on, you can use whatever camera. Then when you put it into production, you can always like get another camera. Maybe you need to do some modifications. If you do classical computer vision and so on, you might need to make some modifications for each camera. But if you're using like deep learning based approaches, trained it on enough data and so on, you can act like get away with converting it to another camera. You can train on different cameras and so on, and you'll just be able to generalize better. So that's a standard camera. You can get away with that. Could even like just be a webcam or whatever, any camera that you can just hook up easily and buy on Amazon or whatever platform. 30 frames per second, also more than enough for most applications. If we need more frames per second, and this doesn't just apply for RGB cameras, could be any type of camera, any like machine camera and so on. We also need to take into account frames per second. So we have image sensor, we have lenses, we have number of frames per second, and also what type. So do we need depth information? Do we just need RGB and so on? Because we have ton of different camera options and also image types. We also have thermal imaging, multispectral imaging, where we basically look at spectrums without like the human eyes, or the human's eyes can't see. So RGB is basically just the wavelengths that the human eyes can see, but we can have multispectral imaging as well, where we can actually see a whole lot of wavelengths more, and even details that is very specific. Could be that you want to run some manufacturing inspection system in your production. Could be apples, potatoes, and so on that could have defects or just anomalies on them that you can't see with the human eye, but you can see them with a multispectral image. Thermal imaging, if you want to capture some temperature, could be fire detection, could be smoke detection and so on, or leakage. That's also very good use cases for those types of cameras. Image sensor, frames per second, resolution, those are like the main factors, and also lenses if you go for a machine vision camera. Right now, we also have depth cameras. You have stereo cameras where you do some math and get distance based on that. You will get centimeter accuracy. There's also cameras like the Z2i. Then you can also get centimeter accuracy, but you can get up to 20 meter accuracy with that camera. It's probably the best production camera out there. If you need a stereo camera, you need a depth map and so on, then it's definitely the best. They also have like the Intel RealSense cameras and all that, but they're not even anywhere near the Z cameras. They're also more expensive, but it's pretty much the best of the best out there, and they also have a nice SDK. So that's a very good usual combo. Also, if you're using NVIDIA Jetson devices, it's very compatible with that. So it's a very strong using the Z2i and also NVIDIA Jetson board together. You could use the RealSense, but it's a bit outdated, and you might be able to get around with it with some other camera solutions. They also have the OpenCV OD boards, also just a stereo camera where you can get depth information. We can go even more hardcore and have time of flight cameras as well. So all the other cameras, they're passive cameras where time of flight, lidars and so on, they're active sensors, so they actually like send something out. Could be sound, could be light and so on, which basically just reflects. So we're capturing how long does it actually take to send out the signal. It will bounce on the objects, we will get the signal back, and we can capture how long it actually took for the signal to get back. And by using that information, we can calculate the depth to objects. And if we just send enough out there, it works the exact same way with lidars, then we get a pretty nice depth information and understanding of our environment around the camera. We also have laser scanners, lasers and all that, but that's for very specific use cases. These are all the types of imaging techniques, images types that we have, but for most use cases and applications, it's just a camera, RGB camera as we're used to. Right now I want to dive more into details with machine vision cameras because that's very important, especially if you're doing like real world production based systems where we both need to take temperatures into account. We need the best of the best, not too much variation from camera to camera, and act like have a stream up and running. We can have a fixed camera that needs to work in very specific environments. So I've just jumped straight into the Basel websites here. There's tons of different manufacturers for machine vision cameras, but this is a pretty good one. So if I just go inside the products, they have a bunch of different cameras, area scan cameras, line scan cameras if you only want to scan in one specific line. Sphere if you want to use short wavelength infrared cameras, so that could be like in different environments. If you have a cloudy environment and so on, you can act like see through the fog, clouds and all that by using some like short wavelength infrared cameras. You can also use long wave infrared cameras, basically just to capture information about how are people moving. Let's say that you want to have a detection system where people are moving behind fog or something. You can actually detect that with these types of cameras. They also have 3D cameras, so we have time of flight, stereo and RGB cameras, which was basically just what I covered. But right now, let's go inside our all cameras tab. We have some different search filters, which is basically just the different parameters that we just talked about with the resolution, frame rate. We also have the interfaces. We can take into account the sensor format, different lenses that we can put on top of the cameras. But if you don't know, it's very important for a computer vision engineer to know about cameras, what do we need and so on. But don't just go out there and buy these cameras if you don't need them for a very specific reason. If you have a factory or production line where we need the best of the best, this is definitely the way to go. But if you're creating some high level or smaller base projects and so on, it's really expensive to go out and put up 500 to 1k euro or dollars for just a camera. Then you also need a lens on top of that. So that's going to be a very expensive upfront investment, but in some cases you need to do it to get the best quality. And if you're doing like real world production systems, this is definitely needed. But even when we look at the machine vision cameras here, tons of different options. Here we can even see that there's 462 products, and this is just from one manufacturer. There's so many options out there, and you will get lost if you don't know exactly what to look for, and also for your specific application and projects. First of all, we have the resolution in megapixels, depending on if you want to use it as a camera or a video camera. If you want to stream it, that's also a very important factor. Sometimes you just want to capture an image based on an event, process that image and do something with that result. Could also be that we have a production line running on a conveyor belt where we need to capture real-time information, so that's also a factor. If you just look at it here, we can just specify the megapixels that we want to use. The one here, this is a pretty standard camera, IMX sensor, 31 frames per second. We have 12.5 megapixel resolution and almost 3.5K by 3.5K. So this is a square format, USB 3, and we also have the sensor format here. So this is also a pretty standard sensor format, but we have sensor time, sensor format, frame rate. So these are the most essential parameters, or basically just factors that we need to take into account. This camera here comes up at the first one. It's a pretty good option, but they also have tons of other ones over here. Right now, let's go down and filter some of them because these are for very specific use cases. So for example, features, let's not cover that. Interface, we have USB, GigE, which is basically just a network protocol. We have 5 GigE if you want to run the cameras even faster. Of course, there's always a trade-off between accuracy, performance, quality, and cost. So definitely make sure that you take that into account. And it pretty much, as anything out there in the whole world, it goes hand in hand. USB 3 is pretty much if you have like some short distance systems, like a couple of meters and so on, that you can hook directly into the computer or the processing power. Could be that you have an edge device sitting at each camera. That could be a very good use case with Jetson Nano. I have a full Jetson system up and running over here in the back that I'm just using if I need that system. So if you have a camera, you can connect. USB 3 is a very good option, but it just requires that your processing power is pretty close. If you want to run it like 10-20 meters to some server, or have a network protocol streaming service up and running that you just connect your cameras to, we need to go into some of the other options here. Could also be a camera link, but the most important options, or the best options, is like 5 GE for smaller or lower budget, and also USB 3. USB 3 is not going to process, it's not going to be able to send as much data as the GE, so it depends on the frame rate that you need, the resolution, and also the distance that it needs to travel. Most people, they don't know about the distance that these different interfaces can travel as well. This is actually like a very important factor that most people don't take into account when they're looking for cameras. So right now, let's just go in and take a look at the USB 3 options. Now we have a 31 frame per second camera. We have an IMX sensor, the same as before. If you scroll a bit further down, we can see we have a 500 frames per second camera here. We have a 23 frame per second camera here with a very high resolution. We can see if we bump up the frames per second, this is a very high speed camera, but then we also lose a lot of resolution. But again, when we use the object detection model and so on, we often downscale it to like 640 by 640 or even 480 by 480. So this could be a very good option as well if you just have like a production line where it's just like running very fast. Then we can go in and take a look at some of the other options. 75 frames per second, we get higher resolution, so it pretty much just goes hand in hand. Sensor format, 2/3 tommer here, probably the best standard, or not the best standard, but this is pretty much just like a standard sensor format. And also this IMX sensor, I really like that. I think it's from Sony that creates those types of sensors. So yeah, this is the USB 3. Now let's go down and take a look at the 5 GE. Let's get rid of the USB. And now we can see we get cameras significantly more expensive because this can travel over longer distances. This is probably a good option. We get our good enough pixel resolution. We have 160 frames per second if we have production line running fast. So yeah, this is basically the trade-off. What interface do we need? USB, internet protocol. What are the different features? We're not looking at that. Shutter, rolling shutter, global shutter, depending on like how fast your objects are moving. If you want to reduce, if you have blurry images and so on, this is something that you can take into account. Have different sensor types. Again, these IMX sensors are like the pretty standard. So just go with the standard format if you're not 100% sure what you're looking for. Sensor format, again, let's see. We can see that we have this one here is a pretty common one, and then we also have this one here, which is also a nice standard that is often used. Pixel size, don't really care too much about that. We have a lens mount, so that could be different options. Basler here is using C mounts. Just make sure when you buy a lens that it's compatible with your camera house as well. C mount, pretty standard format as well. We have spectrum, visible, UV. We have price categories, camera categories, area scan, line scan, and we also have the series. But the trade-off here is how many frames per second do we need? We only need 30 frames per second for most applications. If you have high-speed applications, could also be that you want to do a line calling system in tennis, analyze a golf swing, analyze a tennis serve, and so on. 30 frames per second is not enough because it's only like the whole action only happens in like 200 milliseconds. So that will only be 8 frames that we get to do our analysis on. Then it will be better to bump it up to 60 frames per second, 100 frames per second, and so on. If you use a standard camera, not a machine camera, we will not be able to get these high frame rates at 120, 200, 500 frames per second. Then we definitely need like these higher end cameras. IMX 250 is also a pretty standard sensor. So if you're looking for a high frames per second camera, this is a very good option. You get high resolution, get the 5 GE, you get the standard sensor format, IMX 250, 100 frames per second, and very good resolution. So this is a good option if you're looking for a high-speed camera with a lot of frames, and you can get away with 100 frames per second. Of course, if you need more, you will need to bump that up. But everything can be searched over here in the left side. All the other platforms, all the other manufacturers, they work in the exact same way. They have all the different options. We can see that this is pretty much the exact same camera. It's just lower frames per second, and we have the USB-free protocol, but it's also more than like half the price compared to the other one. So once we've chosen our camera, it's also very important that we go in and find the lenses. So let's go and take a look at the lenses. We're just going to go with all lenses. You can have fixed focal lengths, you can have telecentric lenses. Most often we just want like a fixed lens. It depends on your working distance, how far you're working away. Do we need a fisheye lens? Do we need to like cover a large field of view when we are close to the production line, or whatever use case that we're using our camera for? So this is very important as well. Most often around 25 millimeter in focal length, if more than fine if you just have like a standard working distance and don't have something specific to look for. So the first cameras that I showed you, 30 frames per second, 3K resolution, USB-free protocol, and then take a lens here that has like a 25 millimeter focal length, then you're pretty much good to go in most use cases. When you have to go for a machine vision camera, most cases you don't really even need a machine vision camera. You can get away with CCTV camera, some other camera, even if you're creating computer vision applications with your phone. If you're creating apps for different sports analytics, you can get away with other cameras compared to the machine vision. But if you're working in production, manufacturing, all these different environments, definitely just go with the machine cameras and take the standard option that I just mentioned here, especially if you don't know what exactly you're looking for. So right now we can go inside the C-mount lenses. Here we see the first one is basically just a 50 mil. We have 35 mil here, and we also have a 25. So this is a standard lens. This is pretty good. This is pretty good format. So right now I'm probably like a meter away from the camera, and I'm using 25 millimeters. So you can pretty much see like what you can see. We don't really get too much distortion and all that. So it's a really good option. This one here will work. So we can see that the working distance, they even specified that. So that's 1.5 meters. So we can see here that they even specified the working distance. And these are pretty standard lenses. This is a very zoomed in lens if you go for 50 mil. So the higher focal length that you have, the more zoomed in it's gonna be. And again, the lower, the more field of view you're going to get, or it's basically just going to see further closer to the actual like objects. So size 16 mil, 8.6 mil, that's if you're like either very close or you need a very large field of view. Could be that you need your camera to sit like 10-20 centimeters away from something, but you still want to be able to detect what's going on and cover the distance. That could be constraints in your environment, could be how your production line is set up and all that. So that's basically what the lens is for. The camera, the resolution, frame rate and all that, that's those specifications. The lens is basically just for capturing image at a specific distance. Depending on field of view, we can see the sensor format, so what it's compatible with. This is some pretty standard ones. 100 mil, also a very nice sensor. 12 mil, 4 mil, this is like a very, here you probably get a very fisheye lens, or at least a very zoomed out image. So the other ones we looked at, we had cameras around $500 for a standard machine vision camera, and then we can probably find a lens here. Let's say that we go for this one. This will probably be a very good option, or maybe this one down here. So $100-200 on average, but that's also $700 for a camera. So this is a very expensive camera, but it's also going to provide the best of the best, which is required in most applications and projects. If you get into industrial manufacturing and those use cases, this is overkill. If you're just creating some sports analytics system, or you're creating a hobby project and so on, this is obvious that this is too overkill. But as a computer vision engineer working in companies and so on, it is so important that we still know how to choose the correct camera. What are the different parameters? What should we look for? because most people, they don't know about the working distance, the focal length. How does the focal length affect the frame or the image? How does the travel distance that need to travel with the interface, RGPS stream, USB, Gig E, or how do we actually connect to it? Because there could be constraints, and most often we have to find the camera that fits into our environment. I hope you learned a ton this video here. This is all the different factors for just standard cameras. Also cover some of the other image types. I'm going to cover that in future videos, how to choose the best depth camera if you want to have line scanners, but this is just for raw computer vision with RGB frames. Both if you're just low end, want to find a camera $50-100 with USB interface that you can use for your system, or if you want to go full hardcore and know how we can actually get full scale machine vision cameras, we also cover that. Hope you learned a ton. This is so important for computer vision engineers or companies, corporations looking to get into the computer vision systems. Try to implement some of this stuff here, build systems around it, solve some use cases, have some inspection systems. Could be checking anomalies, could also just be verification, inspection on a production line, conveyor belt, whatever. These are very good cameras for that. All other platforms, all other websites and so on, they're very similar to this one here. I just wanted to show you. I have no affiliates or anything, but these are some pretty good ones and gives a good overview over the different factors. If you just look at the mount, make sure that the mount works, sensor format, the focal length that you have for your lens. We have the resolution, frame rate, interface, and also just do we actually need a machine vision camera. Hope you learned a ton. Hope to see you guys in one of the upcoming videos. Until then, happy learning.